Welcome to Apache Spark for Beginners, a video course by Pact Publishing. Hi, I'm Doug, and I'll be the voice of Raj for this video course. Rajanarayan Totuvakutumana is a seasoned technologist with more than 23 years of software development experience at various multinational companies. He has lived and worked in India, Singapore, and the USA, and is presently based out of the UK. His experience includes architecting, designing, and developing software applications. He has worked on various technologies including major databases, application development platforms, web technologies, and big data technologies. Since 2000, he has been working mainly in Java-related technologies and does heavy-duty server-side programming in Java and Scala. Currently, he's building a next-generation Hadoop Yarn-based data processing platform and an application suite built with Spark using Scala. Raj holds one master's degree in mathematics, one master's degree in computer information systems, and has many certifications in ITIL and cloud computing to his credit. Raj is the author of Cassandra Design Patterns 2nd edition, published by Pact. Spark is one of the most widely used large-scale data processing engines and runs extremely fast. It is a framework that has tools that are equally useful for application developers as well as data scientists. We will begin our journey with Spark Fundamentals, which discusses the fundamentals of Spark as a framework with its APIs and the libraries that comes with it, along with the whole data processing ecosystem Spark is interacting with. Next, in Section 2, Spark Programming Model, we will dive into the uniform programming model based on the tenets of functional programming methodology that is used in Spark. And we will cover the fundamentals of resilient distributed data sets, that is RDD, Spark transformations, and Spark actions. Section 3 will walk you through Spark SQL, which is one of the most powerful Spark libraries used to manipulate data using the ubiquitous SQL constructs in conjunction with the Spark DataFrame. Section 4 will take you through Spark programming with R. It will give you a very good foundation for R to get acquainted with the Spark data processing ecosystem. In Section 5, we will have a look at the use of Spark to do data processing and Python to do data analysis, using a wide variety of charting and plotting libraries available for Python. After this, we will move on to Section 6, Spark Stream Processing, and learn Spark Streaming, which is one of the most powerful Spark libraries to capture and process data that is ingested as a stream. Then we will move on to Section 7, Spark Machine Learning, and we'll explore few powerful Spark libraries used to develop machine learning applications at an introductory level. In the second last section of this video course is Spark Graph Processing. We will cover the basics of GraphX and some use cases implemented using the algorithms provided by GraphX. Finally, in the last section, we will explore the design and development of a Spark data processing applications and cover various features of Spark. By the end of this video course, you'll be able to combine the data processing power of Spark with R and consolidate data processing, stream processing, machine learning, and graph processing into one unified and highly interoperable framework with a uniform API using Scala or Python. You will have all the knowledge you need to develop efficient, large-scale applications using Apache Spark. So, what do you need for this course? Spark 2.0.0 or above is to be installed on at least a standalone machine to run the code samples and do further activities to learn more about the subject. For Section 6, Spark Stream Processing, Kafka needs to be installed and configured as a message broker with its command line producer producing messages and the applications developed using Spark as a consumer of those messages. So, what are you waiting for? Let's jump right in and begin the journey. I am sure you'll have fun being with me and learning throughout the course. Hi, welcome to the first video of the first section, Spark Fundamentals. In this section, we will have a look at the overview of Apache Hadoop. We will then understand Apache Spark, and at the end of this section, we will install Spark 2.0. Now, we move on to the first video of this section that will give you an overview of Apache Hadoop. In this video, we're going to take a look at the overview of Apache Hadoop. We will explore the Apache Hadoop framework and the MapReduce process. There are two open-source data processing frameworks that are worth using that satisfy all major requirements. The first being Apache Hadoop, and the second one is Apache Spark. Apache Hadoop is an open-source software framework designed from ground up to do distributed data storage on a cluster of computers and to do distributed data processing of the data that is spread across the cluster of computers. This framework comes with a distributed file system for the data storage, namely Hadoop Distributed File System, HDFS, and a data processing framework, namely MapReduce. The creation of HDFS is inspired from the Google research paper, the Google File System, and MapReduce is based on the Google research paper MapReduce, Simplify Data Processing on Large Clusters. Hadoop was adopted by organizations in a really big way by implementing huge Hadoop clusters for data processing. It saw tremendous growth from Hadoop MapReduce version 1, MRV1, to Hadoop MapReduce version 2, MRV2. From a pure data processing perspective, MRV1 consisted of HDFS and MapReduce as the core components. Many applications, generally called SQL on Hadoop applications, such as Hive and Pig, were stacked on top of the MapReduce framework. It is very common to see that even though these types of applications are separate Apache projects, as a suite, many such projects provide great value. The Yet Another Resource Negotiator, YARN project, came to the fore with computing frameworks other than MapReduce type to run on the Hadoop ecosystem. With the introduction of YARN sitting on top of HDFS, and below MapReduce in a component architecture laying perspective, the users can write their own applications that can run on YARN and HDFS to make use of the distributed data storage and data processing capabilities of the Hadoop ecosystem. In other words, the newly overhauled MapReduce version 2, MRV2, became one of the application frameworks sitting on top of HDFS and YARN. The figure which you see gives a brief idea about these components and how they are stacked together. MapReduce is a generic data processing model. The data processing goes through two steps, namely map step and reduce step. In the first step, the input is divided into a number of smaller parts so that each one of them can be processed independently. Once the map step is completed, its output is consolidated, and the final result is generated in the reduce step. In a typical word count example, the creation of key value pairs with each word, as the key and the value 1 is the map step. The sorting of these pairs on the key, summing the values of the pairs with the same key, falls into an intermediate combine step. Producing the pairs containing unique words and their occurrence count is the reduce step. From an application programming perspective, the basic ingredients for an oversimplified MapReduce application are the input location, the output location, map function, which is implemented for the data processing need from the appropriate interfaces and classes from the MapReduce library, and the reduce function that is implemented for the data processing need from the appropriate interface and classes from the MapReduce library. The MapReduce job is submitted for running in Hadoop, and once the job is completed, the output can be taken from the output location specified. This two-step process of dividing a MapReduce data processing job to map and reduce tasks was highly effective and turned out to be a perfect fit for many batch data processing use cases. There is a lot of input-output I/O operations with the disk happening under the hood during the whole process. Even in the intermediate steps of the MapReduce job, if the internal data structures are filled with data or when the tasks are completed beyond a certain percentage, writing to the disk happens. Because of this, the subsequent steps in the MapReduce jobs have to read from the disk. Then, the other biggest challenge comes when there are multiple MapReduce jobs to be completed in a chained fashion. In other words, if a big data processing work is to be accomplished by two MapReduce jobs in such a way that the output of the first MapReduce job is the input of the second MapReduce job. In this situation, whatever may be the size of the output of the first MapReduce job, it has to be written to the disk before the second MapReduce could use it as its input. So in this simple case, there's a definite and unnecessary write operation. In many of the batch data processing use cases, these I/O operations are not a big issue. If the results are highly reliable for many batch data processing use cases, latency is tolerated. But the biggest challenge comes from when doing real-time data processing. The huge amount of I/O operations involved in MapReduce jobs makes it unsuitable for real-time data processing with the lowest possible latency. Cool! In this video, we dived into the overview of Apache Hadoop. In the next video, we will explore Apache Spark. In the previous video, we looked at the overview of Apache Hadoop. In this video, we will explore Spark and its advantages. We will also go through the Spark libraries and then dive into Spark programming paradigm. Spark is a Java virtual machine-based distributed data processing engine that scales, and it is fast compared to many other data processing frameworks. Spark was originated at the University of California, Berkeley, and later became one of the top projects in Apache. The research paper Mesos, a platform for fine-grained resource sharing in the data center, talks about the philosophy behind the design of Spark. You can read the complete research paper at this web documentation. The biggest claim from Spark regarding speed is that it is able to run programs up to 100 times faster than Hadoop MapReduce in memory, or 10 times faster on disk. Spark could make this claim because it does the processing in the main memory of the worker nodes and prevents the unnecessary I/O operations with the disks. The other advantage Spark offers is the ability to chain the tasks, even at an application programming level, without writing onto the disk at all or minimizing the number of writes to the disks. How did Spark become so efficient in data processing as compared to MapReduce? It comes with a very advanced directed acrylic graph DAG data processing engine. What it means is that for every Spark job, a DAG of tasks is created to be executed by the engine. The DAG in mathematical parlance consists of a set of vertices and directed edges connecting them. The tasks are executed as per the DAG layout. In the MapReduce case, the DAG consists of only two vertices, with one vertex for the map task and the other one for the reduce task. The edge is directed from the map vertex to the reduce vertex. The in-memory data processing combined with its DAG-based data processing engine makes Spark very efficient. In Spark's case, the DAG of tasks can be as complicated as it can. Thankfully, Spark comes with utilities that give excellent visualization of the DAG of any Spark job that is running. The web application that comes with Spark is capable of monitoring the workers and applications. The DAG of the preceding Spark job generated on the fly looks like this figure. The Spark programming paradigm is very powerful and exposes a uniform programming model supporting the application development in multiple programming languages. Spark supports programming in Scala, Java, Python, and R, even though there is no functional parity across all the programming languages supported. Spark has an interactive shell with read, evaluate, print, and loop repo capabilities for the programming languages Scala, Python, and R. At this moment, there is no repo support for Java in Spark. The Spark repo is a very versatile tool that can be used to try and test Spark application code in an interactive fashion. The Spark repo enables easy prototyping, debugging, and much more. In addition to the core data processing engine, Spark comes with a powerful stack of domain-specific libraries that use the core Spark libraries and provide various functionalities useful for various big data processing needs. This table lists the supported libraries. In any distributed application, it is common to have a driver program that controls the execution, and there will be one or more worker nodes. The driver program allocates the tasks to the appropriate workers. This is the same even if Spark is running in standalone mode. In the case of a Spark application, its Spark context object is the driver program, and it communicates with the appropriate cluster manager to run the task. The Spark master, which is part of the Spark core library, the Mesos master, and the Hadoop Yarn resource manager are some of the cluster managers that Spark supports. In the case of a Hadoop Yarn deployment of Spark, the Spark driver program runs inside the Hadoop Yarn application master process, or the Spark driver program runs as a client to the Hadoop Yarn. This figure which you see describes the standalone deployment of Spark. In the Mesos deployment mode of Spark, the cluster manager will be the Mesos master. Here is the figure describing the Mesos deployment of Spark. The next figure describes the Hadoop Yarn deployment of Spark. In the Hadoop Yarn deployment mode of Spark, the cluster manager will be the Hadoop resource manager, and its address will be picked up from the Hadoop configuration. In other words, when submitting the Spark jobs, there is no need to give an explicit master URL, and it will pick up the details of the cluster manager from the Hadoop configuration. Spark runs in the cloud too. In the case of deployment of Spark on Amazon EC2, apart from accessing the data from the regular supported data sources, Spark can also access data from Amazon S3, which is the online data storage service from Amazon. In this video, we saw in-depth Apache Spark with its libraries and deployment modes. In the next video, we will go ahead and install Spark on our machine. Hey, we are now at the last video of this section, installing Spark on your machine. In the previous video, we dived into what Apache Spark is. In this video, we will install Spark on our machine. We will first do Python installation, and then we will install R. After this, we will install Spark and the development tools. We will also have a look at how to install optional software. Spark supports application development in Scala, Java, Python, and R. In this video, Scala, Python, and R are used. Here's the reason behind the choice of the languages for the examples in this video. The Spark Interactive Shell, or REPL, allows the user to execute programs on the fly, just like entering OS commands on a terminal prompt, and it is available only for the languages Scala, Python, and R. REPL is the best way to try out Spark code before putting them together in a file and running them as applications. REPL helps even the experienced programmer to try and test the code and thus facilitates fast prototyping. So, especially for beginners, using REPL is the best way to get started with Spark. As a prerequisite to Spark installation and to do Spark programming in Python and R, both Python and R are to be installed prior to the installation of Spark. Let us visit www.python.org for downloading and installing Python for your computer. Go to the Downloads tab and select the version which you need. I select here Python 3.5.2. Once the installation is complete, make sure that the required binaries are in the OS search path and the Python interactive shell is coming up properly. Let us now open the Python shell to check our installation. For charting and plotting, the matplotlib library is being used. Even though Spark supports programming in Python version 2.7, as a forward-looking practice, the latest and most stable version of Python available is used. Moreover, most of the important libraries are getting ported to Python version 3 as well. You can visit matplotlib.org for downloading and installing the library. To make sure that the library is installed properly and that charts and plots are getting displayed properly, you can also visit the matplotlib.org/examples/index.html page to pick up some example code and see that your computer has all the required resources and components for charting and plotting. While trying to run some of these charting and plotting samples in the context of the import of the libraries in Python code, there is a possibility that it may complain about the missing locale. In that case, set the following variables in the appropriate user profile to get rid of the error messages. Let us now install R. For this, you can visit www.r-project.org. Once the installation is complete, make sure that the required binaries are in the OS search path and the R interactive shell is coming up properly.
Welcome to Apache Spark 2 for Beginners,
As you
a
run
video
the R
course by
command,
Pact
the shell
Publishing.
should display this content.
You can note that R version 3.3.1 is the choice for R.
Spark installation can be done in many different ways. The most important prerequisite for Spark installation is that the Java 1.8 JDK is installed in the system, and the Java_home environment variable is set to point to the Java 1.8 JDK installation directory. So let's visit spark.apache.org/downloads.html for understanding, choosing, and downloading the right type of installation for your computer.
Spark version 2.0.1 is the version of choice for all examples given in this video course.
If you're interested in building and using Spark from the source code, you should visit http://spark.apache.org/docs/latest/building-spark.html for the instructions. By default, when you build Spark from the source code, it will not build the R libraries for Spark. For that, the Spark R libraries have to be built and the appropriate profile has to be included while building Spark from source code. This command shows how to include the profile required to build the Spark R libraries. Once the Spark installation is complete, define these environment variables in the appropriate user profile. If there are multiple versions of Python executables in the system, then it is better to explicitly specify the Python executable to be used by Spark in the environment variable setting. In the PySpark script, there is a block of code that determines the Python executable to be used by Spark. So it is always better to explicitly set the Python executable for Spark, even if there is only one version of Python available in the system. This is a safeguard to prevent unexpected behavior when an additional version of Python is installed in the future. Once all these steps are completed successfully, make sure that all the Spark shells for the languages Scala, Python, and R are working properly. So, let's now move to the Spark home directory and run the commands on the OS terminal prompt and make sure that there are no errors. And here we run the set of commands to bring up the Scala REPL of Spark. In this display, which you see on your screen, verify that the JDK version, Scala version, and Spark version are correct as per the settings in the computer in which Spark is installed. The most important point to verify is that no error messages are displayed. Next, we run the set of commands to bring up the Python REPL of Spark. Here, verify that the Python version and Spark versions are correct as per the settings in the computer in which Spark is installed. The most important point to verify is that no error messages are displayed. Now again, we run set of commands to bring up the R REPL of Spark in a similar way. In this display, verify that the R version and Spark version are correct as per the settings in the computer in which Spark is installed. The most important point to verify is that no error messages are displayed. As a final test, let us run some of the example programs that came with Spark and make sure that they are giving proper results and not throwing any error messages in the console. If all the REPL for Scala, Python, and R are working fine, it is almost certain that the Spark installation is good. When these example programs are run, apart from the output you see below the commands, there will be a lot of other messages displayed in the console. They are omitted to focus on the results. Let us now step ahead and install the development tool. Most of the code that is going to be used in this video course can be tried and tested in the appropriate REPL. But the proper Spark application development is not possible without some basic build tools. As a bare minimum requirement for developing and building Spark applications in Scala, the Scala build tool, SBT, is a must. You can visit http://www.scala-spt.org for downloading and installing SBT. Maven is the preferred build tool for building Java applications. This video course is not talking about Spark application development in Java, but it is good to have Maven also installed in the system. Maven will come in handy if Spark is to be built from source. You can visit https://maven.apache.org for downloading and installing Maven. There are many integrated development environments, IDEs available for Scala as well as Java. It is a personal choice, and the developer can choose the tool of his or her choice for the language in which he or she is developing Spark applications. Now let us have a look at optional software installation. Spark REPL for Scala is a good start to get into the prototyping and testing of some small snippets of code. But when there is a need to develop, build, and package Spark applications in Scala, it is good to have SBT-based Scala projects and develop them using a supported IDE, including but not limited to Eclipse or IntelliJ IDEA. You need to visit the appropriate website for downloading and installing the preferred IDE for Scala. Notebook-style application development tools are very common these days among data analysts and researchers. This is akin to a lab notebook. In a typical lab notebook, there will be instructions, detailed descriptions, and steps to follow to conduct an experiment. Then, the experiments are conducted. Once the experiments are completed, there will be results captured in the notebook. If all these constructs are combined together and fit into the context of a software program and modeled in a lab notebook format, there will be documentation, code, input, and the output generated by running the code. This will give a very good effect, especially if programs generate a lot of charts and plots. We now go ahead to see how to do IPython installation. In the case of Spark application development in Python, IPython provides an excellent notebook-style development tool, which is a Python language kernel for Jupyter. Spark can be integrated with IPython, so that when the Spark repo for Python is invoked, it will start the IPython notebook. Then create a notebook and start writing code in the notebook just like the way the commands are given in the Spark repo for Python. You can visit http://ipython.org to download and install the IPython notebook. Once the installation is complete, invoke the IPython notebook interface and make sure that some example Python code is running fine. Invoke commands from the directory from where the notebooks are stored or where the notebooks are to be stored. Here, the IPython notebook is stored from a temporary directory. When the following commands are invoked, it will open up the web interface, and from there, create a new notebook by clicking the New drop-down box and picking up the appropriate Python version. Let's now see how to combine a Markdown-style documentation and a Python program and the generated output together in an IPython notebook. Now here, select Python 3. Let us run some example here. So we copy a sample code from the matplotlib.org and then run it. So here is the combined output for the code which we just used. The IPython notebook can be used to write simple Python programs. The IPython notebook can be configured as a shell of choice from Spark, and when the Spark repo for Python is invoked, it will start up the IPython notebook, and Spark application development can be done using IPython notebook. To achieve that, we define some environment variables in the appropriate user profile, so we type the command for it in the command line terminal. Now, define these two variables and save the file. Now, instead of invoking the IPython notebook from the command prompt, invoke the Spark repo for Python. Just like what has been done before, create a new IPython notebook and start writing Spark code in Python. Now, we will read this JSON file, which comes along with Spark. Now, as you can see, we got the output for this code. In the standard Spark repo for any language, it is possible to refer the files located in the local file system with their relative path. When the IPython notebook is being used, local files are to be referred with their full path. Finally, let us see how to set up RStudio. Among the R user community, the preferred IDE for R is the RStudio. RStudio can be used to develop Spark applications in R as well. You need to visit https://www.rstudio.com to download and install RStudio. Once the installation is complete, before running any Spark R code, it is mandatory to include the Spark R libraries and set some variables to make sure that the Spark R programs are running smoothly from RStudio. So, you need to move to RStudio and set this path. Now, add this path. In this R code, change the Spark home directory variable definition to point to the directory where Spark is installed. Let's now run some sample code. Once all the required software is installed, configured, and working as per the details given previously, the stage is set for Spark application development in Scala, Python, and R. The Jupyter Notebook supports multiple languages through the custom kernel implementation strategy for various languages. There is a native R kernel, namely IR kernel, for Jupyter, which can be installed as an R package. In this section, we have seen the overview of Apache Hadoop. We also dived into the understanding of Apache Spark, and then we installed Spark on our machine. In the next section, we will see Spark programming model. Hi, and welcome to the second section of this course, Spark Programming Model. We will cover the following topics in this section: functional programming with Spark, Spark RDD, data transformations and actions, Spark monitoring, Spark programming basics, creating RDDs from files, Spark libraries. Now, we move on to the first video of Section 2, Functional Programming with Spark and Understanding Spark RDD. In this video, we will learn about functional programming with Spark and understanding Spark RDD. Extract, transform, and load, ETL tools, proliferated along with the growth of the data in organizations. The need to move data from one source to one or more destinations, processing it on the fly before it reaches its destination, were all the requirements of the time. Most of the time, these ETL tools were supporting only a few types of data sources and destinations, and were closed to extension to allow them to support new data types and new sources and destinations. Because of these stringent limitations on the tools, sometimes even a one-stop transformation process had to be done in multiple steps. These convoluted approaches mandated the need to have unnecessary wastage in terms of manpower, as well as other computing resources. The main argument from the commercial ETL vendors all the time remained the same: one size doesn't fit all. So, use our suite of tools instead of the point products available on the market. Many organizations got into vendor lock-in because of the profuse need to process data. Almost all the tools introduced before the year 2005 did not make use of the real power of the multi-core architecture of the computers if they supported running their tools on the commodity hardware. So, simple but voluminous data processing jobs took hours and sometimes even days to complete with these tools. Spark became an instant hit in the market because of its ability to process a huge amount of data types and a growing number of data sources and data destinations. The most important and basic data abstraction Spark provides is the Resilient Distributed Dataset, RDD. As discussed in the previous section, Spark supports distributed processing on a cluster of nodes. The moment there is a cluster of nodes, there's a good chance that when the data processing is going on, some of the nodes can die. When such failures happen, the framework should be capable of coming out of such failures. Spark is designed to do that, and that is what the resilient part in the RDD signifies. If there is a huge amount of data to be processed, and there are nodes available in the cluster, the framework should have the capability to split the big dataset into smaller chunks and distribute them to be processed on more than one node in a cluster, in parallel. Spark is capable of doing that, and that is what the distributed part in the RDD signifies. In other words, Spark is designed from the ground up to have its basic dataset abstraction capable of getting split into smaller pieces deterministically and distributed to more than one node in the cluster for parallel processing, while elegantly handling the failures in the nodes. The mutation of objects at runtime and the inability to get consistent results from a program or function because of the side effect that the program logic creates makes many applications very complex. If the functions in programming languages start behaving exactly like mathematical functions in such a way that the output of the function depends only on the inputs, that gives lots of predictability to applications. The computer programming paradigm, giving lots of emphasis to the process of building such functions and other elements based on that, and using those functions just in the way that any other data types are being used, is popularly known as the functional programming paradigm. Out of the JVM-based programming languages, Scala is one of the most important ones that has very strong functional programming capabilities without losing any object orientation. Spark is written predominantly in Scala. Because of that itself, Spark has taken lots of very good concepts from Scala. The most important feature that Spark took from Scala is the ability to use functions as parameters to the Spark transformations and Spark actions. Quite often, the RDD in Spark behaves just like a collection object in Scala. Because of that, some of the data transformation method names of Scala collections are used in Spark RDD to do the same thing. This is a very neat approach, and those who have expertise in Scala will find it very easy to program with RDDs. We will see a few important features in the following sections. Spark RDD is immutable. There are some strong rules based on which an RDD is created. Once an RDD is created intentionally or unintentionally, it cannot be changed. This gives another insight into the construction of an RDD. Because of that, when the nodes processing some part of an RDD die, the driver program can recreate those parts and assign the task of processing it to another node, ultimately completing the data processing job successfully. Since the RDD is immutable, splitting a big one to smaller ones, distributing them to various worker nodes for processing, and finally compiling the results to produce the final result can be done safely without worrying about the underlying data getting changed. Spark RDD is distributable. If Spark is run in a cluster node where there are multiple worker nodes available to take the tasks, all these nodes will have different execution contexts. The individual tasks are distributed and run on different JVMs. All these activities of a big RDD getting divided into smaller chunks, getting distributed for processing to the worker nodes, and finally assembling the results back are completely hidden from the users. Spark has its own mechanism for recovering from the system faults and other forms of errors which occurred during the data processing, and hence this data abstraction is highly resilient. Spark RDD lives in memory. Spark does keep all the RDDs in the memory as much as it can. Only in rare situations where Spark is running out of memory or if the data size is growing beyond the capacity is it written to disk. Most of the processing on RDD happens in the memory, and that is the reason why Spark is able to process the data at a lightning-fast speed. Spark RDD is strongly typed. Spark RDD can be created using any supported data types. These data types can be Scala Java supported intrinsic data types or custom-created data types such as your own classes. The biggest advantage coming out of this design decision is the freedom from runtime errors. If it's going to break because of a data type issue, it will break during compile time. This table captures the structure of an RDD containing tuples of a retail bank account data. It is of the type RDD, string, 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 double. Suppose this RDD is going through a process to calculate the total amount of all these accounts in a cluster of 3 nodes, N1, N2, and N3. It can be split and distributed for something such as parallelizing the data processing. This table contains the elements of the RDD. String, 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 double, distributed to node 1 for processing. This table contains the elements of the RDD string, 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 double, distributed to the node N2 for processing. On node 1, the summation process happens and the result is returned to the Spark driver program. Similarly, on node N2, the summation process happens, the result is returned to the Spark driver program, and the final result is computed. Spark has very deterministic rules on splitting a big RDD into smaller chunks for distribution to various nodes, and because of that, even if something happens to, say, node N1, Spark knows how to recreate exactly the chunk that was lost in the node N1 and continue with the data processing operation by sending the same payload to node N3. This will capture the essence of the process. Spark does a lot of processing in its driver memory and in the executor memory on the cluster nodes. Spark has various parameters that can be configured and fine-tuned so that the required resources are made available before the processing starts. Great! We've successfully learned functional programming with Spark and understanding Spark RDD. In the next video, we will see about data transformations and actions with RDDs. Hi! Welcome to the next video of Section 2, Data Transformations and Actions with RDDs. In the previous video, we learned about functional programming with Spark and understanding Spark RDD. So, let's move on to the topic. In this video, we will see about data transformations and the actions with RDDs. Spark does the data processing using the RDDs. From the relevant data source such as text files and NoSQL data stores, data is read to form the RDDs. On such an RDD, various data transformations are performed and finally the result is collected. To be precise, Spark comes with Spark transformations and Spark actions that act upon RDDs. Let us take this RDD capturing a list of retail banking transactions, which is of the type RDD string string double. To calculate the account-level summary of the transactions from the RDD of the form account no, tran amount. Number 1. First, it has to be transformed to the form of key-value pairs, account no, tran amount, where account no is the key, but there will be multiple elements with the same key. 2. On this key, do a summation operation on tran amount, resulting in another RDD of the form account no total amount, where every account no will have only one element, and total amount is the sum of all the tran amount for the given account no. 3. Now sort the key value pairs on the account no and store the output. In the whole process described, all are Spark transformations except the storing of the output. Storing of the output is a Spark action. Spark does all these operations on a need-to-do basis. Spark does not act when a Spark transformation is applied. The real act happens when the first Spark action in the chain is called. Then, it diligently applies all the preceding Spark transformations in order, and then does the first encountered Spark action. This is based on the concept called lazy evaluation. In the programming language context of declaring and using variables, lazy evaluation means that a variable is evaluated only when it is first used in the program. Apart from this action of storing the output to disk, there are many other possible Spark actions, including but not limited to some of the ones given in this list. Collecting all the contents in the resultant RDD to an array residing in the driver program. Counting the number of elements in the RDD. Counting the number of elements for each key in the RDD element. Taking the first element in the RDD. Taking a given number of elements from the RDD commonly used for top N reports. Taking a sample of elements from the RDD. Iterating through all the elements in the RDD. In this example, many transformations are done on various RDDs that get created on the fly till the process is completed. In other words, whenever a transformation is done on an RDD, a new RDD gets created. This is because RDDs are inherently immutable. These RDDs that are getting created at the end of each transformation can be saved for future reference, or they will go out of scope eventually. To summarize, the process of creating one or more RDDs and applying transformations and actions on them is a very common usage pattern seen ubiquitously in Spark applications. The table referred in the preceding data transformation example contains the values in an RDD of type the RDD string double. In this RDD, there are multiple elements, and each one is a tuple of the type string double. It is very common among programmers and the user community for easy reference and conveying ideas that the term record is being used to refer one to element in the RDD. In Spark RDD, there is no concept of records, rows, and columns. In other words, the term record is mistakenly used synonymously to an element in the RDD, which may be a complex data type such as a tuple or non-scalar data type. In this video course, this practice is highly refrained to use the correct terms. In Spark, there are a good amount of Spark transformations available. These are really powerful because most of these take functions as input parameters to do the transformation. In other words, these transformations act on the RDD based on the functions that are defined and supplied by the user. This becomes even more powerful with Spark's uniform programming model. Whether the programming language of choice is Scala, Java, Python, or R, the way Spark transformations and Spark actions are used is similar. This lets the organizations choose their programming language of choice. In Spark, even though the number of Spark actions are limited in number, they are really powerful, and users can write their own Spark actions if there is a need. There are many Spark connector programs that are available in the market, mainly to read and write data from various data stores. These connector programs are designed and developed either by the user community or by the data store vendors themselves to have connectivity to Spark. In addition to the available Spark actions, they may define their own actions to supplement existing sets of Spark actions. For example, the Spark Cassandra connector is used to connect Cassandra from Spark. This has an action saved to Cassandra. Awesome! In this video, we successfully learned about data transformation and actions with RDDs. In the next video, we'll learn how to monitor with Spark. Hi, welcome to the next video of Section 2, Monitoring with Spark. In the previous video, we learned about data transformations and actions with RDDs. So let's move on to the topic. In this video, we'll see how to monitor Spark. The previous section covered the details of the installation and development tool setup that is required for developing and running data processing applications using Spark. In most of the real-world applications, the Spark applications can become very complex with a really huge directed acrylic graph, DAG, of Spark transformations and Spark actions. Spark comes with really powerful monitoring tools for monitoring the jobs that are running in a given Spark ecosystem. The monitoring doesn't start automatically. First of all, there are some configuration changes to be made. The event logging mechanism should be turned on. For this, take these steps. Once these steps are completed, edit the newly created spark-defaults.conf file to have the following properties. Once these steps are completed, make sure that the previously used log directory exists in the file system. Apart from the preceding configuration file changes, there are many properties in that configuration file that can be changed to fine-tune the Spark runtime. The most important among them that is used frequently is the Spark driver memory. If the applications are dealing with a huge amount of data, it is a good idea to customize this property spark.driver.memory to have a higher value. Then run these commands to start the Spark master. Once the preceding steps are completed, make sure that the Spark Web User Interface, UI, is starting up by going to http://localhost:8080. The assumption here is that there is no other application running in the 8080 port. If for some reason there is a need to run this application on a different port, the command line option Web UI port can be used in the script while starting the web user interface. The web UI should look something similar to this. The most important information to be noted in the preceding figure is the fully qualified Spark master URL, not the REST URL. It is going to be used again and again for many of the hands-on exercises that are going to be discussed in this book. The URL can change from system to system and the DNS settings. Also note that throughout this book for all the hands-on exercises, Spark standalone deployment is used, which is the easiest among deployments to get started with a single computer. From the Spark Web UI, it can be noted that there are no worker nodes available to do any task and there are no running applications. These steps capture the instructions to start the worker nodes. Note how the Spark master URL is being used while starting the worker node. Once the worker node is started, in the Spark Web UI, the newly started worker node is displayed. The template captures the default working nodes that will be started with the invocation of the preceding command. If additional worker nodes are required, copy the slaves.template file to name it to slaves and have the entries captured in there. When a Spark shell, PySpark, or Spark R is started, instructions can be given to it using a given Spark master. This is useful when there is a need to run Spark applications or statements on a remote Spark cluster or against a given Spark master. If nothing is given, the Spark applications will run in the local mode. Once a worker node is started successfully, after this, if an application is run with the preceding Spark master URL, even that application's details will be displayed in the Spark Web UI. A detailed coverage of the applications is to follow in this chapter. Use these scripts to stop the workers and master processes. Awesome! In this video, we successfully learned about monitoring with Spark. In the next video, we'll learn the basic programming with Spark. Hi, welcome to the next video of Section 2, the basics of programming with Spark. In the previous video, we learned about monitoring with Spark. In this video, we will get to the basics of Spark programming. Spark programming revolves around RDDs. In any Spark application, the input data to be processed is taken to create an appropriate RDD. To begin with, start with the most basic way of creating an RDD, which is from a list. The input data used for this Hello World kind of application is a small collection of retail banking transactions. To explore the core concepts, only some very elementary data items have been picked up. The transaction records contain account numbers and transaction amounts. In these use cases and all the upcoming use cases in the book, if the term record is used, that will be in the business or use case context. The use cases selected for elucidating the Spark transformations and Spark actions are here. 1. The transaction records are coming as comma-separated values. 2. Filter out only the good transaction records from the list. The account number should start with SB and the transaction amount should be greater than 0. 3. Find all the high-value transaction records with a transaction amount greater than 1,000. 4. Find all the transaction records where the account number is bad. 5. Find all the transaction records where the transaction amount is less than or equal to 0. 6. Find a combined list of all the bad transaction records. 7. Find the total of all the transaction amounts. 8. Find the maximum of all the transaction amounts. 9. Find the minimum of all the transaction amounts. And 10. Find all the good account numbers. The approach that is going to be followed throughout the book for any application that is going to be developed begins with the Spark REPL for the appropriate language. Start the Scala REPL for Spark and make sure that it starts without any errors and the prompt is seen. For this application, we will enable monitoring to learn how to do that and use it along with the development process. Other than explicitly starting the Spark master and the slave separately, Spark comes with a script that will start both of these together using a single script. Then, fire up the Scala REPL with the Spark master URL. At the Scala REPL prompt, try these statements. The output of the statements is given in bold. All the preceding statements fall into one category except the first RDD creation and 2 function value definitions. They are all Spark transformations. Here is the step-by-step detail capturing what has been done so far. The value AC translist is the array containing the comma-separated transaction records. The value AC trans RDD is the RDD created out of the array, where SC is the Spark context or the Spark driver, and the RDD is created in a parallelized way so that the RDD elements can form a distributed dataset. In other words, an instruction is given to the Spark driver to form a parallel collection or RDD from the given collection of values. The value good trans records is the RDD created from AC trans RDD after filtering the condition transaction amount is greater than 0 and the account number starts with SB. The value high value trans records is the RDD created from good trans records after filtering the conditions transaction amount is greater than 1000. The next 2 statements are storing the function definitions in a Scala value for easy reference later. The values bad amount records and bad account records are RDDs created from AC trans RDD to filter the bad records containing the wrong transaction amount and invalid account number, respectively. The value bad trans records contains the union of the elements of both the bad amount records and bad account records RDDs. The Spark Web UI for this application so far will not show anything at this point because only Spark transformations have been executed. The real activity will start only after the first Spark action is executed. The statements are the continuation of the already executed statements. All these statements did one thing, which is execute a Spark action on the RDDs defined earlier. All the evaluations of the RDDs happened only when a Spark action was called on those RDDs. These statements are doing some of the calculations on the RDDs. These numbers calculated the sum, maximum, and minimum of all transaction amounts from the good records. In all the preceding transformations, the transaction records are processed one at a time. From those records, the account number and transaction amount are extracted and processed. It was done like that because the use case requirement was like that. Now, the comma-separated values in each transaction record are split without looking at whether it is an account number or a transaction amount. The resulting RDD will contain a collection with all these mixed up. Out of that, if the elements starting with SB are picked up, that will result in good account numbers. These statements are going to do that. Now at this point, if the Spark Web UI is opened, one difference can be noticed. Since some Spark actions have been done, an application entry will show up. Since the Scala REPL of Spark is still running, it is shown in the list of applications that are still running. Now, we can navigate by clicking on the application ID to see all the metrics related to the running applications, including the DAG visualizations and many more. These statements covered all the use cases discussed, and it's worth going through the Spark transformations covered so far. These are some of the basic but very important transformations that will be used in most of the applications again and again. Filter, FN. Iterates through all the elements of the RDD, applies the function that is passed, and picks up the elements that return true as evaluated by the function on the element. Map, FN. Iterates through all the elements of the RDD, applies the function that is passed, and picks up the output returned by the function. Flatmap, FN. Iterates through all the elements of the RDD, applies the function that is passed, and picks up the output returned by the function. The big difference here as compared to the Spark transformation map FN is that the function acts on a single element and returns a flat collection of elements. For example, it takes one banking transaction record and splits it into multiple fields, resulting in a collection from a single element. Union, other, takes the union of all the elements of this RDD and the other RDD. It's also worth going through the Spark actions covered so far. These are some of the basic ones, but more actions will be covered in due course. Collect collects all the elements in the RDD to an array in the Spark driver. Reduce fn applies the function fn on all the elements of the RDD, and the final result is calculated as defined by the function. It should be a function that takes two parameters and returns one, which is also commutative and associative. For each fn applies the function fn on all the elements of the RDD. This is mainly used for side effects. The Spark transformation map fn applies the function to all the elements of the RDD and returns another RDD. But the for each fn Spark transformation does not return an RDD. For example, for each print in will take each element from the RDD and print it onto the console. Even though it is not used in the use cases covered here, it is worth mentioning. The next step in the Spark learning process is to try the statements in the Python REPL covering the exact same use case. The variable definitions have been maintained as similar as possible in both the languages to have easy assimilation of ideas. There may be minor variations in the way they are used here as compared to the Scala way. Conceptually, it is independent of the language of choice. Start the Python REPL for Spark and make sure that it starts without any errors and the prompt is seen. While playing around with Scala code, the monitoring was already enabled. Now, fire up the Python REPL with the Spark master URL. At the Python REPL prompt, try the following statements. The output of the statements is given in bold. The real power of the uniform programming model of Spark is very clearly visible if both the Scala and Python code sets are compared. The Spark transformations and Spark actions are the same in both the language implementations. The way functions are passed into these are different because of the programming language syntax differences. Before running the Python REPL for Spark, the Scala REPL was closed, and this was done on purpose. Then the Spark Web UI should look something similar to this. Since the Scala REPL was closed, that is getting listed under the completed applications list. Since the Python REPL is still open, that is getting listed under the running applications list. Note the application names of both the Scala REPL and Python REPL of Spark in the Spark Web UI. These are standard names. When custom applications are run from files, there are ways to assign custom names while defining the Spark context object for the applications to facilitate monitoring of the applications and for logging purposes. These details will be covered later in this section. It is a good idea to spend time with the Spark Web UI, getting familiar with all the metrics that are being captured and how the DAG visualization is given in the UI. It will help a lot while debugging complex Spark applications. MapReduce. Since day one, Spark has been placed as the replacement for Hadoop MapReduce programs. In general, data processing jobs are done in MapReduce style if that job can be divided into multiple tasks and they can be executed in parallel, and the final results can be computed after completing the results from all of these distributed pieces. Unlike Hadoop MapReduce, Spark can do this even if the DAG of activities is more than the two stages, such as map and reduce. Spark is designed to do that, and that is one of the biggest value propositions that Spark highlights. This section is going to continue with the same retail banking application and pick up some of the use cases that are ideal candidates for the MapReduce kind of data processing. The use cases selected for elucidating the MapReduce kind of data processing are given here. The retail banking transaction records come with account numbers and the transaction amounts in comma-separated strings. Pair the transactions to have key-value pairs, such as ACC no tran amount. Find an account-level summary of all the transactions to get the account balance. At the Scala repo prompt, try these statements. Here is the step-by-step detail capturing what has been done so far. 1. The value AC translist is the array containing the comma-separated transaction records. 2. The value AC trans RDD is the RDD created out of the array, where SC is the Spark context or the Spark driver, and the RDD is created in a parallelized way so that the RDD elements can form a distributed dataset. 3. Transform the AC trans RDD to AC keyval to have key-value pairs of the form KV, where the account number is chosen as the key. In this set of elements in the RDD, there will be multiple elements with the same key. 4. In the next step, the key-value pairs are grouped by the key and a reduction function has been passed, which will add the transaction amount to form key-value pairs containing one element for a specific key in the RDD and the total of all the amounts for the same key. Then, sort the elements on the key before producing the final result. 5. Collect the elements to an array at the driver level. Assuming that the RDD AC keyval is partitioned into two parts and distributed to a cluster for processing. This table captures the Spark actions that are introduced in this use case. Reduce by key applies the function fn on the RDD of the form kv and is reduced to remove duplicate keys and apply the function passed as the parameter to be acted on the values at the key level. Sort by key sorts the RDD elements if the RDD is of the form kv by its key k. The reduce by key action deserves a special mention. In grouping of the elements by the key is a well-known operation. But, in the next step, for the same key, the function passed to as a parameter takes two parameters and returns one. It is not very intuitive to get this right, and you may be wondering from where the two inputs are coming while iterating through the values of the kv pair for each key. This behavior takes the concept from the Scala collection method reduce left. This indicates the values of the key SB1001 doing the reduce by key operation is an attempt to explain the concept. This is just for the elucidation purposes of this example, and the actual Spark implementation to do the same may be different. The reduce left operation of the Scala collection method is illustrated. That is an attempt to give some insight into from where the two parameters are coming for the reduce left function. As a matter of fact, many of the transformations that are being used on Spark RDD are adapted from Scala collection methods. At the Python repo prompt, try these statements. The reduce by key took an input parameter, which is a function. Similar to this, there's another transformation that does the key-based operation in a slightly different way. It is group by key. This gathers all the values of a given key and forms the list of values from all the individual elements. Joins. In the Relational Database Management Systems, RDBMS world, joining multiple table rows based on a key is a very common practice. When it comes to the NoSQL data stores, joining multiple tables became a real problem because many of the NoSQL data stores don't have support for the table joins. In the NoSQL world, redundancy is allowed. Whether a technology supports table joins or not, business use cases mandate joins of datasets based on keys all the time. Because of this, it is imperative to have the joins done in a batch mode in many of the use cases. Spark provides transformations to join multiple RDDs based on a key. This supports many use cases. These days, there are many NoSQL data stores having connectors to talk to Spark. When working with such data stores, it is very simple to construct RDDs of data from multiple tables, do the join from Spark, and store the results back into the data stores in batch mode or even in near to real-time mode. Spark transformations are available for left outer join and right outer join, as well as full outer join. The use cases selected for elucidating the join of multiple datasets using a key are: the first dataset contains a retail banking master record summary with an account number, first name, and last name. The second dataset contains the retail banking account balance with an account number and balance amount. The key on both of the datasets is the account number. Join the two datasets and create one dataset containing the account number, full name, and balance amount. At the Scala repo prompt, try these statements. All the statements given previously must be familiar by now, except the Spark transformation join. Similar to these transformations, the left outer join, right outer join, and full outer join are also available with the same usage pattern. Join other num tasks. Joins this RDD with the other RDD, and the elements are joined together based on the key. Suppose the original RDD is of the form KV1, and the second RDD is of the form KV2. Then the join operation will produce tuples of the form KV1, V2 with all the pairs of each key. At the Python repo prompt, try these statements. More actions. So far, the focus was mainly on Spark transformations. Spark actions are also important. To get insight into some more important Spark actions, take these use cases, continuing from where it was stopped in the preceding section's use cases. From the list containing account numbers, names, and account balances, get the one that has the highest account balance. From the list containing account numbers, names, and account balances, get the top 3 having the highest account balance. Count the number of balanced transaction records at an account level. Count the total number of balanced transaction records. Print the name and account balance of all the accounts. Calculate the total of the account balance. At the Scala repo prompt, try these statements. This table captures the Spark actions that are introduced in this use case. First, returns the first element in the RDD. Take n returns an array of the first n elements from the RDD. Count by key returns the count of elements by the key. If the RDD contains KV pairs, this will return a dictionary of k num of values. Count returns the number of elements in the RDD. For each fn applies the function fn to each element in the RDD. In this use case, Spark accumulator is being used with for each fn. At the Python repo prompt, try these statements. Awesome! In this video, we successfully learned the basics of programming with Spark. In the next video, we'll learn how to create RDDs from files and understanding the Spark library stack. Welcome to the last video of Section 2, Creating RDDs from Files and Understanding the Spark Library Stack. In the previous video, we've learned about the basics of programming with Spark. In this video, we'll learn how to create the RDDs from files and we'll understand the Spark library stack. So far, the focus of the discussion was on the RDD functionality and programming with RDDs. In all the preceding use cases, the RDD creation was done from the collection objects. But in the real-world use cases, the data will come from files stored in the local file systems and HDFS. Quite often, the data will come from the NoSQL data stores such as Cassandra. It is possible to create RDDs by reading the contents from these data sources. Once RDD is created, then all the operations are uniform, as given in the preceding use cases. The data files coming out of the file systems may be fixed width, comma-separated, or any other format. But the common pattern used for reading such data files is to read the data line by line and split the line to have the necessary separation of data items. In the case of data coming from other sources, the appropriate Spark connector program is to be used, and the appropriate API for reading data is to be used. Many third-party libraries are available to read the contents from various types of text files. For example, the Spark CSV library available from GitHub is a very useful one for creating RDDs from CSV files. This table captures the way text files are read from various sources, such as local file systems, HDFS, and so on. As discussed earlier, the processing of the text file is up to the use case requirements. Local file system creates an RDD by reading the contents of the file named readme.md from the directory from where the Spark shell is invoked. Here, the RDD is of the type RDD string, and the elements will be lines from the file. HDFS creates an RDD by reading the contents of the file specified in the HDFS URL. The most important aspect while reading the files from the local file system is that the file should be available in all the nodes of the Spark worker nodes. Apart from these two file locations given in the preceding table, any supported file system URL may be used. Just like reading the contents from files in various file systems, it's also possible to write the RDD onto files using the Save as Text File path Spark action. Spark comes with a core data processing engine and a stack of libraries working on top of the core engine. It's very important to understand the concept of stacking libraries on top of the core framework. All these libraries that are making use of the services provided by the core framework support the data abstractions offered by the core framework and much more. Before Spark came onto market, there were lots of independent open source products doing what the library stack in discussion here is now doing. The biggest disadvantage with these point products was their interoperability. They don't stack together well. They were implemented in different programming languages. The programming language of choice supported by these products and the lack of uniformity in the APIs exposed by these products were really challenging to get one application done with two or more such products. That is the relevance of the stack libraries that work on top of Spark. They all work together with the same programming model. This helps organizations standardize on the data processing toolset without vendor lock-in. Spark comes with these stack of domain-specific libraries, and this will give a comprehensive picture of the whole ecosystem as seen by a developer. Spark SQL, Spark Streaming, Spark mlib, Spark GraphX. In any organization, structured data is still very widely used. The most ubiquitous data access mechanism with structured data is SQL. Spark SQL provides the capability to write SQL-like queries on top of the structured data abstraction called the DataFrame API. DataFrame and SQL go very well together and support data coming from various sources such as Hive, Avro, Parquet, JSON, and many more. Once the data is loaded into the Spark context, they can be operated as if they were all coming from the same source. In other words, if required, SQL-like queries can be used to join data coming from different sources, such as Hive and JSON. Another big advantage that Spark SQL and the DataFrame API bring onto the developer's table is the ease of use and no need to know functional programming methods, which is a requirement to do programming with RDDs. The data ingestion into the organizational data sinks is increasing every day. At the same time, the velocity at which data is getting ingested is also increasing. Spark Streaming provides the library to process the data that is ingested from various sources at a very high velocity. In the past, data scientists had the challenge of building their own implementations of the machine learning algorithms and utilities in their programming language of choice. Quite often, such programming languages don't interoperate with the data processing toolset of the organization. Spark mlib provides the unification process when it comes with a lot of machine learning algorithms and utilities working on top of the Spark data processing engine. The LOT applications, especially the social media applications, mandated the need to have data processing capabilities where the data fits into a graph-like structure. For example, the connections in LinkedIn, relationship between friends in Facebook, workflow applications, and many such use cases make use of the graph abstraction extensively. Using the graph to do various computations requires very high data processing capabilities and employment of sophisticated algorithms. Spark GraphX library comes with an API for graphs and makes use of Spark's parallel computing paradigm. Awesome! In this video, we successfully learned how to create RDDs from files, and we've also seen about the understanding the Spark library stack. This video concludes the second section of this course. This section discussed the basic programming model of Spark with its primary dataset abstraction RDDs, and processing of the data in RDDs using Spark transformations and Spark actions were covered using Scala and Python APIs. All the important features of the Spark programming model were covered with the help of real-world use cases. This section also discussed the library stack that comes with Spark and what each one is doing. In summary, Spark comes with a very user-friendly programming model and in turn provides a very powerful data processing toolset. The next section we will discuss the Dataset API and the DataFrame API. The Dataset API is going to be the new way of programming with Spark, while the DataFrame API deals with more structured data. Spark SQL is also introduced to manipulate structured data and show how that can be intermixed with any Spark data processing application. Hey! Welcome to this section, Spark SQL. In the previous section, we explored about Spark programming model in depth. In this section, we will cover in detail about the structure of data and Spark SQL. We will also learn about aggregations and multi-data source joins in Spark. We will then have a look at dataset and data catalog. Let us now move on to the first video of this section, Understanding the Structure of Data and the Need of Spark SQL. In this video, we will explore data types in RDBMS and understand Hadoop Distributed File System, HDFS, and also the need of Spark SQL. So, the main reason why most data scientists, data analysts, and business analysts could not make use of RDD-based Spark programming model is because it requires some amount of functional programming. The solution to this problem is Spark SQL. Spark SQL is a library built on top of Spark. It exposes SQL interface and DataFrame API. DataFrame API supports programming languages like Scala, Java, Python, and R. Let's now understand what do we mean by the structure of the data. The data stored in RDBMS has a way of storing data in rows, columns, or records fields. Every field has a data type, and every record is a collection of fields of the same or different data types. In the early days of RDBMS, the data types of the fields were scalar, and in the recent versions it expanded to include collection data types or composite data types as well. So whether the record contains scalar data types or composite data types, the important point to note here is that there is a structure to the underlying data. Many of the data processing paradigms have adopted the concept of mirroring the underlying data structure persisted in the RDBMS or other stores in memory to make the data processing easy. In other words, if the data in an RDBMS table is being processed by a data processing application, if the same table-like data structure is available in memory to the programs, for the end users and programmers, it's easy to model the applications and query the data. For example, suppose there is a set of comma-separated data items with a fixed number of values in each row, having a specific data type for the values coming in the specific position in all the rows. This is a structured data file. It is a data table and is very similar to an RDBMS table. In programming languages such as R, there's a data frame abstraction used to store data tables in memory. The Python data analysis library named Pandas also has a similar data frame concept. Once that data structure is available in memory, the programs can extract the data and slice and dice it as per the need. The same data table concept is extended to Spark, known as DataFrame, built on top of RDD. And there's a very comprehensive API known as DataFrame API in Spark SQL to process the data in the data frame. An SQL-like query language is also developed on top of the DataFrame abstraction, catering to the needs of the end users to query and process the underlying structured data. In summary, DataFrame is a distributed data table organized in rows and columns and having names for each column. The Spark SQL library built on top of Spark is developed based on this research paper, which is titled Spark SQL, Relational Data Processing in Spark. You can spare some time and read it to enhance your knowledge. It talks about 4 goals for Spark SQL, and they are reproduced verbatim as support relational processing both within Spark programs that is on native RDDs and on external data sources using a programmer-friendly API. Next, provide high performance using established DBMS techniques. It also easily supports new data sources, including semi-structured data and external databases amenable to query federation, and enable extension with advanced analytics algorithms such as graph processing and machine learning. DataFrame holds structured data, and it is distributed. It allows selection, filtering, and aggregation of data. Sounds very familiar to RDD, right? So, the key difference between RDD and DataFrame is that DataFrame stores much more information about the structure of the data, such as the data types and names of the columns, than RDD. This allows the data frame to optimize the processing much more effectively than Spark transformations and Spark actions doing processing on RDD. The other most important aspect to mention here is that all the supported programming languages of Spark can be used to develop applications using the DataFrame API of Spark SQL. For all practical purposes, Spark SQL is a distributed SQL engine. If you have worked earlier to Spark 1.3, you must be familiar with Schema RDD, and the concept of DataFrame is exactly built on top of Schema RDD with API-level compatibility. Let's now understand the need of Spark SQL. There is no doubt that SQL is the lingua franca for doing data analysis, and Spark SQL is the answer from the Spark family of toolsets to do data analysis. So what does it provide? It provides the ability to run SQL on top of Spark. Whether the data is coming from CSV, Avro, Parquet, Hive, NoSQL, data stores such as Cassandra, or even RDBMS, Spark SQL can be used to analyze data and mix in with Spark programs. Many of the data sources mentioned here are supported intrinsically by Spark SQL, and many others are supported by external packages. The most important aspect to highlight here is the ability of Spark SQL to deal with data from a very wide variety of data sources. Once it is available as a data frame in Spark, Spark SQL can process data in a completely distributed way, combining the data frames coming from various data sources to process and query as if the entire data set were coming from a single source. In a previous section, the RDD was discussed in detail and introduced as the Spark programming model. So the question here is the DataFrames API and the usage of SQL dialects in Spark SQL replacing RDD-based programming model? Definitely not. The RDD-based programming model is the generic and the basic data processing model in Spark. RDD-based programming requires the use of real programming techniques. The Spark transformations and Spark actions use a lot of functional programming constructs. Even though the amount of code that is required to be written in the RDD-based programming model is less compared to Hadoop MapReduce or any other paradigm, there is still a need to write some amount of functional code. This is a barrier for many data scientists, data analysts, and business analysts, who may perform major exploratory kinds of data analysis or do some prototyping with the data. Spark SQL completely removes those constraints. Simple and easy-to-use domain-specific language that is DSL-based methods to read and write data from data sources, SQL-like language to select, filter, and aggregate, and the capability to read data from a wide variety of data sources make it easy for anybody who knows the data structure to use it. Typically, during the application design phase, business analysts generally do lots of analysis with the application data using SQL, and that is fed to the application requirements and testing artifacts. While designing big data applications, the same thing is needed, and in such situations, apart from business analysts, data scientists will also be there in the team. In a Hadoop-based ecosystem, Hive is used extensively for data analysis with big data. Now, Spark SQL brings that capability to any platform with support for a whole lot of data sources. If there's a standalone Spark installation on commodity hardware, lots of these kinds of activities can be done to analyze the data. A basic Spark installation deployed in standalone mode on commodity hardware is enough to play around with a whole lot of data. The SQL on Hadoop strategy has introduced many applications, such as Hive and Impala to name a few, providing an SQL-like interface to the underlying big data stored in the Hadoop distributed file system, also called HDFS. So where does Spark SQL fit in that space? Spark SQL can process the data from Hive tables faster than Hive using its Hive query language. Another very interesting feature of Spark SQL is that it can read data from different versions of Hive, which is a great feature enabling data source consolidation for data processing. The library that exposes Spark SQL and DataFrame API provides interfaces that can be accessed through JDBC ODBC. This opens up a whole new world of data analysis. For example, a business intelligence or BI tool that connects to data sources using JDBC ODBC can use a whole lot of data sources supported by Spark SQL. Moreover, the BI tools can push down the processor-intensive join aggregation operations to a huge cluster of worker nodes in the Spark infrastructure. Fantastic! In this video, we've explored data types in RDBMS. We also dived into the understanding of Hadoop distributed file system and then went ahead to understand the need of Spark SQL. In the next video, we go through the anatomy of Spark SQL. Hey there! This is the second video of this section, Anatomy of Spark SQL. In the previous video, we learned about the structure of data and understood the need of Spark SQL. In this video, we're going to take a look at the advantages of DataFrame, and also we will learn about query planning and optimizations of Spark SQL. Interaction with Spark SQL library is done mainly through two methods. One is through SQL-like queries, and the other is through DataFrame API. Before getting into the details of how DataFrame-based programs work, it's a good idea to see how the RDD-based programs work. The Spark transformations and Spark actions are converted into Java functions, and they act on top of RDDs, which are nothing but Java objects acting upon data. Since RDD is a pure Java object, there is no way at compile time or at runtime to know about what data is going to process. There is no metadata available to the execution engine beforehand to optimize the Spark transformations or Spark actions. There are no multiple execution paths or query plans available in advance to process that data, and so evaluation of the efficacy of various paths of execution is not available. Here, there is no optimized query plan executed because there is no schema associated with data. In the case of DataFrame, the structure is well known in advance. Because of this, the queries can be optimized and data cache can be built beforehand. The SQL-like queries and DataFrame API calls made against DataFrame are converted to language-neutral expressions. The language-neutral expression corresponding to an SQL query or DataFrame API is called an unresolved logical plan. The unresolved logical plan is converted to a logical plan by doing validations on column names from the metadata of the data frame. The logical plan is further optimized by applying standard rules, such as simplification of expressions, evaluations of expressions, and other optimization rules to form an optimized logical plan. The optimized logical plan is converted to multiple physical plans. The physical plans are created by using Spark-specific operators in a logical plan. The best physical plan is chosen, and the resultant queries are pushed down to RDDs to act on the data. Because the SQL queries and DataFrame API calls are converted to language-neutral query expressions, the performance of these queries is consistent across all the supported languages. That is the same reason why the DataFrame API is supported by all the Spark-supported languages, such as Scala, Java, Python, and R. In the future, there is a good chance that many more languages are going to be supporting DataFrame API and Spark SQL because of this reason. The query planning and optimizations of Spark SQL are worth mentioning here too. Any query operation done on a data frame through SQL queries or through DataFrame API is highly optimized before the corresponding operations are physically applied on the underlying base RDD. There are many processes in between before the real action happening on the RDD. Two types of queries can be called against a data frame. They are SQL queries or DataFrame API calls. They go through a proper analysis to come up with a logical query plan of execution. Then, optimizations are applied on the logical query plans to arrive at an optimized logical query plan. From the final optimized logical query plan, one or more physical query plans are made. For each of the physical query plans, cost models are worked out, and based on the optimal cost, an appropriate physical query plan is selected, and highly optimized code is generated and run against the RDDs. This is the reason behind the consistent performance of queries of any type on DataFrame. This is the same reason why the DataFrame API calls from all these different languages, Scala, Java, Python, and R, give consistent performance. Let's revisit the bigger picture once again, as you see in this figure, to set the context, and also see what is being discussed here before getting into and taking up the use cases. The use cases that are going to be discussed here will demonstrate the ability to mix SQL queries with Spark programs. Multiple data sources will be chosen. Data will be read from those sources using DataFrame, and uniform data access will be demonstrated. The programming languages used to demonstrate are still Scala and Python. The usage of R to manipulate data frames is on the agenda of this video course, and a whole section is dedicated to the same. Wonderful! In this video, we've learned about the structure and internal workings of Spark SQL. In the next video, we'll jump into data frame programming. This is the third video of this section, Data Frame Programming. In the previous video, we learned about the anatomy of Spark SQL. In this video, we'll create the RDD and convert RDD to data frame. We will then calculate the aggregates using mixing of data frame and RDD-like operations, and also calculate the minimum using mixing of data frame and RDD-like operations. So, let us begin and understand the uses we've selected here for elucidating the Spark SQL way of programming with data frame. The transaction records come as comma-separated values. We filter out only the good transaction records from the list. The account number should start with SB, and the transaction amount should be greater than 0. We find all the high-value transaction records with a transaction amount greater than 1,000. Also, find all the transaction records where the account number is bad. Then, find all the transaction records where the transaction amount is less than or equal to 0. Find a combined list of all the bad transaction records and the total of all the transaction amounts. At the end, we find the maximum and minimum of all the transaction amounts along with all the good account numbers. This is exactly the same set of use cases that were used in the previous videos as well, but here the programming model is totally different. Using this set of use cases, two types of programming models are demonstrated here. One is using the SQL queries, and the other is using data frame APIs. At the Scala REPL prompt, we first define a Scala case class is to describe the structure of the transaction record to be fed into the data frame. Next, we write functions to convert the sequence of strings to objects defined by the case classes. Let's now create a list from where the RDD is going to be created. That is where we define an array with the necessary transaction records. Now we create the RDD. Next, we convert RDD to data frame. An RDD is made from the array, split the comma-separated values, mapped it to create objects using the Scala case class that was defined as the first step in the scripts, and the RDD is converted to a data frame. This is one use case of interoperability between RDD and data frame. The next thing we do is register temporary view in the data frame for using it in SQL. Let's print the structure of the data frame. And now show the first few records of the data frame. After this, use SQL to create another data frame containing the good transaction records. Let us now register temporary view in the data frame for using it in SQL and show the first few records of the data frame. Next, use SQL to create another data frame containing the high-value transaction records, and also we print these records. Let's use SQL to create another data frame containing the bad account records and print first few records. We now use SQL to create another data frame containing the bad amount records, and let's see the first few records. Next, do the union of two data frames and create another data frame, and here you can see the first few records of the data frame. Let's calculate the sum and print few records. Next, we calculate the maximum and the minimum amounts and show few records. Let us now use SQL to create another data frame containing the good account numbers, and we also show the first few records of this data frame. Now, we calculate the aggregates using mixing of data frame and RDD-like operations. Now we move on to the Python REPL prompt to perform the same operations. So here too, we create the list from where the RDD is going to be created. Next, we create the data frame for the account transactions. Let's register temporary view in the data frame for using it in SQL. After this, we print the structure of the data frame and show the first few records of this data frame. Now we use SQL to create another data frame containing the good transaction records. After this, we register temporary table in the data frame for using it in SQL, and we show the first few records of this data frame. Let's use SQL to create another data frame containing the high-value transaction records and display the first few records of it. Now, use SQL to create another data frame containing the bad account records and show it. Again, use SQL to create another data frame containing the bad amount records. Let's do the union of two data frames and create another data frame and show this. Next, we calculate the sum, and also calculate the maximum and minimum amounts, and let's see a few records. We again use SQL to create another data frame containing the good account numbers. Then, calculate the sum using mixing of data frame and RDD-like operations. Also, we calculate the maximum using mixing of data frame and RDD-like operations. Similarly, calculate the minimum using mixing of data frame and RDD-like operations. In this Python code, except for a few language-specific constructs, such as importing libraries and the definition of lambda functions, the style of programming is almost the same, most of the time, as the Scala code. This is the advantage of Spark's uniform programming model. As discussed earlier, when business analysts or data analysts provide the SQL for data access, it is very easy to integrate that along with the data processing code in Spark. This uniform programming style of coding is very useful for organizations to use the language of their choice for developing data processing applications in Spark. On DataFrames, if applicable Spark transformations are applied, then a dataset is returned instead of a data frame. The concept of dataset is introduced toward the end of this section. There is a very strong relationship between data frame and dataset, and that is explained in the section covering datasets. While developing applications, caution must be used in this kind of situation. For example, in the coming code snippets, if this transformation is tried in Scala REPL, it will return a dataset. Like the previous code, initially some data frame-specific basic commands are given here. These are used regularly to see the contents and for doing some sanity tests on the data frame and its contents. There are commands that are typically used in the exploratory stage of the data analysis, quite often to get more insight into the structure and contents of the underlying data. Now, at the Scala REPL prompt, we start to write our code. So, first we create the data frame using API for the good transaction records and show the first few records of this data frame. Next, create the data frame using API for the high-value transaction records and display first few records. Now, we create the data frame using API for the bad account records. Let's create the data frame using API for the bad amount records, and we show the first few records of it. After this, we do the union of two data frames and display the first few records of this data frame. Now, let's calculate the aggregates in one shot. And here, we use DataFrame using API for creating the good account numbers. We also show the first few records of this data frame. Next, we persist the data of the data frame into a Parquet file, and then read the data into a data frame from the Parquet file and show it. Let's move on to the Python REPL prompt and try the same operations with Python. Here, we first print the structure of the data frame. Next, we create the data frame using API for the good transaction records and show the first few records of it. Then, we create the data frame using API for the high-value transaction records and display the first few records. Now, let's create the data frame using API for the bad account records and show it. Then, we create the data frame using API for the bad amount records. Now, we do the union of two data frames and create another data frame and show it on the screen. Then, we calculate the sum, and also calculate the maximum and minimum amount. Let's create the data frame using API for the good account numbers, and here we show the first few records from the database. Now we persist the data of the data frame into a Parquet file, and then we read the data into a data frame from the Parquet file. Here, in this Python code, except for a very few variations in the aggregation calculations, the programming constructs are almost similar to its Scala counterpart. The last few statements of the Scala and Python sections are about the persisting of the data frame contents into the media. The writing and reading operations are very much required in any kind of data processing operations, but most of the tools don't have a uniform way of writing and reading. Spark SQL is different. The DataFrame API comes with a rich set of persistence mechanisms. It is very easy to write contents of a data frame into many supported persistence stores. All these writing and reading operations have very simple DSL-style interfaces. These are some of the built-in formats in which data frames can be written to and read from. Apart from these, there are so many other external data sources supported through third-party packages. The write and read of data frame into and from Parquet has been demonstrated in the code we just used. All the preceding inherently supported data stores have very simple DSL-style syntax for persistence and reading back, which makes the programming style uniform once again. The DataFrame API reference is a great source to know about the details of dealing with each of these data stores. The sample code in this video persists data in Parquet and JSON formats. The data store location names chosen are python.trans.parquet and scala.trans.parquet, and so on. This is just to give an indication of which programming language is used and which is the format of the data. This is not a proper convention, but a convenience. When one run of the program is completed, these directories would have been created. Next time the same program is run, it will try to create the same and will result in an error. The workaround is to remove the directories manually before the subsequent runs and proceed. Proper error handling mechanisms and other nuances of fine programming are going to dilute the focus and hence are deliberately left out of this video course. Cool! In this video, we dived into data frame programming. We did first programming with SQL, and then we did programming with DataFrame API. In the next video, we will explore about aggregations and multi-data source joining with Spark SQL. This is the fourth video of this section, Understanding Aggregations and Multi-Data Source Joining with Spark SQL. In the previous video, we looked at data frame programming. In this video, we will understand aggregations and multi-data source joining with Spark SQL. We will first define the case classes for using in conjunction with data frames, and then create the data frame using API for the account summary records. We will also register temporary view in the data frame for using it in SQL. In SQL, aggregation of data is very flexible. The same thing is true in Spark SQL too. Instead of running SQL statements on a single data source located in a single machine, here Spark SQL can do the same on distributed data sources. In the previous video, a MapReduce use case was discussed to do data aggregation, and the same thing is being used here to demonstrate the aggregation capabilities of Spark SQL. In this video, also, the use cases are approached in the SQL query way, as well as in the DataFrame API way. Let's move to the Scala REPL prompt. Here, we first define the case classes for using in conjunction with data frames. Next, we write the functions to convert the sequence of strings to objects defined by the case classes. Let's now create the list from where the RDD is going to be created. Then, we create the data frame. Now, we show the first few records of the data frame. Next, we register temporary view in the data frame for using it in SQL. Let's now use SQL to create another data frame containing the account summary records. Let's see the first few records of the account summary. The next task is to create the data frame using API for the account summary records. So let's do it. And now we show the first few records of this data frame. So in this code, everything is very similar to the previous section's code. The only difference is that here, aggregations are used in the SQL queries, as well as in the DataFrame API. Now, we move to the Python REPL prompt to test the same working with Python. Here, we create the list from where the RDD is going to be created, as we did in the Scala REPL prompt. Next, we create the data frame. Then, register temporary view in the data frame for using it in SQL. Let's now use SQL to create another data frame containing the account summary records, and show the first few records of this data frame. After this, we create the data frame using API for the account summary records. Let's again show the first few records of the data frame. So you can clearly notice that in the DataFrame API for Python, there are some minor syntax differences as compared to its Scala counterpart. In the previous section, the joining of multiple RDDs based on the key has been discussed. In this video, the same use case is implemented using Spark SQL. The use cases selected for elucidating the joining of multiple datasets using a key are given here. The first dataset contains a retail banking master record summary with account number, first name, and last name. The second dataset contains the retail banking account balance with account number and balance amount. The key on both of the datasets is account number. Join the two datasets and create one dataset containing account number, first name, last name, and balance amount. From this report, pick up the top 3 accounts in the terms of the balance amount. In this video, the concept of joining data from multiple data sources is also demonstrated. First, the data frames are created from 2 arrays. They are persisted in Parquet and JSON formats. Then, they are read from the disk to form the data frames, and they are joined together. Now we move on to the Scala REPL prompt, and here we define the case class for using in conjunction with data frames. Let's define one more class. Next, we use the functions to convert the sequence of strings to objects defined by the case classes. Let's now create the list from where the RDD is going to be created. Then we create 2 data frames, so the first one is account master. And now we create the second one that is account balance. Let's persist the data of the data frame into a Parquet file. Then we persist the data of the data frame into a JSON file. Let us now read the data into a data frame from the Parquet file. Next, we register temporary view in the data frame for using it in SQL. Now, read the data into a data frame from the JSON file. Let's register temporary view in the data frame for using it in SQL, and show the first few records of this data frame. Let's use SQL to create another data frame containing the account detail records. Let's have a look at the first few records of the data frame account detail. Now, continue from the same Scala REPL session and create the data frame using API for the account detail records. Here, we print the first few records of the data frame. Next, we use SQL to create another data frame containing the top 3 account detail records. Let's again show the first few records of the data frame. The join type selected here is inner join. Instead of that, any other type of join can be used, either through the SQL query way or through the DataFrame API way. In this particular use case, it can be seen that the DataFrame API is becoming a bit clunky, while the SQL query looks very straightforward. The point here is that depending on the situation, in the application code, the SQL query way and the DataFrame API way can be mixed to produce the desired result. The DataFrame account detail top 3, which we will be using ahead, is an example of that. Now, let's go to the Python REPL prompt and do the same working in Python. So, first create the list from where the RDD is going to be created. After this, we create the DataFrame account master. Next, we persist the data of the data frame into a Parquet file. And now, persist the data of the data frame into a JSON file. Let's read the data into a data frame from the Parquet file. Then, we register temporary table in the data frame for using it in SQL. Also, register temporary table in the data frame for using it in SQL for the Python master JSON file. Next, we register temporary table in the data frame for using it in SQL for balance. Let's show the first few records of the data frame account master. After this, we show the first few records of the data frame account balance. Let's use SQL to create another data frame containing the account detail records. And now we show the first few records of the data frame account details. We now move on to create the data frame using API for the account detail records. Show the first few records of the data frame. We again use SQL to create another data frame containing the top 3 account detail records. Finally, let's show the first few records of the data frame account detail top 3. Here, application of the RDD operations on data frame has been demonstrated. This shows the capability of Spark SQL to interoperate with the RDDs and vice versa. In the same way, SQL queries and the DataFrame API can be mixed in to have flexibility to use the easiest method of computation when solving real-world use cases in the applications. Awesome! In this video, we diced into aggregations and multi-data source joining with Spark SQL. In the next video, we'll explore about introducing datasets. We'll also learn about data catalogs. Hi! Welcome to the last video of this section, Introducing Datasets and Understanding Data Catalogs. In the previous video, we looked at aggregations and multi-data source joining with Spark SQL. In this video, we'll apply filter and create dataset of good and high-value transaction and use Spark SQL to find out invalid transaction records. We'll also get the catalog object from the Spark session object. Dataset is an abstraction that complements the RDD-based Spark programming model. It works pretty much the same way as RDD when it comes to Spark transformations and Spark actions, and at the same time, it is highly optimized like the Spark SQL. Dataset API provides strong compile-time type safety when it comes to writing programs, and because of that, the Dataset API is available only in Scala and Java. Let's move to the Scala repo prompt. Here, we first define the case classes for using in conjunction with DataFrames and dataset. Next, we created the list from where the dataset is going to be created using a case class. Now, let's create the dataset. And then we print the data replated to the dataset. Let's apply filter and create another dataset of good transaction records. Now, we again apply filter and create another dataset, but this time we do it for high-value transaction records. Let's show some data for high-value transactions. Next, we define a function that identifies the bad amounts record. After this, we define the function that identifies bad accounts. Now, we apply filter and create another dataset of bad amount records and display it. Again, we apply filter and create another dataset of bad account records and print some data related to it. Let's do the union of two datasets and create another dataset for bad transaction records and print it. Next, we calculate the sum. Now, calculate the maximum value. After this, we calculate the minimum value. Let's now convert the dataset to data frame and print some dataset on the screen. Next, we use Spark SQL to find out invalid transaction records. Let's show these invalid transactions. It's time to check the interoperability of RDD, DataFrame, and dataset, so we do it right here. Let's create an RDD. Now convert the RDD to DataFrame. And now convert the DataFrame to dataset with this type checking. Let's show some dataset records. It is very clear that the dataset-based programming has good applicability in many of the data processing use cases. At the same time, it has got high interoperability with other data processing abstractions within Spark itself. In this code, the DataFrame was converted to dataset with this type specification. This type of conversion is really required when reading data from external data sources such as JSON, Avro, or Parquet files. That is when strong type checking is needed. Typically, structured data is read into DataFrame, and that can be converted to dataset with strong type safety check like this in one shot. If the Scala code throughout this video are examined when some of the methods are called on a DataFrame, instead of returning a DataFrame object, an object of this type is returned. This is the important relationship between DataFrame and dataset. In other words, DataFrame is a dataset of type org.apache.spark.sql.row. If required, this object of type org.apache.spark.sql.dataset org.apache.spark.sql.row can be explicitly converted to DataFrame using the toDef method. Too many choices confuse everybody. Here in the Spark programming model, the same problem is seen, but it is not as confusing as in many other programming paradigms. Whenever there's a need to process any kind of data with very high flexibility in terms of the data processing requirements and having the lowest API level control such as library development, the RDD-based programming model is ideal. Whenever there is a need to process structured data with flexibility for accessing and processing data with optimized performance across all the supported programming languages, the DataFrame-based Spark SQL programming model is ideal. Whenever there is a need to process unstructured data with optimized performance requirements, as well as compile time, type safety, but not very complex Spark transformations and Spark Actions usage requirements, the dataset-based programming model is ideal. At a data processing application development level, if the programming language of choice permits, it is better to use dataset and DataFrame to have better performance. Let's now move to understand data catalogs. So DataFrames and datasets programming models can deal with structured data. The structured data comes with metadata or the data describing the structure of the data. Spark SQL provides a minimalist API known as Catalog API for data processing applications to query and use the metadata in the applications. The Catalog API exposes a catalog abstraction with many databases in it. For the regular Spark session, it will have only one database, namely default. But if Spark is used with Hive, then the entire Hive metastore will be available through the Catalog API. Let's jump into the usage of Catalog API in Scala and Python. Let's continue from the same Scala repo prompt. So first, we get the catalog object from the Spark session object. Next, get the list of databases. Now, display the details of the databases. After this, we display the details of the tables in the database. Let's display some data. So, this list contains the temporary view that was created in the dataset use case discussed in the previous video. The views created in the applications can be removed from the database using the Catalog API. Let's list the available tables after dropping the temporary view. Let's print some data from it. Similarly, the Catalog API can be used from Python code as well. Since the dataset example was not applicable in Python, the table list will be empty. Let's move on to the Python repo prompt. Here, we get the catalog object from the Spark session object. Next, we get the list of databases and their details. At the end, we display the details of the tables in the database. The Catalog API is very handy when writing data processing applications with the ability to process data dynamically based on the contents in the metastore, especially when using it in conjunction with Hive. For more information, you can visit pandas.pydata.org, or you can even read this documentation at amplab.cs.berkeley.edu. Wonderful! In this section, we learned about structure of data and Spark SQL. We also learned about aggregations and multi-data source joins in Spark. We then explored dataset and data catalog. In the next session, we will be performing Spark programming with R. Hello! In the previous section, we discussed about Spark SQL. Welcome to this section, Spark programming with R. In this section, we will first know the need for Spark R and the basics of R language. We will then explore data frames in R and Spark. We'll also dive into the data frame programming with R, and finally, we'll understand aggregations and multi-data source joins with Spark. Now we move on to the first video of this section, where we will understand the need of Spark R and then learn the basics of R language. In this video, we're going to see why we need of Spark R and what the basics of R language are. We will explore some data types of R and their use in Spark. So, we begin with understanding the need for R. R is used for computing needs by many data scientists. It has inherent support for many statistical functions and many scalar data types. and has composite data structures for vectors, matrices, data frames, and more for statistical computation. R is highly extensible, and for that, external packages can be created. Once an external package is created, it has to be installed and loaded for any program to use it. A collection of such packages under directory forms an R library. In other words, R comes with a set of base packages and additional packages that can be installed on top of it to form the required library for the desired computing needs. In addition to functions, datasets can also be packaged in R packages. Since plain base R installation cannot interact with Spark, we have the Spark R package that exposes all the required objects and functions for R to talk to the Spark ecosystem. Compared to Scala, Java, and Python, the Spark programming in R is different, and the Spark R package mainly exposes R API for DataFrame-based Spark SQL programming. At the moment, R cannot be used to manipulate the RDDs of Spark directly, so for all practical purposes, the R API for Spark has access to only Spark SQL abstractions. The Spark MLlib can also be programmed using R because Spark MLlib uses DataFrames. Do you know how Spark R is going to help the data scientists to do better data processing? The base R installation mandates that all the data to be stored or accessible on the computer where R is installed. The data processing occurs on the single computer on which the R installation is available. Moreover, if the data size is more than the main memory available on the computer, R will not be able to do the required processing. With the Spark R package, there is access to a whole new world of a cluster of nodes for data storage and for doing data processing. With the help of Spark R package, R can be used to access the Spark data frames as well as R data frames. Let us now look into the distinction between the two types of data frames, R data frames and Spark data frames. An R data frame is completely local and a data structure of the R language. A Spark data frame is a parallel collection of structured data managed by the Spark infrastructure. An R data frame can be converted to a Spark data frame, and a Spark data frame can be converted to an R data frame. So, when a Spark data frame is converted to an R data frame, it should fit in the available memory of the computer. This conversion is a great feature, and there's a need to do so. By converting a Spark data frame to an R data frame, a lot of computations, charting, and plotting that is done by other R functions can be done. Whereas by converting an R data frame to a Spark data frame, the data can be distributed and processed in parallel, so multi-batch processing can be completely avoided if Spark with R is used to process the data. Spark with R can be used to process raw data, and finally, the aggregated and summarized data can be used to produce the reports, charts, or plots. Because of the inability to process huge amounts of data, and for doing data analysis with R, many times ETL tools are made to use for doing the pre-processing or transformations on the raw data, and only in the final stage is the data analysis done using R. Because of Spark's ability to process data at scale, Spark with R can replace the entire ETL pipeline and do the desired data analysis with R. Spark with R is a good alternative to packages such as dplyr. The Spark R package is yet another R package, but that is not stopping anybody from using any of the R packages that are already being used. At the same time, it supplements the data processing capability of R Manifold by making use of the huge data processing capabilities of Spark. Let us now move on to the basics of R language. R comes with a few built-in data types to hold numerical values, character values, and Boolean values. There are composite data structures available, namely vectors, lists, matrices, and data frames. A vector consists of ordered collection of values of a given type. A list is an ordered collection of elements that can be of different types. A matrix is a two-dimensional data structure holding numerical values in rows and columns. A data frame is a two-dimensional data structure containing rows and columns where columns can have different data types, but a single column cannot hold different data types. Let's now step ahead to see some code samples of using a variable, a numeric vector, a character vector, a list, a matrix, a data frame, and assigning column names to a data frame. The variable names are given as self-descriptive as possible for the reader to understand without the help of additional explanation. The following code snippet run on a regular R repo gives an idea of the data structures of R. So, we start by creating a variable and assign the value to it as 5. Let's now create some vector to store numeric values, character values, and Boolean values. So, we are now ready to display the list of our data. So let's do it. Then we create two matrices, define its size, and pass values to the rows and columns. Next, we create three vectors for name, age, and the marital status. Let's now create a data frame and pass these vectors which we just created. Superb! So, we are now ready to assign column names to our data frame. Let's go ahead and do it. Here, some of the functions that are commonly used with data frames are demonstrated. All these commands are to be executed on the regular R REPL as a continuation of the session that we just executed. The head command returns the first part of the data frame and return two rows, the first two entries. Whereas the tail command returns the last part of the data frame and return two rows. Let's now extract the number of rows in a data frame. Next, we return the number of columns in a data frame. We now returns the first and the second column of the data frame in both the return value is a data frame. After this, we extract the named columns and the contents of the data frame. Finally, we pull out the slice of the data frame by single row and multiple rows. In this video, we dive into the need of Spark R and we explored how to create different data types in Spark. In the next video, we'll have more fun with data frames in R and Spark. In the previous video, we learned about the need of Spark R and the basics of R language. In this video, we will dive into data frames in R and Spark. Let's now convert an R data frame to a Spark data frame and vice versa. This is going to be a very common operation when programming Spark with R. We will execute the code in the R REPL of Spark. Let us first start with the command faithful, which is a data set and the data frame that comes with base R and. Obviously, it is an R data frame. Next, we convert R data frame to Spark data frame. So for this, we use the Spark faithful command. And let us now display the converted data frame. Let's now try calling a Spark R function, showDF, on an R data frame. As we call this function, it throws an error message as you see on your screen. Next, we convert the Spark data frame to an R data frame, so we use here the R faithful command. Now, there is no complete compatibility and interoperability between an R data frame and a Spark data frame in terms of the supported functions. If you use a lot of charting and plotting, you have to be extra careful while dealing with R data frames in conjunction with Spark data frames. The charting and plotting of R works with only R data frames. If there is a need to produce charts or plots with the data processed by Spark and available in Spark data frame, it has to be converted to an R data frame to proceed with the charting and plotting. Let's now use the faithful dataset again for the elucidation purposes in the R REPL of Spark. After this, we convert the faithful R data frame to Spark data frame. Now, we write the command for Spark data frame, i.e. Spark faithful not producing a histogram. So you see the error generated that X must be numeric. Next comes the R data frame faithful producing a histogram. As you see here, this output demonstrates that the Spark data frame cannot be used to do charting, and R data frame has to be used for the same. The charting and plotting library, when used with Spark data frame, gave an error because of the incompatibility of the data types. An important thing to note here is, the most important aspect to have in mind is that an R data frame is an in-memory resident data structure, while a Spark data frame is a parallel collection of datasets distributed across a cluster of nodes. So all the functions that use R DataFrames need not work with Spark DataFrames and vice versa. Awesome! In this video, we learned about the DataFrames in Spark and R, and also we saw how to convert them. In the next video, we'll step ahead to learn Spark DataFrame programming with R. In the previous video, we learned how to use DataFrames in R and Spark. In this video, we're going to take a look at Spark DataFrame programming with R. We will learn how to write programs with SQL and R DataFrame APIs. Let's move on now to the R REPL prompt. Here we will work with retail banking transaction records, which contains account number, transaction account, and process these with Spark SQL to get the desired results. Let us now change the data directory location to the right location in the system in which this program is being run. For this, we give the data directory command and pass the right path of the directory to it. Next, we read data from a JSON file to create DataFrame. After this, print the structure of the DataFrame. And now show sample records from it. Next, we register temporary view definition in the DataFrame for SQL queries. We then retrieve DataFrame containing good transaction records using SQL. Let's now register temporary table definition in the DataFrame for SQL queries. And then we show sample records from it. Let's extract DataFrame containing high-value transaction records using SQL. And we print sample records from it. Let's now display DataFrame containing bad account records using SQL. And here you can see some sample records from the DataFrame. We now move to DataFrame containing bad amount records using SQL and print the sample records. So here it is. We now create a DataFrame by taking the union of two DataFrames. And after this, we show sample records from the DataFrame. Let's now select DataFrame containing some amount using SQL and display these sample records from the DataFrame. Next, we take maximum amount and print the sample records from the DataFrame. After the maximum amount, we take DataFrame containing minimum amount using SQL. And again, we show sample records from the DataFrame. Finally, we select DataFrame containing good account number. And here are the sample records from the DataFrame. Cool! We are now ready to do programming with our DataFrame API. So what are we waiting for? Let's do it! So to start with, let us read data from a JSON file to create DataFrame and print the sample records from the DataFrame. Next, we take the DataFrame containing good transaction records using API and print sample records from it. After this, we select high-value transaction records using API and show the sample records from the DataFrame. Next, we move on to DataFrame containing bad account records and display the sample records. We then pull DataFrame containing bad account records using API. Let's now create a DataFrame by taking the union of two DataFrames and show its sample records. We now take our hands-on DataFrame containing some amount using API and print sample records from it. After this comes DataFrame containing maximum amount using API, and here are the sample records. Then comes DataFrame containing minimum amount using API, so we retrieve it. Let's now extract DataFrame containing good account number records using API, and let's display sample records here. Finally, let's persist the DataFrame into a Parquet file. The Parquet format data is stored in the current directory, from where the corresponding REPL is invoked. When it is run as a Spark program, the directory again will be the current directory from where the Spark submit is invoked. Here, we read the data from the Parquet file and also show sample records from the DataFrame. Here, the most important aspect to notice is that the filter predicate is to be given exactly like the predicates in the SQL statements. Filters cannot be chained. Wonderful! In this video, we saw how to use SQL programming in Spark. We also performed programming with our DataFrame API. In the next video, we will explore aggregations in Spark R and understand multi-data source joins. Hey! In the previous video, we looked at Spark DataFrame programming with R. In this video, we will step ahead to understand aggregations in Spark R and also explore the multi-data source joins in it. In SQL, aggregation of data is very flexible. The same thing is true in Spark SQL too. Instead of running SQL statements on a single data source located in a single machine here, Spark SQL can do the same on distributed data sources. So, once you are at the R REPL prompt, first we read data from the JSON file to create DataFrame. After this, we register temporary view definition in the DataFrame for SQL queries and show sample records from the DataFrame. Next, we retrieve DataFrame containing account summary records using SQL and print sample records from it. Let's now pull DataFrame containing account summary records using API and also show sample records from the DataFrame. So, in the R DataFrame API, there are some syntax differences as compared to its Scala or Python counterparts, mainly because this is a purely API-based programming model. Now, since we are done with aggregations in Spark R, let us now move on to understand multi-data source joins with Spark. The first dataset contains a retail banking master record summary with the account number, first name, and last name. The second dataset contains the retail banking account balance with account number and balance amount. The key on both of the datasets is the account number. Join the two datasets and create one dataset containing the account number, first name, last name, and balance amount. From this report, pick up the top 3 accounts in terms of the balance amount. The Spark data frames are created from persisted JSON files. Instead of the JSON files, it can be any supported data files. Then, they are read from the disk to form the data frames and they are joined together. Let's now move on to the R REPL prompt. We first read data from JSON file and then show sample records from the data frame. Next, we register temporary view definition in the data frame for SQL queries and print sample records. Let's now register temporary view definition in the data frame for SQL queries. We now step ahead to retrieve data frame containing account detail records using SQL by joining multiple data frame contents and also display sample records from the data frame. Let's persist data in the data frame into Parquet file, and then we read data into a data frame by reading the contents from it and show sample records from the data frame. Now, continuing from the same R REPL session, let's get the same result through the DataFrame API. For this, we change the column names. And now we pull the data frame containing account detail records using API by joining multiple data frame contents and display its sample records. At the end, let's retrieve data frame containing account detail records using SQL by selecting specific fields. And as usual, we show sample records from the data frame. The join type we selected here is inner join. Instead of that, any other type of join can be used either through the SQL query way or through the DataFrame API way. One word of caution before using the join using DataFrame API is that the column names of both the Spark data frames have to be different to avoid ambiguity in the resultant Spark data frame. For more information, you can read the documentation at spark.apache.org. Superb! So we started with the basics of R language, and we learned what the need for Spark R is. We then saw data frames in R and Spark, and we also did data frame programming with R. And finally, we dived into understanding aggregations and explored multi-data source joins in Spark R. In the next section, we will perform Spark data analysis with Python. Hello! In the previous section, we dived into Spark programming with R. In this section, we will explore charting and plotting libraries. We will then see how to set up a dataset. We will also capture the high-level details of the data analysis use cases, and then we will go through various charts and plots. Let's move on to the first video of this section, charting and plotting libraries and setting up a dataset. This video will walk you through the charting and plotting libraries and give a brief description of the application stack. We will also see how to set up a dataset with Spark in conjunction with Python, NumPy, SciPy, and Matplotlib. Python is a programming language heavily used by data analysts and data scientists these days. There are numerous scientific and statistical data processing libraries available, as well as charting and plotting libraries that can be used in Python programs. Python is also widely used as a programming language to develop data processing applications in Spark. This brings in a great flexibility to have a unified data processing and data analysis framework with Spark, Python, and Python libraries, enabling us to do scientific and statistical processing and charting and plotting. This block diagram gives the overall structure of the application stack. Here we will use NumPy and SciPy libraries to do numerical, statistical, and scientific data processing. We will also use the matplotlib to do the charting and plotting that produces 2D images. It is very important to make sure that the NumPy, SciPy, and matplotlib Python libraries are working fine with the Python installation before working with the code in this section. This has to be tested and verified in isolation before using it in Spark applications. There are many public data sets available for the consumption of the general public that can be used for education, research, and development purposes. Here, we will use MovieLens dataset, which allows us to rate and personalize movie recommendations. You can download these datasets from grouplens.org/datasets/MovieLens. In this section, we will use the MovieLens 20M dataset to demonstrate the usage of distributed data processing with Spark in conjunction with Python, NumPy, SciPy, and matplotlib. So we click on the link for download. So the MovieLens 20M dataset has data in multiple files. Let us see those datasets that are going to be used in the data analysis use cases of this video. We have the ML-100K file, which contains the u.user file with the demographic information about the users who have rated movies. The structure of the dataset is given as you see, reproduced as it is from the README file accompanying the dataset with the user ID, age, gender, occupation, and zip code. Next is u.item, containing the information about the movies that are rated by the users. The structure of the dataset is given here, reproduced as it is from the README file accompanying the dataset with a long list beginning with movie ID, movie title, etc. I would like to share a tip before we end this video. So, Spark is used to process the data and prepare the required dataset. Once the required processed data is available in Spark DataFrame, it is collected into the driver program. In other words, the data is transferred from the distributed collection of Spark into a local collection as tuples in the Python program for charting and plotting. For charting and plotting, Python needs the data locally. It cannot use Spark DataFrames directly to do charting and plotting. Cool! In this video, we saw in detail the application stack of Spark and the charting and plotting libraries used. We also learned how to set up a dataset and make it ready for use. In the next video, we will be covering charts, plots, and histograms in depth. In the previous video, we learned how to set up a dataset and saw in detail the charting and plotting libraries. In this video, we're going to take a look at create various charts and plots to visually represent various aspects of the MovieLens 100K and perform data processing, charting, and plotting. A histogram is generally used to show how a given numerical dataset is distributed over consecutive non-overlapping intervals of equal size. The interval or bin size is chosen based on the dataset. The bin or interval represents the ranges of data. In this use case, the dataset consists of the ages of the users. In this case, it does not make sense to have a bin size of 100, as there will only be one bin and the entire dataset will fall into it. The height of the bars representing the bins indicates the frequency of data items in that bin or interval. Let us now use the set of commands to bring up the Python repo of Spark, followed and then perform the data processing, charting, and plotting. We first navigate to the Spark home directory and import all the required libraries initially. Next, we change the appropriate data file location. After this, let's create the data frame of the user dataset, so you need to type all this code with patience. As you see the output, it shows just 20 top rows. We now go on to create the data frame of the user dataset with only one column age. Let's now see the age distribution of the users. Awesome! So here we read the user dataset line by line to form the RDD. From the RDD, a Spark data frame is created. Using Spark SQL, another Spark data frame is created containing only the age column. The summary of that Spark data frame is displayed to show the summary statistics of the contents. The contents are collected into a local Python collection object. Using the collected data, a histogram of the age column is plotted, as you see in this figure. Let us now move on to density plot. So a density plot is very close to a histogram. Whenever there is a finite data sample with a need to estimate the probability density function of a random variable, density plots are used heavily. A histogram doesn't show when data smooths out or when there is continuity in the data points. For that purpose, density plots are used. Since a histogram and density plot are used for similar purposes, but show different behavior for the same data, generally a histogram and density plot are used side by side in many applications. So what are we waiting for? Let's draw a density plot. We first import the Gaussian KDE package and we set the covariance factor and all other parameters. Here, the same Spark data frame that is created containing only the age column is used, and the contents are collected into a local Python collection object. Using the collected data, a density plot of the age column was plotted, as you see in this output, with the line space from 0 to 100 representing the age. If multiple charts or plots are looked at side by side, the matplotlib library provides ways to do that. Let's now obtain a histogram and a box plot side by side. So now we step ahead to create multiple diagrams in one figure. We'll have two plots on one row, where the first one is the histogram of the distribution, while the second one is the box plot containing the summary of the distribution. Wonderful! So here, the same Spark data frame that is created containing only the age column is used, and the contents were collected into a local Python collection object. Using the collected data, a histogram of the age column is plotted along with a box plot containing indicators for the minimum, 25th percentile, median, 75th percentile, and maximum values, as you see on your screen. For more information on NumPy, SciPy, and Matplotlib, you can visit numpy.org, scipy.org, and matplotlib.org. In this video, we've plotted the age distribution using histogram and density plots in Spark by using NumPy, SciPy, and Matplotlib libraries. In the next video, we'll focus on bar charts and pie charts. In the previous video, we looked at histograms and density plots. In this video, we're going to explore more on different types of charts and bars, namely stacked bar chart, donut chart, box plot, and vertical bar chart. Bar charts can be drawn in different ways. The most common one is where the bars are standing vertically on the x-axis. Another variation is where the bars are drawn on the y-axis and have the bars laid out horizontally. It is very common to get confused between a histogram and bar chart. The important difference is that a histogram is used to plot continuous but finite numerical values, but a bar chart is used to represent categorical data. As a continuation of the same Python repo of Spark, let's run the commands here. So, we first select the occupation and the user count from the dataset and display it. So now you can see the top 10 tuples with the occupation and count. Next, we display the top 10 occupation in terms of the number of users having that occupation who have rated movies. So here, a Spark data frame is created containing the top 10 occupations of the users in terms of the number of users who have rated movies. The data is collected into a Python collection object to plot the bar chart. Let us now dive into stacked bar chart. The bar chart that we just drew in this video gives the top 10 user occupations in terms of the number of users, but that does not give details about how that number is made up in terms of the gender of the users. In this kind of situation, it is good to use a stacked bar chart with each bar showing the counts by gender. We go ahead to select the occupation and gender from the dataset and display it. Here, we display top 20 rows from the dataset. Now, we define the X location for the group. Next, we define the width of the bars. Here, a Spark data frame is created containing only the occupation and gender columns. A cross-tab operation is done on that to produce another Spark data frame, which produces columns for occupation, male user count, and female user count. Since there are only 2 gender values in this data, it makes sense to have a stacked bar chart to see the total as well as the proportions of male and female user counts in each occupation category. Spark SQL comes with lots of mathematical and statistical data processing capabilities. The preceding sections use the describe.show method on the Spark data frame objects. In those Spark data frames, the preceding method acted on the available numeric columns. There will be situations where there are multiple numeric columns, and in those situations, the preceding method has the ability to pick and choose the desired columns for getting the summary statistics. Similarly, there are methods to find covariance, correlation, and so on the data from the Spark data frame. Let's now use this method in our code. As you see, we also obtain the covariance and correlation for this summary statistics. Great! Next comes pie chart. If there's a need to visually represent a dataset to explain the whole-part relationship, a pie chart is very commonly used. As a continuation of the same Python repo of Spark, let's run the commands here. Here we create a Spark data frame containing the bottom 10 occupations of the users in terms of the number of users who have rated movies. The data is collected into a Python collection object to plot the pie chart. Pie charts can be drawn in different forms. One such form, the donut chart, is often used these days. Let us now explore the donut chart. We select top 10 zip codes in terms of the number of users living in that zip code who have rated movies. Next, we draw a circle at the center of pi to make it look like a donut. Here, the aspect ratio is to be made equal. This is to make sure that the pie chart is coming perfectly as a circle. Like we did previously, a Spark data frame is created here containing the top 10 zip codes of the users in terms of the number of users who live in that area and who have rated movies. The data was collected into a Python collection object to plot the donut chart. Let us now take our hands on box plot. Frequently, it is a common requirement to compare summary statistics of different datasets in one figure. The box plot is a very common plot used to capture the summary statistics of a dataset in an intuitive way. Let us now plot box plots of the ages by profession. Here, a Spark data frame is created with occupation and age columns for each of 3 occupations: administrator, engineer, and programmer. Box plots are created for each of these datasets on one figure, which contains indicators for the minimum, 25th percentile, median, 75th percentile, and outlier values for each of the datasets to facilitate comparison. The box plot for the programmer occupation shows 2 value points represented by the plus symbol. They are outlier values. Finally, let's take vertical bar chart now. The main dataset we used for listing various charting and plotting use cases was the user data. The dataset that we take up next is the movie dataset. In many datasets to produce various charts and plots, it will be a requirement to make the data suitable for the appropriate figure. Spark is rich with features to do the data processing. The following use case demonstrates the preparation of data by applying some aggregation and using Spark SQL. The desired dataset is prepared for a classic bar chart containing the counts of movies by genre. Now we write the code to display movie types and the counts. With this code, a Spark data frame is created with the movie dataset. The genre of the movie is captured in separate columns. Across the dataset, an aggregation is done using Spark SQL. A new Spark data frame summary is created and the data values are collected into a Python collection object. Since there are too many columns in the dataset, a Python function was used to convert that kind of data structure into a dictionary object containing the column name as the key and the selected single row value is the value of the key. From that dictionary, two datasets are created and a bar chart is drawn. When working with Spark, Python is used to develop data analysis applications, and it is almost certain that there are going to be many charts and plots. Instead of trying out all the code samples given in this video on the Python repo for Spark, it is better to use IPython Notebook as the IDE so that the code and the results can be seen together. In the next video, have a look at scatter plot and line graph. In the previous video, we looked at bar charts and pie chart. In this video, we'll learn in detail about scatter plot and line graph using Spark. We will also see enhanced scatter plot in depth. Scatter plots are very commonly used for plotting values that have two variables, such as a point in Cartesian space having an x value and y value. In this movie dataset, the number of movies released in a given year shows this kind of behavior. In scatter plots, typically, the values represented at the intersection points of x-coordinate and y-coordinate are points. Because of recent technology developments and the availability of sophisticated graphics packages, many use different shapes and colors to represent the points. Simple and elegant shapes that do not clutter the Cartesian space are ideal for non-point representations of the values. As a continuation of the same Python repo of Spark, we run the commands here. In this code, a Spark data frame is used to collect the top 10 years in terms of the number of movies released in that year, and the values are collected into a Python collection object and a scatter plot is drawn. Next, we move on to enhanced scatter plot. It is a very simple and elegant scatter plot, but it does not really convey the comparative behavior of a given plotted value as compared to the other values in the same space. For that, instead of representing the points as fixed radius circles, if the points are drawn as circles with the area proportional to the value, that will give a different perspective. So let's display top 10 years where the most number of movies have been released. Here we have used the same dataset that we did to draw the same scatter plot. Instead of plotting the points with uniform area circles, the points were drawn with proportionate area circles. In all these lines of code, the charts and plots are displayed using the show method. There are methods in matplotlib to save the generated charts and plots to disk, and they can be used for emailing, publishing to dashboards, and more. Now let's dive into line graph. There are similarities between a scatter plot and a line graph. A scatter plot is ideal for representing individual data points, but taking all the points together gives a trend. A line graph also represents individual data points, but the points are connected. This is ideal for seeing the transition form from one point to another point. In one figure, multiple line graphs can be drawn, enabling the comparison of two datasets. The preceding use case used a scatter plot to represent the number of movies released over a few years. Those numbers are just discrete data points plotted on one figure. If the need is to see a trend of how movie releases are changing over the years, a line graph is ideal. Similarly, if there is a need to compare movie releases over the years for two different genres, then one line can be used for each genre, and both can be plotted on a single line graph. Here we created Spark DataFrames to get the datasets for the number of action movies and drama movies released over the period of the last 10 years. The data was collected into Python collection objects and line graphs were drawn in the same figure. Python, in conjunction with the matplotlib library, is very rich in terms of methods to produce publication-quality charts and plots. Spark can be used as the workhorse for processing the data coming from the heterogeneous sources of data, and the results can also be saved to a wide variety of data formats. The data file we used in this section is read from a local file system. Instead of this, it can be read from HDFS or any other Spark-supported data source. When using Spark as the primary framework for data processing, the most important point to keep in mind is that any possible data processing is to be done by Spark, mainly because Spark can do data processing in the best way. Only the processed data is to be returned to the Spark driver program for doing the charting and plotting. Wonderful! In this section, we covered the usage of Spark with Python in conjunction with Python charting and plotting libraries for developing data analysis applications. The next section will walk you through Spark Streaming, which is a library that works on top of Spark and enables the processing of various types of data streams.
Hello, welcome to a new section of our video course, Spark Stream Processing. Our previous section was about Spark data analysis with Python. In this section, we will first have a look at data stream processing and micro-batch data processing. We will then dive into a log event processor. We will also explore a windowed data processing and other options. Finally, we will move on to Kafka stream processing and streaming jobs with Spark. Let's move on to the first video of this section that deals with data stream processing and micro-batch data processing. In this video, we're going to take a look at data stream processing framework and production of discretized stream, or D-streams, which is a data abstraction. We will also learn programming with D-streams. Data processing use cases can be mainly divided into two types. The first type is the use cases, where the data is static and processing is done in its entirety as one unit of work, or by dividing it into smaller batches. While doing the data processing, the underlying dataset does not change, nor do new datasets get added to the processing units. This is batch processing. The second type is the use cases where the data is getting generated like a stream, and the processing is done as and when the data is generated. This is stream processing. In the previous sections of this video course, all the data processing use cases were pertaining to the former type. This section is going to focus on the latter. Let us now start with data stream processing. Data sources generate data like a stream, and many real-world use cases require them to be processed in real time. The meaning of real time can change from use case to use case. The main parameter that defines what is meant by real time for a given use case is how soon the ingested data or the frequent interval in which all the data ingested since the last interval needs to be processed. For example, when a major sports event is happening, the application that consumes the score events and sends them to the subscribed users should be processing the data as fast as it can. The faster it can be sent, the better it is. But what is the definition of fast here? Is it fine to process the score data within, say, an hour of the score event happening? Probably not. Is it fine to process the data within a minute of the score event happening? It is definitely better than processing after an hour. Is it fine to process the data within a second of the score event happening? Probably yes, and much better than the earlier data processing time intervals. In any data stream processing use cases, this time interval is very important. The data processing framework should have the capability to process the data stream in an appropriate time interval of choice to deliver good business value. When processing stream data in regular intervals of choice, the data is collected from the beginning of the time interval to the end of the time interval, grouped in a micro-batch, and data processing is done on that batch of data. Over an extended period of time, the data processing application would have processed many such micro-batches of data.
In this type of processing, the data processing application will have visibility of only the specific microbatch that is getting processed at a given point in time. In other words, the application will not have any visibility or access to the already processed microbatches of data. Now, there is another dimension to this type of processing. Suppose a given use case mandates the need to process the data every minute, but at the same time. While processing the data of a given microbatch, there is a need to peek into the data that was already processed in the last 15 minutes. A fraud detection module of a retail banking transaction processing application is a good example of this particular business requirement. There's no doubt that the retail banking transactions are to be processed within milliseconds of their occurrence. When processing an ATM cash withdrawal transaction, it is a good idea to see whether somebody is trying to continuously withdraw cash and, if found, send the proper alert. For this, when processing a given cash withdrawal transaction, the application checks whether there are any other cash withdrawals from the same ATM using the same card that was used in the last 15 minutes. The business rule is to send an alert when such transactions are more than 2 in the last 15 minutes. In this use case, the fraud detection application should have visibility of all the transactions that happened in a window of 15 minutes. A good stream data processing framework should have the ability to process the data in any given interval of time, as well as the ability to peek into the data ingested within a sliding window of time. The Spark streaming library that is working on top of Spark is one of the best data stream processing frameworks that has both of these capabilities. Look again at the bigger picture of the Spark library stack as given in this figure to set the context and see what is being discussed here before getting into and taking up the use cases. Let us now understand micro-batch processing. So every Spark streaming data processing application will be running continuously till it is terminated. This application will be constantly listening to the data source to receive the incoming stream of data. The Spark streaming data processing application would have a configured batch interval. At the end of every batch interval, it will produce a data abstraction named discretized stream or dstream, which works very similar to Spark's RDD. Just like RDD, a dstream supports an equivalence method for the commonly used Spark transformations and Spark actions. Just like RDD, a dstream is also immutable and distributed. The figure on your screen shows how dstreams are being produced in a Spark streaming data processing application. It depicts the most important elements of a Spark streaming application. For the configured batch interval, the application produces one dstream. Each dstream is a collection of RDDs consisting of the data collected within that batch interval. The number of RDDs within a dstream for a given batch interval will vary. Since Spark streaming applications are continuously running applications collecting data, in this section, rather than running the code in REPL, the complete application is discussed, including the instructions to compile, package, and run. The Spark programming model was discussed in the previous section. Let us jump into programming with dstreams. Programming with dstreams in a Spark streaming data processing application also follows a very similar model, as dstreams consist of one or more RDDs. When methods such as Spark transformations or Spark actions are invoked on a dstream, the equivalent operation is applied to all the RDDs that constitute the dstream. An important point to note here is that not all the Spark transformations and Spark actions that work on RDD are unsupported on dstreams. The other notable change is the differences in capability across programming languages. The Scala and Java APIs for Spark streaming are ahead of the Python API in terms of the number of features supported for Spark streaming data processing application development. This figure depicts how methods applied on a dstream are applied on the underlying RDDs. The Spark streaming programming guide is to be consulted before using any of the methods on dstreams. The Spark streaming programming guide is marked with special callouts containing the text Python API wherever the Python API deviates from its Scala or Java counterparts. Assume that for a given batch interval in a Spark streaming data processing application, a dstream is generated consisting of multiple RDDs. When a filter method is applied on that dstream, here's how it gets translated into the underlying RDDs. This figure shows a filter transformation applied on a dstream with two RDDs, resulting in another D stream containing only one RDD because of the filter condition. Superb! In this video, we've learned the working of data stream processing and micro-batch data processing. In the next video, we will have a look at a log event processor. We now move on to the second video of this section, a log event processor. In the previous video, we looked at data stream processing and micro-batch data processing. In this video, we will first set the netcat server and see how to organize files. We'll also learn to submit the jobs to Spark clusters, monitor and compile the application, and then implement it in Scala and Python. These days, it is very common to have a central repository of application log events in many enterprises. Also, the log events are streamed live to data processing applications in order to monitor the performance of the running applications on a real-time basis so that timely remediation measures can be taken. Such a use case is discussed here to demonstrate the real-time processing of log events using a Spark streaming data processing application. In this use case, the live application log events are written to a TCP socket. The Spark streaming data processing application constantly listens to a given port on a given host to collect the stream of log events. Let us now get ready with the netcat server. The netcat utility that comes with most Unix installations is used here as the data server. To make sure that netcat is installed in the system, type the manual command as we're going to do here, and after coming out of it, run it and make sure that there is no error message. Once the server is up and running, whatever is typed in the standard input of the netcat server console is considered as the application logs events for simplicity and demonstration purposes. Let's run few commands from a terminal prompt to start the netcat data server on localhost port 9999. So, for now, we type man nc command here. Now, open another window and type this command. After this, navigate to your browser and in the URL, give the URL path for this local host. Now, go back to your netcat terminal window. So, once these steps are completed, the netcat server is ready and the Spark streaming data processing application will process all the lines that are typed in the previous console window. Leave this console window alone. All the following shell commands will be run in a different terminal window. Since there's a lack of parity of Spark streaming features between different programming languages, the Scala code is used to explain all the Spark streaming concepts and use cases. After that, the Python code is given, and if there's a lack of support for any of the features being discussed in Python, that is also captured. Let's now look into organizing files. So in this folder tree, the project and target folders are created at runtime. The source code that comes with this book can be copied directly to a convenient folder in the system. Now, let's open a terminal. For compiling and packaging, the Scala build tool, that is SBT, is used. In order to make sure that SBT is working properly, let's run few commands from the Scala folder of the tree which we just saw, in the terminal window. This is to make sure that SBT is working fine and the code is compiling. So we first change the working directory and then navigate to the Scala folder. And now we install SBT and compile it. So this message ensures that SBT is successfully installed. The table here captures the representative sample list of files and the purpose of each of them in the context of the Spark streaming data processing application that is used here. So let's have a look at each of them. The first is readme.txt. It gives the instructions to run the application, one for the Scala application and the other one for the Python application. Next is submitpy.sh. It has bash script to submit the Python job to the Spark cluster, the compile.sh to compile the Scala code, and submit.sh to submit the Scala job to the Spark cluster. After this, we have config.sbt. So we open the config.sbt file, and what you see here are the jar files. Then comes .scala, which is a Spark streaming data processing application code in Scala, and also .py for Spark streaming data processing application code in Python. The last one is the .jar, which is Spark streaming and Kafka integration jar file that needs to be downloaded and placed under the lib folder for the proper functioning of the applications. This is being used in submit.sh as well as in submitpy.sh for submitting the job to the cluster. Now, to properly run the application, some of the configurations depend on the system in which it is being run. They are to be edited in the submit.sh file and the submitpy.sh file. Wherever such edits are required, comments are given with the Phillip tag. The most important of these are the setting of the Spark installation directory and the Spark master configuration, which can differ from system to system. What you see here is the source of submit.sh file. Here, we make an assumption that the Spark home directory and Kafka home directory environment variables are already set in the system that is running the application. We have another file with the name submitpy.sh, which you see here. In this, you need to make the required configuration as per your system. We now step ahead to learn how to monitor the running application. As described in Section 2, Spark Programming Model, Spark installation comes with a powerful Spark Web UI for monitoring the Spark applications that are running. There are additional visualizations available specifically for the Spark streaming jobs that are running. We'll now see how to start the Spark master and workers and enable monitoring. The assumption here is that you've made all the configuration changes suggested in Section 2, Spark Programming Model, to enable Spark application monitoring. If that is not done, the applications can still be run. The only change to be made is to put the cases in the submit.sh file and the submitpy.sh file to make sure that instead of the Spark master URL, something like local4 is used. Now, let's run the commands on the terminal window. Make sure that the Spark Web UI is up and running by visiting the URL http://localhost:/8080/ in your browser. Awesome! So this is how you can monitor the running applications. Now, let's implement the application in Scala. The code which you see here is the Scala code for the log event processing application. Here, there are two Scala objects, Object Streaming Apps and the log settings. One is for setting the proper logging levels to make sure that unwanted messages are not displayed on the console. The Streaming Apps Scala object holds the logic of the stream processing. So, a Spark configuration is created with the application name. A Spark Streaming Context object is created, which is the heart of the stream processing. The second parameter of the streaming context constructor is the batch interval, which is 10 seconds. The line containing ssc.socket text stream creates dstreams at every batch interval, which is 10 seconds here, containing the lines typed in the netcat console. A filter transformation is applied next on the dstream to have only the lines containing the word error. The filter transformation creates new dstreams containing only the filtered lines. The next line prints the dstream contents to the console. In other words, for every batch interval, if there are lines containing the word error that get displayed in the console. At the end of this data processing logic, the given streaming context is started and will run until it is terminated. In this code, there is no loop construct telling the application to repeat till the running application is terminated. This is achieved by the Spark streaming library itself. From the beginning till the termination of the data processing application, all the statements are run once. All the operations on the dstreams are repeated internally for every batch. If the output of the previous application is closely examined, the output from the print-ln statements are only seen once in the console, even though these statements are between the initialization and termination of the streaming context. That is because the magic loop is repeating only for the statements containing original and derived dstreams. Because of the special nature of the looping implemented in Spark streaming applications, it is futile to give print statements and log statements within the streaming logic in the application code, like the one that is given in this code. If that is a must, then these logging statements are to be instrumented within the functions that are passed to dstreams for the transformations and actions. If persistence is required for the processed data, there are many output operations available for D streams just as there are for RDDs. Let's now compile and run the application. So on the terminal window to compile, we run few commands and to run the application. So we first start the netcat server. Now open another terminal and run this command. Again, we open a new terminal and set the path to our working directory. Here, we first compile and then use the submit.sh command. Instead of using ./compile.sh, a simple spt compile command can also be used. Note that as we did previously, the netcat server must be running before these commands are executed. As you can hear, we obtain the message of the start and end of stream processing. Also, every message is print after a time interval of 10 seconds. Now, if no error messages are shown, and the results are showing in line with the previous output, the Spark streaming data processing application has started properly. Let us now jump into handling the output. You should note that the output of the print statements comes before the dstream output print. So far, nothing has been typed in the netcat console, and therefore there is nothing to process. Now, first start the netcat console. Now, open one more terminal and run this command. So when you click Enter, you get the netcat server. Now, we again open a new terminal and start the threads. Then, in a new terminal, we navigate to our working directory, where all other folders are saved. Let's compile the file and submit the files to the streaming apps. Here too, we have got the message for start and end of streaming process, and the time interval here is 10 seconds that was started earlier, and enter these lines of log event messages by giving a gap of few seconds to make sure that the output goes to more than one batch, where the batch size is 10 seconds. Now again, go to the netcat server and type this message. So as you can see that the message is printed here. Let's try the same once more. As you can see, the batch is being processed. So this is how we handle the output. You can observe that once the log event messages are entered into the netcat console window, the results will start showing up in the Spark streaming data processing application, filtering only the log event messages containing the keyword error. Now go to the folder where all the source codes are placed and open the submit.sh file. We mark this line as comment, and here's the local host 7077, which we will be using. Also, save this file and again go to the terminal, and you need to stop this. Again, open a new terminal and move to the working directory and compile the file and then run it. Now we move to the browser and enter the URL localhost ;8080. So when you enter, you can find that the application Streaming Apps is running now. Now click on the Streaming tab to reveal the page containing the streaming statistics. Fantastic! So you can see we have obtained the statistics. Here you can observe that the scheduling delay is 2 milliseconds and processing time is average 394 milliseconds. So if you go on refreshing, it goes on changing. You can check this as many times as you wish. There are a whole lot of application statistics available from these Spark Web UI pages, and exploring them extensively is a good idea to gain a deeper understanding of the behavior of the Spark streaming data processing applications submitted. Care must be taken while enabling the monitoring of streaming applications, as it should not affect the performance of the application itself. Let's implement the application in Python. So we've saved the code for this in streamingapps.py. Now, before you start, make sure you have started the netcat server and the bash terminal. Before running the application, the submitpy.sh file has to be changed to point to the right Spark installation directory and configure the Spark master. If monitoring is enabled, and if the submission is pointing to the right Spark master, the same Spark Web UI will capture the statistics of the Python Spark streaming data processing applications as well. Let's run commands on the terminal window to run the Python application. Once the log event messages are entered into the Netcat console window, these results start showing up in the streaming application, filtering only the log event messages containing the keyword error. Now, go to your browser and enter the same URL which we use for Scala. So now we can see that the Python streaming app is running. Now, go to Streaming. In a similar way, you can find the scheduling delay time and the processing time. When you refresh this, you find a variation in the result. We now close this file and go to the submitpy.sh file. Here we change the local host, save the changes, and again go to the Bash terminal. Now, if you type a message in the Netcat console, the message is printed on the Python console as well. If you look at the outputs from both the Scala and Python programs, you can clearly see whether there are any log event messages containing the word error in a given batch interval. Once the data is processed, the application discards the processed data without returning them for any future use. In other words, the application never retains or remembers any of the log event messages from the previous batch intervals. If there is a need to capture the number of error messages, say in the last 5 minutes or so, then the previous approach will not work. We will see this in the next video. Cool! In this video, we worked to build a log event processor. In the next video, we will see windowed data processing and more processing options. We are now at the third video of this section, windowed data processing and more processing options. In the previous video, we looked at a log event processor. In this video, we'll learn how to count the number of log event messages in Scala and Python as well. We will also look into other processing options. In the Spark streaming data processing application discussed in the previous section, assume that there is a need to count the number of log event messages containing the keyword error in the previous 3 batches. In other words, there should be the ability to count the number of such event messages across a window of 3 batches. At any given point in time, the window should be sliding along with time as and when a new batch of data is available. 3 important terms have been discussed here, and the figure on your screen explains them. They are listed here. The first one is the batch interval. This is the time interval at which a dstream is produced. Next is window length, the duration of the number of batch intervals where there is a need to peek into all the dstreams produced in those batch intervals. And the third one is sliding interval, which is the interval at which the window's operation, such as counting the event messages, is performed. So in this figure, at a given point in time, the dstreams used for the operation to be performed are enclosed in a rectangle. In every batch interval, a new dstream is generated. Here, the window length is 3, and the operation to be performed in a window is counting the number of event messages in that window. The sliding interval is kept the same as the batch interval, so that the counting operation is done as and when a new dstream is generated, so that the count is correct all the time. At time t2, the counting operation is done on the dstreams generated at times t0, t1, and t2. At time t3, the counting operation is done again since the sliding window is kept the same as the batch interval, and this time counting the events is done on the dstreams generated at time t1, t2, and t3. At time t4, the counting operation is done again, counting the events done on the dstreams generated at time t2, t3, and t4. The operations continue in that fashion till the application is terminated. Let us now see how to count the number of log event messages processed in Scala. In the previous video, the processing of the log event messages is shown. In the same application code, after the printing of the log event messages containing the word error, include these lines of code in the Scala application. Here, the first parameter is the window length, and the second one is the sliding window interval. This single magic line will print a count of log event messages processed once the few lines of code are typed in the Netcat console, which we show now. For this, make sure you have started the man NC, the Netcat server, and the local host. Also, open one more terminal and here to your working directory. And now compile the code with the compile.sh command. And then open the Netcat server and type these messages. So, you can see that the same Spark streaming data processing application in Scala with the additional lines of code produces this output. So you can see that the error message is printed here and the count is 1. The warning message has been skipped. Now open a Netcat server and now we copy these messages here. When you give a warning message, it is ignored, and if you go to the Scala prompt, you can find the count as 2. If the output is studied properly, it can be noticed that in the first batch interval, 1 log event message is processed. Obviously, the count displayed is 1 for that batch interval. In the next batch interval, 1 more log event message is processed. The count displayed for that batch interval is 2. In the next batch interval, no log event message is processed. But the count for that window is still 2. For 1 more window, the count is displayed as 2. Then it reduces to 1 and then 0. The most important point to be noted here is that in the application codes for both Scala and Python, immediately after streaming context creation, this line of code needs to be inserted to specify the checkpoint directory. Now, we step ahead to see how to count the number of log event messages processed in Python. In the Python application code, after the printing of the log event messages containing the word error, include these lines of code in the Scala application. The first parameter is the window length, and the second one is the sliding window interval. This single magic line will print a count of log event messages processed once few lines are typed in the Netcat console, which we're going to see right now. Before this, make sure that the Netcat server and the local host is running. Here, we first move to the right working directory. So, at the bash terminal, we first move to the working directory and run the application. And now, at the Netcat console, we type these messages. Now, you can see here, initially there was no count. After that, it changes after a delay of 30 seconds. The output pattern of the Python application is also very similar to the Scala application. As you can see, when it crosses the 30 seconds, the count becomes 0. Now, let us explore more processing options. Apart from the count operation in a window, there are more operations that can be done on dstreams in conjunction with windowing. This table captures the important transformations. All these transformations are acting on the selected window and return a dstream. One of the most important steps of stream processing is the persisting of the stream data into secondary storage. Since the velocity of the data in Spark streaming data processing applications is going to be very high, any kind of persistence mechanism that introduces additional latency into the whole process is not an advisable solution. In batch processing scenarios, it is fine to write to the HDFS and other file system-based storage. But when it comes to the storage of stream output, depending on the use case, an ideal stream data storage mechanism should be chosen. No SQL data stores such as Cassandra support fast writes of temporal data. It is also ideal to read the data that is stored for any further analysis purposes. Spark Streaming Library supports many output methods on dstreams. They include options to save the stream data as text file, object file, Hadoop files, and so on. As well as this, there are many third-party drivers available to save the data into various data stores. Wonderful! In this video, we've learned about windowed data processing, along with other processing options. In the next video, we will step ahead further to see the Kafka stream processing. This is the 4th video of this section, Kafka stream processing. Previously, we saw windowed data processing and more processing options. In this video, we see how to start Zookeeper and Kafka. We will also perform the implementation of Kafka processing in Scala and Python. The log event processor example covered in this section was listening to a TCP socket for the stream of messages to be processed by the Spark streaming data processing application. But in real-world use cases, this is not going to be the case. Message queuing systems with publish-subscribe capability are generally used for processing messages. The traditional message queuing systems fail to perform because of the huge volume of messages to be processed per second for the needs of large-scale data processing applications. Kafka is a publish-subscribe messaging system used by many low-T applications to process a huge number of messages. Here are a few capabilities of Kafka, which made it one of the most widely used messaging systems extremely fast. So, Kafka can process huge amounts of data by handling, reading, and writing in short intervals of time from many application clients. It is highly scalable. Since Kafka is designed to scale up and scale out to form a cluster using commodity hardware, also, it persists a huge number of messages. So, messages reaching Kafka topics are persisted into the secondary storage, while at the same time it is handling huge number of messages flowing through. A detailed treatment of Kafka is outside the scope of this video course. Here we assume that we are familiar with and have working knowledge of Kafka. From a Spark streaming data processing application perspective, it doesn't really make a difference whether it is a TCP socket or Kafka that is being used as a message source. But working on a teaser use case with Kafka as the message producer will give a good appreciation of the toolsets enterprises are using heavily. If you need a guidance on this, you can seek it from this book, that is, Learning Apache Kafka, 2nd edition, by Nishant Garg, which is available at Pact Publishing. Pact Publishing product. Before proceeding further, let us understand some of the important elements of Kafka Producer. It is the real source of the messages, such as weather sensors or mobile phone network. Next is the broker, which is the Kafka cluster, which receives and persists the messages published to its topics by various producers. And the last one is the consumer, the data processing applications subscribe to the Kafka topics that consume the messages published to the topics. The same log event processing application use case discussed in the previous part is used again here to elucidate the usage of Kafka with Spark streaming. Instead of collecting the log event messages from the TCP socket, here the Spark streaming data processing application will act as a consumer of a Kafka topic, and the messages published to the topic will be consumed. The Spark streaming data processing application uses the version 0.8.2.2 of Kafka as the message broker, and the assumption is that you have already installed Kafka, at least in a standalone mode. Let us do some activities to make sure that Kafka is ready to process the messages produced by the producers and that the Spark streaming data processing application can consume those messages. Start the Zookeeper that comes with Kafka installation. Then start the Kafka server. Also, create a topic for the producers to send the messages to. After this, pick up one Kafka producer and start publishing log event messages to the newly created topic. And lastly, use the Spark streaming data processing application to process the log events published to the newly created topic. So, if you have not installed Kafka, for Kafka installation, visit this link and click on the download option and select the appropriate version depending on the Scala version installed on your system. Now, go to your command line terminal and set the environmental variable. We now move on to see how to start Zookeeper and Kafka. Let us have a look at the scripts that we run from separate terminal windows in order to start Zookeeper and the Kafka broker, and to create the required Kafka topics. Make sure that the environment variable Kafka home directory is pointing to the directory where Kafka is installed. Also, it is very important to start Zookeeper Kafka Server, Kafka Producer, and Spark Streaming Log Event Data Processing application in separate terminal windows. So, we first start the Zookeeper. Next, we open another terminal and create a topic. Since I've already created one, it shows the message that SFB already exists. Now, open one more terminal and start a console producer. The Kafka message producer can be any application capable of publishing messages to the Kafka topics. Here, the Kafka-console-producer that comes with Kafka is used as the producer of choice. Once the producer starts running, whatever is typed into its console window will be treated as a message that is published to the chosen Kafka topic. The Kafka topic is given as a command line argument when starting the Kafka-console-producer. The submission of the Spark streaming data processing application that consumes log event messages produced by the Kafka producer is slightly different from the application covered in the preceding section. Here, many Kafka jar files are required for the data processing. Since they are not part of the Spark infrastructure, they have to be submitted to the Spark cluster. So in the working directory under the libs directory, you can find the jar files are required for the successful running of this application. Here are all the Kafka jar files, as you can see. In this list of jar files, the Maven repository coordinate for Spark Streaming Kafka.jar is org.apache.spark Spark Streaming. This particular jar file has to be downloaded and placed in the lib folder of the directory structure given in Figure 4. It is being used in the submit.sh and the submitpy.sh scripts, which submit the application to the Spark cluster. The download URL for this jar file is given in the reference part of this section. In the submit.sh and submitpy.sh files, the last few lines contain a conditional statement looking for the second parameter value of 1 to identify this application and ship the required jar files to the Spark cluster. Instead of shipping these individual jar files separately to the Spark cluster when the job is submitted, an assembly jar can be used by creating it using SBT. Let's now see how to implement the application in Scala. We'll now build a Scala code for the log event processing application that processes the messages produced by the Kafka producer. The use case of this application is the same as the one discussed in the previous part concerning windowing operations. So here's the code we have written. Compared to the Scala code in the previous part, the major difference is in the way the stream is created. Now, make sure all your prerequisites are working. First, set the path to the working directory and then compile the code. Now you can see the time slot. So if you open a broker server and type any message in it, the message will be displayed in the Netcat server. You can notice that it ignores the warning messages, as you can see here. Finally, we implement the application in Python. What you see here is the Python code for the log event processing application that processes the messages produced by the Kafka producer. The use case of this application is also the same as the one discussed in the previous part concerning windowing operations. So this is the file which we have saved as kafkastreamingapps.py. Now, to run this file, we go to a new command line terminal and type these commands to run the Scala application. Now, we open the broker list terminal and type a message here. When both of these programs are running, whatever log event messages are typed into the console window of the Kafka console producer and invoked using the following command and inputs will be processed by the application. The outputs of this program will be very similar to the ones that we obtained before in Scala. Spark provides two approaches to process Kafka streams. The first one is the receiver-based approach that was discussed previously, and the second one is the direct approach. This direct approach to processing Kafka messages is a simplified method in which Spark Streaming is using all the possible capabilities of Kafka, just like any of the Kafka topic consumers, and polls for the messages in the specific topic and the partition by the offset number of the messages. This direct approach to processing Kafka messages is a simplified method in which Spark Streaming is using all the possible capabilities of Kafka, just like any of the Kafka topic consumers, and polls for the messages in the specific topic and the partition by the offset number of the messages. Depending on the batch interval of the Spark Streaming data processing application, it picks up a certain number of offsets from the Kafka cluster, and this range of offsets is processed as a batch. This is highly efficient and ideal for processing messages with a requirement to have exactly once processing. This method also reduces the Spark Streaming library's need to do additional work to implement the exactly once semantics of the message processing and delegates that responsibility to Kafka. The programming constructs of this approach are slightly different in the APIs used for the data processing. Consult the appropriate reference material for the details. This video introduced the concept of a Spark Streaming library and discussed some of the real-world use cases. There's a big difference between Spark data processing applications developed to process static batch data and those developed to process dynamic stream data in a deployment perspective. The availability of data processing applications to process a stream of data must be constant. In other words, such applications should not have components that are single points of failure. The next video is going to discuss this topic. In this video, we have learned about Kafka stream processing and its implementation in both Scala and Python. In the next video, we will explore Spark stream processing jobs in production. Hi, welcome to the last video of this section, Spark streaming jobs in production. In the previous video, we learned how to do Kafka stream processing. In this video, we will first have a look at the components working together in a Spark streaming application infrastructure deployed in a cluster. Then, we will learn to implement fault tolerance in Spark streaming data processing applications. We will also explore structured streaming. When a Spark streaming application is processing the incoming data, it is very important to have uninterrupted data processing capability so that all the data that is getting ingested is processed. In business-critical streaming applications, most of the time, missing even one piece of data can have a huge business impact. To deal with such situations, it is important to avoid single points of failure in the application infrastructure. From a Spark streaming application perspective, it is good to understand how the underlying components in the ecosystem are laid out so that the appropriate measures can be taken to avoid single points of failure. A Spark streaming application deployed in a cluster such as Hadoop Yarn, Mesos, or Spark standalone mode has two main components very similar to any other type of Spark application. One is the Spark driver that contains the application code written by the user, and the other one is the executors that execute the job submitted by the Spark driver. But the executors have an additional component called a receiver that receives the data getting ingested as a stream and saves it as blocks of data in memory. When one receiver is receiving the data and forming the data blocks, they are replicated to another executor for fault tolerance. In other words, in-memory replication of the data blocks is done onto a different executor. At the end of every batch interval, these data blocks are combined to form a D stream and sent out for further processing downstream. This figure depicts the components working together in a Spark streaming application infrastructure deployed in a cluster. Here, there are two executors. The receiver component is deliberately not displayed in the second executor to show that it is not using the receiver, and instead just collects the replicated data blocks from the other executor. But when needed, such as on the failure of the first executor, the receiver in the second executor can start functioning. Let us now see how to implement fault tolerance in Spark streaming data processing applications. Spark streaming data processing application infrastructure has many moving parts. Failures can happen to any one of them, resulting in the interruption of the data processing. Typically, failures can happen to the Spark driver or the executors. This video is not intended to give detailed treatment to running the Spark streaming applications in production with fault tolerance. The intention is to make you appreciate the precautions to be taken when deploying Spark streaming data processing applications in production. When an executor fails, since the replication of data is happening on a regular basis, the task of receiving the data stream will be taken over by the executor on which the data was getting replicated. There is a situation in which when an executor fails, all the data that is unprocessed will be lost. To circumvent this problem, there is a way to persist the data blocks into HDFS or Amazon S3 in the form of write-ahead logs. There is no need to have both the in-memory replication of the data blocks and write-ahead logs together in one infrastructure. Keep only one of them, depending on the need. When the Spark driver fails, the driven program is stopped. All the executors lose connection and they stop functioning. This is the most dangerous situation. To deal with this situation, some configuration and code changes are necessary. The Spark driver has to be configured to have an automatic driver restart, which is supported by the cluster managers. This includes a change in the Spark job submission method to have the cluster mode in whichever may be the cluster manager. When a restart of the driver happens, to start from the place when it crashed, a checkpointing mechanism has to be implemented in the driver program. This has already been done in the code samples that are used. Here are a few lines of code to do this job. So for this, in the Kafka streaming apps.scala file, we will create the streaming context and set the checkpoint directory. In a sample application, it is fine to use a local system directory as the checkpoint directory. But in a production environment, it is better to keep this checkpoint directory as an HDFS location in the case of Hadoop or an S3 location in the case of an Amazon cloud. From an application coding perspective, the way the streaming context is created is slightly different. From an application coding perspective, the way the streaming context is created is slightly different. Instead of creating a new streaming context every time, the factory method getOrCreate of the streaming context is to be used with a function, as you can find in the code segment. If this is done, when the driver is restarted, the factory method will check the checkpoint directory to see whether an earlier streaming context was in use, and if found in the checkpoint data, it is created. Otherwise, a new streaming context is created. Here's the code which gives the definition of a function that can be used with getOrCreate factory method of the streaming context. As mentioned earlier, a detailed treatment of these aspects is beyond the scope of this video course. So, at a data source level, it is a good idea to build parallelism for faster data processing, and depending on the source of data, this can be accomplished in different ways. Kafka inherently supports partition at the topic level, and that kind of scaling out mechanism supports a good amount of parallelism. As a consumer of Kafka topics, the Spark streaming data processing application can have multiple receivers by creating multiple streams, and the data generated by those streams can be combined by the union operation on the Kafka streams. The production deployment of Spark streaming data processing applications is to be done purely based on the type of application that is being used. Some of the guidelines given previously are just introductory and conceptual in nature. There is no silver bullet approach to solving production deployment problems, and they have to evolve along with the application development. Let us now look into structured streaming. In the data streaming use cases that have been covered so far, there are many developer tasks in terms of building of the structured data and implementing fault tolerance for the application. The data that has been dealt with so far in data streaming applications is unstructured data. Just like the batch data processing use cases, even in streaming use cases, if there's the capability to process structured data, that is a great advantage, and lots of pre-processing can be avoided. Data stream processing applications are continuously running applications, and they are bound to develop failures or interruptions. In such situations, it is imperative to build fault tolerance in the data streaming applications. In any data streaming application, the data is getting ingested continuously, and if there's a need to interrogate the data received at any given point in time, the application developers have to persist the data processed into a data store that supports querying. In Spark 2.0, the structured streaming concept is built around these aspects, and the whole idea behind building this brand new feature from the ground up is to relieve application developers of these pain areas. There is a feature with the reference number Spark-8360 being built at the time of creating this video, and its progress can be monitored by visiting the corresponding page. The structured streaming concept can be explained using a real-world use case, such as the banking transaction use case we looked at before. Assume that the comma-separated transaction records containing the account number and transaction amount are coming in a stream. In the structured stream processing method, all these data items get ingested into an unbounded table, or data frame, that supports querying using Spark SQL. In other words, since the data is accumulated in a data frame, whatever data processing is possible using a data frame will be possible with the stream data as well. This reduces the burden on application developers, and they can focus on the business logic of the application rather than the infrastructure-related aspects. For more information on this, you can also visit issues.apache.org/jira/browse/Spark-836. Cool! So this section introduced the basics of the Spark streaming library, and we've developed a simple log event message processing system with two types of data source, one using a TCP data server and the other using Kafka. At the end of this section, we had a brief look at the production deployment of Spark streaming data processing applications and the possible ways of implementing fault tolerance in Spark streaming data processing applications as discussed. The next section will take you through the machine learning library of Spark. Hello! Welcome to a new section of this video course, Spark Machine Learning. In the previous section, we learned about Spark stream processing. In this section, we will learn about using Spark for machine learning and model persistence. We will then have a look at spam filtering and feature algorithms. We will then dive into wine quality prediction and finding cinnamons. Now we move on to the first video of this section that deals with understanding machine learning and need of Spark for it. In this video, we will look into the overview of machine learning and then explore the necessity of Spark for machine learning. We will also learn the terminology and concepts used in Spark machine learning. The process of learning from a dataset and doing predictions based on the learning is known as machine learning. Machine learning originates from the study of artificial intelligence in computer science. In traditional computing, input data is fed to a program to generate output. But in machine learning, input data and output data are fed to a machine learning algorithm to generate a function or program that can be used to predict the output of an input according to the learning done on the input-output dataset fed to the machine learning algorithm. The data available in the wild may be classified into groups. It may form clusters, or it may fit into certain relationships. These are different kinds of machine learning problems. For example, if there is a data bank of pre-owned car sale prices with its associated attributes or features, it is possible to predict the price of a car just by knowing the associated attributes or features. Regression algorithms are used to solve these kinds of problems. If there is a data bank of spam and non-spam emails, then when a new email comes, it is possible to predict whether the new email is spam or non-spam. Classification algorithms are used to solve these kinds of problems. These are just a few machine learning algorithm types, but in general, when using a bank of data, if it is necessary to apply a machine learning algorithm and use that model to make predictions, then the data should be divided into features and outputs. For example, in the case of the car price prediction problem, price is the output, and here are some of the possible features of the data: the car make, car model, year of manufacture, mileage, fuel type, and gearbox type. So whichever machine learning algorithm is being used, there will be a set of features and one or more outputs. Many authors and publications use the term label for output. In other words, features are the input and label is the output. The figure which you see depicts the way a machine learning algorithm works on the underlying data to enable predictions. Data comes in various shapes and forms. Depending on the machine learning algorithm used, the training data has to be pre-processed to have the features and labels in the right format to be fed to the machine learning algorithm. That in turn generates the appropriate hypothesis function, which takes the features as the input and produces the predicted label. Here, the function or program that is generated by the machine learning algorithm is widely known as hypothesis function. In reality, the flow given in this figure is not as simple as it seems. Once the model is trained, a lot of testing has to be done on the model to test predictions with known labels. The chain of train and test processes is an iterative process, and in each iteration, the parameters of the algorithm are tweaked to make the prediction quality better. Once an acceptable test result is produced by the model can be moved to production for doing the live prediction needs. Spark comes with a machine learning library that is rich with capabilities to make practical machine learning a reality. Let's jump right in and understand why we need Spark for machine learning. So, we've already covered various data processing functionalities of Spark in detail. Spark's machine learning library uses many Spark core functionalities, as well as Spark libraries such as Spark SQL. The Spark Machine Learning Library makes machine learning application development easy by combining data processing and machine learning algorithm implementations in a unified framework with the ability to do data processing on a cluster of nodes, combined with ability to read and write data to a variety of data formats. Spark comes with two flavors of the machine learning library. They are spark.mlib and spark.ml. The first one is developed on top of Spark's RDD abstraction, and the second one is developed on top of Spark's DataFrame abstraction. It is recommended to use the spark.ml library for any future machine learning application developments. Let's focus on the spark.ml machine learning library for now. These are the terminology and concepts that are used again and again in this section. The first is estimator, which is an algorithm that works on top of a Spark data frame containing features and labels. It trains on the data provided in the Spark data frame and creates a model. This model is used to do future predictions. Next is transformer, that converts a Spark data frame containing features and transforms it to another Spark data frame containing predictions. The model created by an estimator is a transformer. Then follows parameter, which is to be used by the estimators and transformers. Often, this is specific to the machine learning algorithm. Spark Machine Learning Library comes with a uniform API for specifying the right parameters to the algorithms. And the last one is pipeline. This is a chain of estimators and transformers working together forming a machine learning workflow. All these new terms are slightly difficult to understand in a theoretical perspective, but if an example is given, the concepts will become much clearer. Cool! In this video, we've learned about machine learning and the necessity of Spark for machine learning. In the next video, look into wine prediction and model persistence. We are now at the second video of this section, wine quality prediction and model persistence. In the previous video, we looked at the overview of machine learning and why Spark is better for machine learning. In this video, we will have performed wine quality predictions on the wine quality dataset, and also we'll have a look at model persistence. The University of California Irvine Machine Learning Repository provides a lot of datasets as a service to those who are interested in learning about machine learning. This is available at archive.ics.uci.edu. Also, we use here the wine quality dataset to demonstrate some machine learning applications, which is available at the same website. It contains two datasets with various features of white and red wines from Portugal. For this, you can visit this link and download it from the download link data folder. So, we click on this web link and then download this zip file. So, the wine quality dataset download link lets you download the datasets for red wine and white wine as two separate CSV files. As you can see here, we have one as red.csv and the other one at white.csv. Once these files are downloaded, edit the two datasets to remove the first header line containing the column name and save it. Similarly, let's do it for white.csv file. This is to let the programs parse the numerical data without errors. Detailed error handling and excluding the header record are avoided on purpose to focus on the machine learning functionality. Here, the dataset containing various features of red wine is used in this wine quality prediction use case. So what you see here are the features of the dataset. Based on these features, the quality is determined. Here, quality is the label of this dataset. Using this dataset, a model is going to be trained, and then, using the trained model, testing is done and predictions are made. This is a regression problem. The linear regression algorithm generates a linear hypothesis function. In mathematical terms, a linear function is a polynomial of degree 1 or less. In this machine learning application use case, it deals with modeling the relationship between a dependent variable, that is wine quality, and a set of independent variables which are the features of the wine. Now, at the Scala REPL prompt, let us run some code. So, to start with, we first change this directory to the right location where the wine quality dataset is stored. Next, we define the case class that holds the wine data. Let's now create the RDD by reading the wine data from the disk. The wine data has to be downloaded to the appropriate working directory in the system where we run this, and these lines of code should use this path. After this, we create the data frame containing the training data having two columns. The first one is the actual output or label of the data, and the second one is the vector containing the features. Vector is a data type with zero-based indices and double-typed values. In that, there are two types, namely dense and sparse. A dense vector is backed by a double array representing its entry values. A sparse vector is backed by two parallel arrays, indices, and values. Let's now show the training data. So, we use the show method for it. As you can see, we got the top 20 rows in the output. Next, we create the object of the algorithm, which is the linear regression. Now we use linear regression parameter to make ir.fit method at most 10 iterations. Let's create a trained model by fitting the parameters using the training data. Once the model is prepared, to test the model, prepare the test data containing the labels and feature sectors. So, this is the temporary view which we have created. Now we do the transformation of the test data using the model and predict the output values or labels. This is to compare the predicted value and the actual label value. Let's show the data which we have tested. Next, prepare a dataset without the output or labels to predict the output using the trained model. Also, we show the predicted data. Now, let's do the transformation with the predict dataset and display the predictions and display it. So to continue with the model persistence coming in this video ahead, you should keep this session on. This code does a lot of things. It performs the chain of activities in a pipeline, which are listed on your screen. First, it reads the wind data from the data file to form a training data frame. Secondly, it creates a linear regression object and sets the parameters. Next, it fits the model with the training data, and this completes the estimator pipeline. It also creates a data frame containing test data. Typically, the test data will have both features and labels. This is to make sure that the model is right and used for comparing the predicted label and actual label. Using the model created, it does a transformation with the test data, and from the data frame produced, extracts the features, input labels, and predictions. Note that while doing the transformation using the model, the labels are not required. In other words, the labels will not be used at all. Using the model created, it does a transformation with the prediction data, and from the data frame produced, extracts the features and predictions. Note that while doing the transformation using the model, the labels are not used. In other words, the labels are not used while doing the predictions. This completes a transformer pipeline. The pipelines in this code are single-stage pipelines, and for this reason, there's no need to use the pipeline object. Multiple stage pipelines are going to be discussed in the coming videos. The fitting or testing phases are repeated iteratively in real-world use cases until the model is giving the desired results when doing predictions. The figure which you see elucidates the pipeline concept that is demonstrated through the code. Spark 2.0 comes with the ability to save and load machine learning models across programming languages with ease. In other words, you can create a machine learning model in Scala and load it into Python. This allows us to create a model in one system, save it, copy it, and use it in other systems. Let's continue with the model persistence, keeping this session on. Here, we assume that the model definition model equals ir.fit is still in context. Now, we import some files here. Next, we save the model. Now, we will use the wine.lr model created to get an output in the Python repo. Let's now demonstrate the same use case using Python. So we move at the Python repo prompt, and here we import some files. Next, we change the directory to the right one where the data is stored. So in a similar way, we begin with creating the RDD by reading the wine data from the disk. Vector is a data type with zero-based indices and double-typed values. In that, there are two types, namely dense and sparse. A dense vector is backed by a double array representing its entry values, while a sparse vector is backed by two parallel arrays which are indices and values. Then, we create the data frame containing the training data having two columns. One is the actual output or label of the data, and the vector containing the features. And now we show the training data with the first 20 rows. We then create the object of the algorithm, which is the linear regression with the parameters. We make the linear regression parameter to make ir.fit use at most 10 iterations. Next, we create a trained model by fitting the parameters using the training data. Once the model is prepared, to test the model, prepare the test data containing the labels and feature vectors. Now we create a temporary view and also show the data related to test df. Next, we do the transformation of the test data using the model and predict the output values or tables. This is to compare the predicted value and the actual label value. Let's show the tested data here. Let's prepare a dataset without the output or labels to predict the output using the trained model, and also we display the predicted data. Now we do the transformation with the predict dataset and display the predictions. Let's continue with the model persistence, keeping this session on. So the loaded model can be used for testing or prediction, just like the original model. Let's load the linear regression model saved using the Scala program. So we import these essential files and show the predictions so that we can compare it to the output which we obtained previously. Cool! As mentioned earlier, linear regression is a statistical model and an approach for modeling the relationship between two types of variable. One is an independent variable and the other is a dependent variable. The dependent variable is computed from the independent variables. In many cases, if there's only one independent variable, then the regression will be a simple linear regression. But in reality, in practical real-world use cases, there will be multitude of independent variables, just like in the wine dataset. This falls into the case of multiple linear regressions. This should not be confused with multivariate linear regression. In multivariate regression, multiple and correlated dependent variables are predicted. In the use case that is being discussed here, the prediction is only done for one variable, which is the quality of the wine, and hence it is a multiple linear regression and not a multivariate linear regression problem. Some schools even use multiple linear regression as univariate linear regression. In other words, irrespective of the number of independent variables, if there is only one dependent variable, it is termed as univariate linear regression. Wonderful! In this video, we performed wine quality prediction on the wine quality dataset and also looked into model persistence. In the next video, we'll learn about wine classification. We are now at the third video of this section, wine classification. In the previous video, we looked at wine quality prediction and model persistence. In this video, we're going to model the relationship between a dependent variable and a set of independent variables. We will use logistic regression algorithm to train the model. The dataset containing various features of white wine is used in this wine quality classification use case. These are the features of the dataset which you see here. Based on these features, the quality is determined. If the quality is less than 7, then it is classified as bad, and a value of 0 is assigned to the label. If the quality is 7 or above, then it is classified as good, and a value of 1 is assigned to the label. In other words, the classification value is the label of this dataset. Using this dataset, a model is going to be trained, and then using the trained model, testing is done and predictions are made. This is a classification problem. The logistic regression algorithm is used to train the model. In this machine learning application use case, it deals with modeling the relationship between a dependent variable that is wine quality and a set of independent variables or the features of the wine. Now we move at the Scala REPL prompt. Let's initially import some packages. Next, we change this directory to the right location where the data is stored. Then we define the case class that holds the wine data. Let's create the RDD by reading the wine data from the disk. Now we create the data frame containing the training data having two columns. One is the actual output or label of the data, and the other is the vector containing the features. Also, here we display the training data. After this, we create the object of the algorithm, which is the logistic regression. Here's the logistic regression parameter to make ir.fit use at most 10 iterations and the regularization parameter. When a higher degree polynomial used by the algorithm to fit a set of points in a linear regression model, to prevent overfitting, regularization is used, and this parameter is just for that. Now we create a trained model by fitting the parameters using the training data. Once the model is prepared, to test the model, prepare the test data containing the labels and feature vectors. Also, we show the test data which we have created and we create the temporary view. Let's do the transformation of the test data using the model and predict the output values or labels. This is to compare the predicted value and the actual label value. Let's again show the data which we have tested. Now, we prepare a dataset without the output or labels to predict the output using the trained model. And next, we show the predicted values. Let's again do the transformation with the predict dataset and display the predictions. This code snippet works exactly like a linear regression use case, except for the model used here. The model used here is logistic regression, and its label takes only two values, that is 0 and 1. Creating the model, testing the model, and then the predictions are all similar here. In other words, the pipelines look very similar. Let's demonstrate the same use case using Python, so we move at the Python REPL prompt. Let's import some packages. Next, we change this directory to the right location where the data is stored. Now, we create the RDD by reading the wine data from the disk. Let's create the data frame containing the training data having two columns. One is the actual output or label of the data, and second is the vector containing the features. And now, we show the training data. Let's create the object of the algorithm, which is the logistic regression with the parameters. We use logistic regression parameter to make ir.fit use at most 10 iterations, and the regularization parameter. When a higher degree polynomial used by the algorithm to fit a set of points in a linear regression model to prevent overfitting, regularization is used, and this parameter is just for that. Next, create a trained model by fitting the parameters using the training data. Once the model is prepared, to test the model, prepare the test data containing the labels and feature vectors. Also, we create a temporary view and display it. Now, we do the transformation of the test data using the model and predict the output values or labels. This is to compare the predicted value and the actual label value. Let's prepare a dataset without the labels to predict the output using the trained model. Also, we display the predicted values. And now, we do the transformation with the predict dataset and display the predictions. Logistic regression is very similar to linear regression. The major difference in logistic regression is that its dependent variable is a categorical variable. In other words, the dependent variable takes only a selected set of values. In this use case, the values are 0 or 1. The value 0 means that the wine quality is bad, and the value 1 means that the wine quality is good. To be more precise here, the dependent variable used is binary dependent variable. The use cases covered so far have only a handful of features. But in real-world use cases, the number of features is going to be really huge, especially in machine learning use cases where lots of text processing is done. The next video is going to discuss one such case. In this video, we have performed modeling on the relationship between wine quality and the features of the wine, and used logistic regression algorithm to train the model. In the next video, we will dive into spam filtering. Hey! This is the fourth video of this section, spam filtering. In the previous video, we looked at wine classification. In this video, we're going to first split lines into words, and then we'll transform these words using hashing TF algorithm. Next, we will train a logistic regression model. We will also use the pipeline abstraction and perform the prediction. Spam filtering is a very common use case that is used in many applications. It is ubiquitous in email applications. It is one of the most widely used classification problems. In a typical mail server, a huge number of emails are processed. The spam filtering is done on the emails received before they are delivered to the recipient's mailboxes. For any machine learning algorithm, a model has to be trained before making a prediction. To train the model, training data is required. So, do you know how is training data collected? A trivial way is that the users themselves mark some of the emails received as spam. Use all the emails in the mail server as training data and keep refreshing the model on a regular basis. This includes spam and non-spam emails. When the model has a good sample of both kinds of email, the prediction is going to be good. The spam filtering use case covered in this video is not a full-blown production-ready application, but it gives a good insight into how one can be built. Here, instead of using the entire text of an email, only one line is used for simplicity. If this is to be extended to process real emails, instead of the single strings, read the contents of a full email to one string and proceed as per the logic given in this application. The lines are split into words to have a bag of words, and the words are chosen as features. Since it is easy to process numerical features, these words are transformed to hashed term frequency vectors. In other words, the series of words or terms in the lines are converted to their firm frequencies using a hashing method. So even in small-scale text processing use cases, there will be thousands of features. That is why they need to be hashed for easy comparison. As discussed in previous video, in typical machine learning applications, the input data needs to undergo lots of pre-processing to get it in the right form of features and labels in order to build the model. This typically forms a pipeline of transformations and estimations. In this use case, the incoming lines are split into words, and those words are transformed using hashing TF algorithm. And then, a logistic regression model is trained before doing the prediction. This is done using the pipeline abstraction in the Spark machine learning library. Now, we move at the Scala REPL prompt. So, let's first import some packages. Next, we prepare training documents from a list of messages from emails used to filter them as spam or not spam. If the original message is a spam, then the label is 1, and if the message is genuine, then the label is 0. Let's configure a Spark machine learning pipeline consisting of 3 stages: tokenizer, hashing TF, and LR. Now, logistic regression parameter to make the LR.fit method use at most 10 iterations and the regularization parameter. When a higher degree polynomial used by the algorithm to fit a set of points in a linear regression model to prevent overfitting. Regularization is used, and this parameter is just for that. Next, we fit the pipeline to train the model to study the messages. Let's prepare messages for prediction, which are not categorized and leaving up to the algorithm to predict. And now we show the test data. After this, we make predictions on the new messages and display it. This code does the typical chain of activities: preparing training data, creating the model using the pipeline abstraction, and then predicting using the test data. It doesn't reveal how the features are created and processed. In an application development perspective, Spark Machine Learning Library does the heavy lifting and does everything under the hood using the pipeline abstraction. If the pipeline methodology is not used, then tokenization and then hashing are to be done as separate data frame transformation. Let's have a continuation of these commands to get an insight into how that can be done as simple transformations to see the features using the naked eyes. So first, we select the feature eyes fields from the dataset. So, let's implement the same use case in Python and the Python REPL prompt. First, we import some packages. We prepare training documents from a list of messages from emails used to filter them as spam or not spam. If the original message is a spam, then the label is 1, and if the message is genuine, then the label is 0. And now we show the training data. Let's configure a Spark machine learning pipeline consisting of 3 stages: tokenizer, hashing TF, and LR. Let's see logistic regression parameter to make LR.fit use at most 10 iterations and the regularization parameter. When a higher degree polynomial used by the algorithm to fit a set of points in a linear regression model to prevent overfitting, regularization is used, and this parameter is just for that. Next, we fit the pipeline to train the model to study the messages. After this, we prepare messages for prediction, which are not categorized and leaving up to the algorithm to predict. Let's display the test data. Now we make predictions on the new messages, and also we display the prediction of data. As discussed previously, the transformations abstracted by the pipeline is elucidated ahead using Python explicitly. So, as a continuation of these commands, let's have an insight into how this can be done as simple transformations to see the features using the naked eyes. Now, we create a temporary view and we display the data related to the selected field here. We again create a temporary view and display the selected field. Based on the insight provided in the preceding use case, lots of text processing machine learning applications can be developed by abstracting away lots of transformations using the Spark Machine Learning Library pipelines. Just like the way the machine learning models are persisted to the media, all of the Spark Machine Learning Library pipelines can also be persisted to the media and reloaded by other programs. Wonderful! In this video, we have used logistic regression for spam filtering. In the next video, we'll have a look at feature algorithms and we'll see how to find synonyms. Hi! This is the last video of this section, featuring algorithms and finding synonyms. In the previous video, we looked at spam filtering. In this video, we're going to take a look at In real-world use cases, it is not very easy to get the raw data in the appropriate form of features and labels in order to train the model. Doing lots of pre-processing is very common. Unlike other data processing paradigms, Spark, in conjunction with the Spark Machine Learning Library, provides a comprehensive set of tools and algorithms for this purpose. This pre-processing algorithms can be put into three categories. First is the feature extraction. Next comes feature transformation, and the last one is feature selection. The process of extracting the features from the raw data is feature extraction. The hashing TF that was used in the preceding use case is a good example of an algorithm that converts terms of text data to feature vectors. The process of transforming features into different formats is feature transformation. The process of selecting a subset of features from a superset is feature selection. Covering all these is beyond the scope of this video, but the coming part of this video is going to discuss an estimator, which is an algorithm that is used to extract features, that is used to find synonyms of words in documents. These are not the words' actual synonyms, but the words that are related to a given word in a context. So a synonym is a word or phrase that has exactly the same meaning or very close meaning to another word. In a purely literature perspective, this explanation is correct. But in a much wider perspective, in a given context, some of the words will have a very close relationship, and that is also called synonymous in this context. For example, Roger Federer is synonymous with tennis. Finding this kind of synonym in context is a very common requirement in entity recognition, machine translation, and so on. The word-to-vec algorithm computes a distributed vector representation of words from the words of a given document or collection of words. If this vector space is taken, the words that have similarity or synonymity will be close to each other. The University of California Irvine Machine Learning Repository provides a lot of data sets as a service to those who are interested to learn machine learning, which is available at this website. Here, we use the 20 newsgroups dataset to find synonyms of words in context. It contains a dataset consisting of 20,000 messages taken from 20 newsgroups. So we click on the download link and click on the tar.gz file. This file is to be downloaded and unzipped. The data directory used in the following code snippets should point to the directory where the data is available in unzipped form. If the Spark driver is giving out-of-memory error because of the huge size of the data, remove some of the newsgroup's data that is of not interest and experiment with a subset of the data. Let's move on to the Scala REPL prompt to run the code. Here, we first change this directory to the right location where the data is stored. Then, we read the entire text into a data frame. Only these directories under the data directory has been considered for running this program, which we discussed just now. All other directories have been removed before running this program. There is no harm in returning all the data. The only difference will be in the output. Now we tokenize the sentences to words. Next, we remove the stop words such as a, an, the, I, etc., which doesn't have any specific relevance to the synonyms. After this, we remove the stop words from the text. Let's prepare the estimator. It sets the vector size, and the method setMinCount sets the minimum number of times a token must appear to be included in the word-to-vec model's vocabulary. And now we train the model. Also, we need to find 10 synonyms of a given word, so we do it right here. We also display the synonyms. Let us also find 10 synonyms of a different word and display these synonyms. The code is loaded with a lot of functionality. The dataset is read from the file system into a data frame as one sentence of text from a given file. The tokenization is done to convert the sentences into words using regular expressions and removing the gaps. Then, from those words, the stop words are removed so that we only have relevant words. Finally, using the word-to-vec estimator, a model is trained with the data prepared. From the trained model, synonyms are determined. Let's demonstrate the same use case using Python at the Python REPL prompt. We first import some necessary packages. And then we change this directory to the right location where the data is stored. Let's read the entire text into a data frame. Only those 4 directories which we used in this video previously are considered for running this program, and all other directories are removed before running this program. There is no harm in retaining all the data. The only difference will be in the output. Let's tokenize the sentences to words. Next, we prepare the estimator. It sets the vector size, and the parameter min_count sets the minimum number of times a token must appear to be included in the Word2Vec model's vocabulary. And we train the model. We are now ready to find synonyms of a given word. So let's find 10 synonyms for now, and we also display the output for it. Again, we find 10 synonyms of a different word and display it. Here, the major difference between the Scala implementation and Python implementation is that in the Python implementation, the stop words have not been removed. That is because that functionality is not available in Python API of the Spark machine library. Because of this difference, the list of synonyms generated by Scala program and Python program are different. Awesome! In this section, we've covered some of the very common prediction use cases and classification use cases with Scala and Python implementations using the Spark machine learning library. We started by understanding the need of Spark for machine learning, and then we performed wine quality prediction, wine classification, spam filter. Finally, we also explored about synonym finding machine learning use cases. The next section will walk you through Spark graph processing. Hello! Welcome to a new section of this video course, Spark Graph Processing. In this section, we will go through graphics and their uses, and also the GraphX library. Then, we'll move on to PageRank algorithm and the connected component algorithm. Finally, we will explore about graph frames and graph queries. Let's move on to the first video of this section, Understanding Graphs with Their Usage. In this video, we're going to take a look at different types of graphs and their usage. A graph is a mathematical concept and a data structure in computer science. It has huge applications in many real-world use cases. It is used to model a pairwise relationship between entities. An entity here is known as a vertex, and 2 vertices are connected by an edge. A graph comprises a collection of vertices and the edges connecting them. Conceptually, it is a deceptively simple abstraction, but when it comes to processing a huge number of vertices and edges, it is computationally intensive and consumes a lot of processing time and computing resources. Here is a representation of a graph with 4 vertices and 3 edges. Let us now step ahead to understand graphs and their usage. There are numerous application constructs that can be modeled as graphs. In a social networking application, the relationship between users can be modeled as a graph in which the users form the vertices of the graph and the relationships between users form the edges of the graph. In a multi-stage job scheduling application, the individual tasks form the vertices of the graph, and the sequencing of the tasks forms the edges. In a road traffic modeling system, the towns form the vertices of the graph, and the roads connecting the towns form the edges. The edges of a given graph have a very important property, namely the direction of the connection. In many use cases, the direction of the connection doesn't matter. The case of connectivity between cities by roads is one such example. But if the use case is to produce driving directions within a city, the connectivity between traffic junctions has a direction. Take any 2 traffic junctions, and there will be road connectivity. But it is also possible that it is a one-way road, so it all depends on the direction the traffic is flowing. If the road is open to traffic from traffic junction J1 to J2, but closed from J2 to J1, then the graph of driving directions will have a connectivity from J1 to J2, and not from J2 to J1. In such cases, the edge connecting J1 and J2 has a direction. If the road between J2 and J3 is open in both directions, then the edge connecting J2 and J3 has no direction. A graph in which all the edges have a direction is called a directed graph. When representing a graph pictorially, it is mandatory to give the direction on the edges of the directed graph. If it is not a directed graph, the edge can be represented without any direction at all, or with direction to both sides. This is up to the individual's choice. The figure which you see is not a directed graph, but is represented with directions to both the vertices that the edge is connecting. In this second figure, the relationship between two users in a social networking application use case is represented as a graph. Users form the vertices and the relationships between the users form the edges. User A follows user B. At the same time, user A is the son of user B. In this graph, there are two parallel edges sharing the same source and destination vertices. A graph containing parallel edges is called a multigraph. The graph shown in this figure is also a directed graph. This is a good example of a directed multigraph. In real-world use cases, the vertices and edges of a graph represent real-world entities. These entities have properties. For example, in the social connectivity graph of users from a social networking application, the users form the vertices and users have many properties, such as name, email, phone number, and so on. Similarly, the relationships between the users form the edges of the graph, and the edges connecting user vertices can have properties such as relationship. Any graph processing application library should be flexible enough to attach any kind of property to the vertices and edges of a graph. Cool! In this video, we've explored about graphs and their usage. In the next video, we will dive into the Spark graphics library. Hi! We now move on to the second video of this section, the Spark graphics library. In the previous video, we explored graphs with their usage. In this video, we're going to take a look at GraphX library and learn how to do graph partitioning. Let us now begin to explore the Spark graphics library. So, for graph processing, many libraries are available in the open source world. Giraffe, Pregal, GraphLab, and Spark GraphX are some of them. Spark GraphX is one of the most recent entrants into this space. What is so special about Spark GraphX? Spark GraphX is a graph processing library built on top of the Spark data processing framework. Compared to other graph processing libraries, Spark GraphX has a real advantage. It can make use of all the data processing capabilities of Spark. However, in reality, the performance of graph processing algorithms is not the only aspect that needs consideration. In many applications, the data that needs to be modeled as a graph does not exist in that form naturally. In many use cases, more than the graph processing, lots of processor time and other computer resources are expended to get the data in the right format so that the graph processing algorithms can be applied. This is the sweet spot where the combination of the Spark data processing framework and the Spark graphics library deliver their value. The data processing jobs to make the data ready to be consumed by the Spark graphics can be easily done using the plethora of tools available in the Spark toolkit. In summary, the Spark graphics library, which is part of the Spark family, combines the power of the core data processing capabilities of Spark and a very easy-to-use graph processing library. Revisit the bigger picture once again as given in Figure 3 to set the context and see what is being discussed here before getting into the use cases. Unlike other chapters, in this chapter the code samples will only be done in Scala because the Spark graphics library only has a Scala API available at the moment. Graph Overview. In any real-world use case, it is easy to understand the concept of a graph comprising vertices and edges. But when it comes to the implementation, this is not a data structure that is very well understood by even good designers and programmers. The reason is simple. Unlike other ubiquitous data structures such as list, set, map, queue, and so on, graphs are not commonly used in most applications. Taking this into consideration, the concepts are introduced slowly and steadily, one step at a time, with simple and trivial examples before taking up some real-world use cases. The most important aspect of the Spark graphics library is a data type, graph, which extends the Spark Resilient Distributed Dataset, or RDD, and introduces a new graph abstraction. The graph abstraction in Spark GraphX is a directed multigraph with properties attached to all the vertices and edges. The properties for each of these vertices and edges can be user-defined types that are supported by the Scala type system. These types are parameterized in the graph type. A given graph may be required to have different data types for vertices or edges. This is possible by using a type system related by an inheritance hierarchy. In addition to all these basic ground rules, the library includes a collection of graph builders and algorithms. A vertex in a graph is identified by a unique 64-bit long identifier. org.apache.spark long.graphx.vertexID. Instead of the vertex ID type, a simple Scala type long can also be used. In addition to that, vertices can take any type as a property. An edge in a graph should have a source vertex identifier, a destination vertex identifier, and any type as a property. This figure shows a graph with a vertex property as a string type and an edge property as a string type. In addition to the properties, each vertex has a unique identifier and each edge has a source vertex number and destination vertex number. When processing a graph, there are methods to get the vertices and edges. But these independent objects of a graph in isolation may not be sufficient while doing processing. A vertex has its unique identifier and a property, as stated previously. An edge is uniquely identified by its source and destination vertices. To easily process each edge in graph processing applications, the triplet abstraction of Spark GraphX library provides an easy way to access the properties of the source vertex, destination vertex, and the edge from a single object. Let's create the graph we saw in the previous figure using the Spark GraphX library. After creating the graph, many methods are invoked on the graph that expose various properties of the graph. So we move it to the Scala repo prompt to try some code for it. We begin by importing some essential packages. Let's now create an RDD of users containing tuple values with a mandatory long and another string type as the property of the vertex. Next, we create an RDD of edge type with string type as the property of the edge. Then we create a graph containing the vertex and edge RDDs as created before. Let's now render the number of edges and vertices in the graph. Next, we give the number of edges coming to each of the vertex. Here, the first element in the tuple is the vertex ID, and the second element in the tuple is the number of edges coming to that vertex. Let's give the number of edges going out of each of the vertex, and next we print it. Here, the first element in the tuple is the vertex ID, and the second element in the tuple is the number of edges going out of that vertex. Let's see the total number of edges coming in and going out of each vertex. As we saw previously, the first element in the tuple is the vertex ID, and the second element in the tuple is the total number of edges coming in and going out of that vertex. Let's get the vertices of the graph. Then, we get all the vertices with the vertex number and the property as a tuple. So now we get the edges of the graph. Next, we obtain all the edges properties with source and destination vertex numbers. Lastly, we get the triplets of the graph, and let's see the output for the triplets. You must be familiar with Spark programming using RDDs. This code snippet elucidated the process of constructing the vertices and edges of a graph using RDDs. RDDs can be constructed using data persisted in various data stores. In real-world use cases, most of the time the data will come from external sources, such as non-SQL data stores, and there are ways to construct RDDs using such data. Once the RDDs are constructed, graphs can be constructed using that. Finally, the coming tables show how the vertices and edges are represented. It is important to note that these tables are only for explanation purposes. The real internal representation follows the rules and regulations of RDD representation. If anything is represented as an RDD, it is bound to get partitioned and distributed. But if the partitioning and distribution are done freely, without any control for the graph, then it is going to be suboptimal when it comes to graph processing performance. Because of that, the creators of the Spark GraphX library have thought through this problem well in advance and implemented a graph partitioning strategy in order to have an optimized representation of the graph as RDDs. So, let's have a look at graph partitioning now. It is important to understand a little bit about how the graph RDDs are partitioned and distributed across various partitions. This will be useful for advanced optimizations that determine the partition and distribution of the various RDDs that are the consistent parts of a graph. In general, there are 3 RDDs for a given graph, apart from the vertex RDD and the edge RDD. One more RDD is used internally, and that is the routing RDD. To have optimal performance, all the vertices needed to form a given edge are kept in the same partition where the edge is stored. If a given vertex is participating in multiple edges, and these edges are located in different partitions, then this particular vertex can be stored in multiple partitions. To keep track of the partitions where a given vertex is stored redundantly, a routing RDD is also maintained, containing the vertex details and the partitions in which each vertex is available. In this figure, let's assume that the edges are partitioned into partitions 1 and 2. Also assume that the vertices are partitioned into partitions 1 and 2. In partition 1, all the vertices required for the edges are available locally. But in partition 2, only one vertex for the edge is available locally. So the missing vertex is also stored in partition 2 so that all the required vertices are available locally. To keep track of the replications, the vertex routing RDD maintains the partition numbers where a given vertex is available. If you observe this figure in the vertex routing RDD, callout symbols are used to show the partitions in which these vertices are replicated. In this way, while processing the edges or triplets, all the information related to the constituent vertices is available locally, and performance will be highly optimal. Since the RDDs are immutable, the problems associated with information getting changed are removed, even if they are stored in multiple partitions. Fantastic! In this video, we have dived into the GraphX library and learned how to do graph partitioning. In the next video, we'll be learning about graph processing. We are now at the third video of this section, Graph Processing and Graph Structure Processing. Previously, we looked at the Spark GraphX library. In this video, we're going to first create the graph using the vertices and edges, and then we will create a new graph with the original vertices and the new edges. Finally, we will print this graph. The constituent elements of a graph exposed to the users are the vertex RDD and the edge RDD. Just like any other data structure, a graph also undergoes lots of changes because of the change in the underlying data. To make the required graph operations to support various use cases, there are many algorithms available, using which the data hidden in the graph data structure can be processed to produce the desired business outcomes. Before getting into the algorithms to process a graph, let us understand some of the basics of graph processing using an air travel use case. Assume that a person is trying to find a cheap return air ticket from Manchester to Bangalore. In the travel preferences, this person has mentioned that he or she doesn't care about the number of stops, but the price should be the lowest. Assume that the air ticket reservation system has picked up the same stops for both the onward and the return journey, and produced these routes or journey legs with the cheapest price. This route plan is a perfect example of a graph. If the onward journey is considered as one graph and the return journey is considered as another graph, the return journey graph can be produced by reversing the onward journey graph. So let's move to the Scala REPL prompt. Here, we first import these essential packages. Next, we create the vertices with the stops. Then, we create the edges with travel legs. Now, let's create the onward journey graph. We also print the onward journey triplet. Let's now reverse the onward journey. So, the source and destination of the onward journey legs are reversed in the return journey legs. When a graph is reversed, only the source and destination vertices of the edges are reversed, and the identity of the vertices remains the same. In other words, the vertex identifiers of each of the vertices remain the same. While processing a graph, it is important to know the names of the triplet attributes. They are useful for writing programs and processing the graph. As a continuation of the same Scala REPL session, let's try a few commands. Here's a table that gives the list of attributes of a triplet that can be used to process a graph and extract the required data from the graph. So the previous code and this table may be cross-verified to fully understand that in a graph, vertices are RDDs and edges are RDDs, and just by virtue of that, transformations are possible. Now, let's demonstrate graph transformations. For this, we use the same use case with a slight twist. Assume that a travel agent is getting special discount prices from the airline companies for selected routes. The travel agent decides to keep the discount and offer the market price to his or her customers, and for this purpose, he or she adds 10% to the price given by the airline company. This travel agent has noticed that the airport names are being displayed inconsistently and wanted to make sure that there is consistent representation when displayed throughout the website and decides to change all the stop names to uppercase. Let us continue with the same Scala REPL session and create the vertices. Next, we create the edges. We again create the graph using the vertices and edges. We also convert the stop names to uppercase. Let's get the edges from the selected journey and add 10% price to the original price. Now, we create a new graph with the original vertices and the new edges. After this, we print the contents of the original graph. Let's print the contents of the transformed graph. In essence, these transformations are truly RDD transformations. If there is a conceptual understanding of how these different RDDs are cobbled together to form a graph, any programmer with RDD programming proficiency will be able to do graph processing very well. This is another testament to the power of the unified programming model of Spark. This use case did the map transformation on vertex and edge RDDs. Similarly, filter transformations are another useful type that is commonly used. Apart from these, all the transformations and actions can be used to process the vertex and edge RDDs. Now, we jump into graph structure processing. Previously, we did one type of graph processing by individually processing the required vertices or edges. One disadvantage of this approach is that the processing is going through 3 different stages. First, extract vertices or edges from the graph. Next, process the vertices or edges. And then recreate a new graph with the processed vertices and edges. This is tedious and prone to user programming errors. To circumvent this problem, there are some structural operators available in the Spark GraphX library that lets users process the graph as an individual unit that produces a new graph. One important structural operation has already been discussed in the previous video, which is the reversal of a graph producing a new graph with all the directions of the edges reversed. Another frequently used structural operation is the extraction of a subgraph from a given graph. The resultant subgraph can be the entire parent graph itself or a subset of the parent graph, depending on the operation that is done on the parent graph. When creating a graph from data from external sources, there's a possibility that the edges may have invalid vertices. This is very much a possibility if the vertices and the edges are created from the data coming from 2 different sources or different applications. With these vertices and edges, if a graph is created, some of the edges will have invalid vertices and processing will result in unexpected outcomes. Let's have a look at a use case where some of the edges containing invalid vertices and pruning are done to get rid of that using a structural operator. For this, we navigate to the Scala REPL prompt. So here we first import some libraries. Next, we create an RDD of users containing tuple values with a mandatory long and another string type as the property of the vertex. Next, we create an RDD of edge type with string type as the property of the edge. Let us now create a vertex property object to fill in a void if an invalid vertex ID is given in the edge. Also, we create a graph containing the vertex and edge RDDs as created before. Now, list the graph triplets and find some of the invalid vertex IDs given, and for them, the missing vertex property is assigned with the value missing. Since the edges with the invalid vertices are invalid too, filter out those vertices and create a valid graph. The vertex predicate here could be any valid filter condition of a vertex. Similar to vertex predicate, if the filtering is to be done on the edges instead of the vpred, use epred as the edge predicate. In huge graphs, at times depending on the use case, there can be a whole lot of parallel edges. In some use cases, it is possible to combine the data of the parallel edges and maintain only one edge instead of maintaining lots of parallel edges. In the preceding use case, the final graph without any invalid edges, there are parallel edges, one with the property follows and the other with sun, which have the same source and destination vertices. It is fine to combine these parallel edges into one single edge with the property concatenated from the parallel edges, which will reduce the number of edges without losing information. This is accomplished by the group edges structural operation of the graph. Now we continue at the same Scala REPL session and import the partition strategy classes. Next, we partition the user graph. This is required to group the edges. After this, we generate the graph without parallel edges and combine the properties of duplicate edges. Let's print the details. This structural change in the graph reduced the number of edges by grouping the edges. When the edge property is numerical, and if it makes sense to consolidate by aggregating them, then also reduce the number of edges by removing the parallel edges, which can reduce the graph processing time considerably. One important point for you to note in this code is that the graph has been partitioned before the group by operation on the edges. By default, the edges and the constituent vertices of a given graph need not be co-located in the same partition. For the group by operation to work, all the parallel edges have to be located on the same partition. The canonical random vertex cut partition strategy makes sure that co-location happens for all the edges between two vertices irrespective of direction. There are some more structural operators available in the Spark graphics library, and a consultation of the Spark documentation will give a good insight into them. They can be used depending on the use case. Superb! In this video, we saw how to do graph processing and graph structure processing. In the next video, we will perform tennis tournament analysis. Hey, let's move to the fourth video of this section, tennis tournament analysis. In the previous video, we learned how to perform graph processing and also graph structure processing. In this video, we're going to model tennis tournament results using a graph. We find different players and groups based on their performance, that is, winners and losers. Since the basic graph processing fundamentals are in place, now it is time to take up a real-world use case that uses graphs. Here, a tennis tournament's results are modeled using a graph. The Barclays ATP World Tour 2015 singles competition results are modeled using a graph. The vertices contain the player details and the edges contain the individual matches played. The edges are formed in such a way that the source vertex is the player who won the match and the destination vertex is the player who lost the match. The edge property contains the type of the match, the points the winner got in the match, and the head-to-head count of the players in the match. The point system used here is fictitious and is nothing but a weight earned by the winner in that particular match. The initial group matches carried the least weight, the semifinal matches carried more weight, and the final match carried the most weight. If you're not familiar with the game of tennis, you don't need to worry because the rules of the games are not discussed here and are not required to understand this use case. For all practical purposes, it is to be taken only as a game played between two people, where one wins and the other loses. Let's move on to the Scala repo prompt, and here we first import few essential packages. Next, we define a property class that is going to hold all the properties of the vertex, which is nothing but player information. After this, we create the player vertices. Now, let's define a property class that is going to hold all the properties of the edge, which is nothing but match information. And now, we create the match edges. Next, we create a graph with the vertices and edges. The graph containing the tennis tournament has been created, and from now on, all that is going to be done is the processing of this base graph and extracting information from it to fulfill the requirements of the use cases. Let's print the match details. Next, we print matches with player names and the match type and the result. It is worth noticing here that the usage of triplets in graphs comes in handy for extracting all the required data elements of a given tennis match, including who was playing, who won, and the match type from a single object. The following implementations of analysis use cases involve filtering the tennis match records of the tournament. Here, only simple filtering logic is used, but in real-world use cases, any complex logic can be implemented in functions that can be passed as arguments to the filter transformations. Now, we step ahead to Group 1 winners with their group total points. Then, we find the group total of the players. Now, let's group 2 winners with their group total points. These implementations of analysis use cases involve grouping by key and doing summary calculations. It is not limited to just finding the sum of the tennis match record points, as we in the coming use case implementations. Rather, user-defined functions can be used to do the calculations as well. Now, we find the group total of the players. Next is the semifinal winners with their group total points. We now find the group total of the players. Let's see the final winner with the group total points. Now we'll see the tournament total point standing. We then find the winner of the tournament by finding the top scorer of the tournament. Next, we find out how many head-to-head matches held for a given set of players in the descending order of head-to-head count. Let's step ahead to find unique records from the query by implementing the analysis use cases with the Spark distinct transformation. So, we get the list of players who have won at least one match. Next, we list players who have lost at least one match. After we print the list of players who have won at least one match and lost at least one match. Now, we print the list of players who have no wins at all. Finally, we display the list of players who have no loss at all. So you can see that the value 1 and no losses returned an empty set, which means that there is no single player in this tournament who have only wins. In this use case, not much effort has been made to make the results pretty, because they are reduced to simple RDD-based structures that can be manipulated, however, required using the RDD programming techniques that were already covered in the initial sections of this video course. The highly succinct and uniform programming model of Spark, in conjunction with the Spark GraphX library, helps developers build real-world use cases with very few lines of code. This also demonstrates that once the right graph structure is built with the relevant data with the supported graph operations, lots of truth that is hidden in the underlying data can be brought to light. Awesome! In this video, we have modeled tennis tournament results using a graph. In the next video, we will learn to apply the PageRank algorithm. Welcome to the 5th video of this section, Applying the PageRank algorithm. Previously, we learned how to perform tennis tournament analysis. In this video, we will first define property classes to hold all the properties of the edges and vertices, and then create a graph with the vertices and edges. And finally, we will run the PageRank algorithm to calculate the rank of each vertex. A research paper titled The Anatomy of a Large-Scale Hypertextual Web Search Engine by Sergey Brin and Lawrence Page revolutionized web searching, and Google based its search engine on this concept of PageRank and came to dominate other web search engines. When searching the web using Google, pages that are ranked highly by its algorithm are displayed. In the context of graphs, instead of web pages, if vertices are ranked based on the same algorithm, lots of new inferences can be made. From the outside, it may sound like this PageRank algorithm is useful only for web searches, but it has immense potential to be applied to many other areas. In graph parlance, if there's an edge, E, connecting two vertices from V1 to V2, according to the PageRank algorithm, V2 is more important than V1. In a huge graph of vertices and edges, it is possible to calculate the PageRank of each and every vertex. The PageRank algorithm can be applied very well to the tennis tournament analysis use case covered in the preceding section. In the graph representation that is adopted here, each match is represented as an edge. The source vertex has the winner's details and the destination vertex has the loser's details. In the game of tennis, if this can be termed as some fictitious importance ranking, then in a given match the winner has higher importance ranking than the loser. If the graph in the previous use case is taken to demonstrate the PageRank algorithm, then that graph has to be reversed so that the winner of each match becomes the destination vertex of each and every edge. So, let's go to the Scala repo prompt and do it. Here, we first import some necessary files. Next, we define a property class that is going to hold all the properties of the vertex, which is nothing but player information. Then, we create the player vertices. Now, let's define a property class that is going to hold all the properties of the edge, which is nothing but match information. After this, we create the match edges. And now, create a graph with the vertices and edges. We then reverse this graph to have the winning player coming in the destination vertex. Now, run the PageRank algorithm to calculate the rank of each vertex. Finally, we extract the vertices sorted by the rank. And now we print the ranked players. If you scrutinize this code carefully, you can see that the highest ranked players have won the highest number of matches. To learn about the tennis tournament analysis, you can visit this wiki page and read here. Wonderful! In this video, we have applied the PageRank algorithm to the tennis tournament results. In the next video, we will learn about connected component algorithm. This is the sixth video of this section, Connected Component Algorithm. In the previous video, we looked at applying the PageRank algorithm. In this video, we will create the RDD with users as the vertices and edges connecting the users. We will then create a graph and find the connected components of the graph. Finally, we will extract the user names with their CC component ID. In a graph, finding a subgraph consisting of connected vertices is a very common requirement with tremendous applications. In any graph, two vertices are that connected to each other by paths consisting of one or more edges, and are not connected to any other vertex in the same graph, are called a connected component. For example, in a graph G, vertex V1 is connected to V2 by an edge, and V2 is connected to V3 by another edge. In the same graph G, vertex V4 is connected to V5 by another edge. In this case, V1 and V3 are connected. V4 and V5 are connected, and V1 and V5 are not connected. In graph G, there are two connected components. The Spark graphics library has an implementation of the connected components algorithm. In a social networking application, if the connections between the users are modeled as a graph, finding whether a given user is connected to another user is achieved by checking whether there is a connected component with these two vertices. In computer games, maze traversing from point A to point B can be done using a connected components algorithm by modeling the maze junctions as vertices and the paths connecting the junctions as edges in a graph. In computer networks, checking whether packets can be sent from one IP address to another IP address is achieved by using a connected components algorithm. In logistics applications, such as a courier service, checking whether a packet can be sent from point A to point B is achieved by using a connected components algorithm. The figure on your screen shows a graph with three connected components. This figure is the pictorial representation of a graph. In it, there are three clusters of vertices connected by edges. In other words, there are three connected components in this graph. The use case of users in a social networking application in which they follow each other is taken up here again for elucidation purposes. By extracting the connected components of the graph, it is possible to see whether any two users are connected or not. This figure shows the user graph. In the graph depicted here, it is clearly evident that there are two connected components. It is easy to say that Thomas and Matthew are connected, and at the same time, Thomas and Martin are not connected. If the connected component graph is extracted, it can be seen that Thomas and Martin will have the same connected component identifier, and at the same time, Thomas and Martin will have a different connected component identifiers. Let's go to the Scala repo prompt, and here we import few necessary packages first. Next, we create the RDD with users as the vertices. And now, we create the edges connecting the users. Let's create a graph. We now find the connected components of the graph. After this, we extract the triplets of the connected components. Let's print the structure of the triplets. And now, we print the vertex numbers and the corresponding connected component ID. The connected component ID is generated by the system, and it is to be taken only as a unique identifier for the connected component. Next, we find the users in the source vertex with their CC ID. Similarly, let's find the users in the destination vertex with their CC ID. And now, we find the union. Then, we join with the name of the users. Lastly, we print the user names with their CC component ID. If two users share the same CC ID, then they are connected. There are some more graph processing algorithms available in the Spark graphics library, and a detailed treatment of the complete set of algorithms deserves a video course on its own. The point here is that the Spark graphics library provides very easy-to-use graph algorithms that fit very well into Spark's uniform programming model. Cool! In this video, we have dived into the connected component algorithm. In the next video, we will have a look at DataFrames and its queries. Hi, welcome to the last video of this section, Understanding DataFrames and its queries. Previously, we learned about connected component algorithm. In this video, we will explore the DataFrames and then create a graph. We will also apply filter and select only the needed edges. We will then create the DataFrame-based graph from Spark GraphX-based graph and finally convert the DataFrame-based graph to a Spark GraphX-based graph. The Spark GraphX library is the graph processing library that has the least programming language support. Scala is the only programming language supported by the Spark GraphX library. DataFrames is a new graph processing library available as an external Spark package developed by Databricks, University of California, Berkeley, and Massachusetts Institute of Technology, built on top of Spark DataFrames. Since it is built on top of DataFrames, all the operations that can be done on DataFrames are potentially possible on DataFrames, with support for programming languages such as Scala, Java, Python, and R with a uniform API. Since DataFrames is built on top of DataFrames, the persistence of data, support for numerous data sources, and powerful graph queries in Spark SQL are additional benefits users get for free. Just like the Spark GraphX library, in DataFrames the data is stored in vertices and edges. The vertices and edges use DataFrames as the data structure. The first use case covered in the beginning of this section is used again to elucidate DataFrames-based graph processing. Here's a caution. DataFrames is an external Spark package. It has some incompatibility with Spark 2.0. Because of that, the code which we are going to use here will not work with Spark 2.0. They work with Spark 1.6. You can refer to their website to check Spark 2.0 support. Now let's move to our Scala repo prompt of Spark 1.6. Since DataFrames is an external Spark package, while bringing up the appropriate repo, the library has to be imported and the commands are used in the terminal prompt to fire up the repo and make sure that the library is loaded without any error messages. Here, we import few essential packages. Next, we create a data frame of users containing tuple values with a mandatory long and another string type as the property of the vertex. Then, we create a data frame for edge with string type as the property of the edge. Now, we show the vertices in the graph. Next, we show the edges in the graph. Let's see the number of edges and vertices in the graph. Also, we see the number of edges coming to each of the vertex. Now, let's see the number of edges going out of each of the vertex. We now show the total number of edges coming in and going out of each vertex. Let's get the triplets of the graph. Using the DataFrame API, apply filter and select only the needed edges. Now, create an RDD of users containing tuple values with a mandatory long and another string type as the property of the vertex. Next, create an RDD of edge type with string type as the property of the edge. Here, we also create a graph containing the vertex and edge RDDs as created before. Now we step ahead and create the DataFrame-based graph from Spark GraphX-based graph, and let's display the triplets with the edges, source, and destination. And now we convert the DataFrame-based graph to a Spark GraphX-based graph. When creating data frames for the DataFrame, the only thing to keep in mind is that there are some mandatory columns for the vertices and the edges. In the data frame for vertices, the ID column is mandatory. In the data frame for edges, the SRC and DST columns are mandatory. Apart from that, any number of arbitrary columns can be stored with both the vertices and the edges of a graph frame. In the Spark GraphX library, the vertex identifier must be a long integer. But the graph frame doesn't have any such limitations, and any type is supported as the vertex identifier. You should already be familiar with data frames. Any operation that can be done on a data frame can be done on the vertices and edges of a graph frame. All the graph processing algorithms supported by GraphX are supported by DataFrames as well. The Python version of DataFrames has fewer features. Since Python is not a supported programming language for the Spark graphics library, GraphFrame to GraphX and GraphX to GraphFrame conversions are not supported in Python. Since readers are familiar with the creation of DataFrames in Spark using Python, the Python example is omitted here. Moreover, there are some pending defects in the GraphFrames API for Python, and not all the features demonstrated previously using Scala function properly in Python at the time of creating this video. Let's now dive into GraphFrame queries. The Spark graphics library is the RDD-based graph processing library, but GraphFrames is a Spark DataFrame-based graph processing library that is available as an external package. Spark GraphX supports many graph processing algorithms, but GraphFrames supports not only graph processing algorithms, but also graph queries. The major difference between graph processing algorithms and graph queries is that graph processing algorithms are used to process the data hidden in a graph data structure, while graph queries are used to search for patterns in the data hidden in a graph data structure. In GraphFrame parlance, graph queries are also known as motif finding. This has tremendous applications in genetics and other biological sciences that deal with sequence motifs. From a use case perspective, take the use case of users following each other in a social media application. Users have relationships between them. In the previous sections, these relationships were modeled as graphs. In real-world use cases, such graphs can become really huge, and if there's a need to find users with relationships between them in both directions, it can be expressed as a pattern in graph query, and such relationships can be found using easy programmatic constructs. The demonstration used here models the relationship between the users in a graph frame, and a pattern search is done using that. We move to the Scala repo prompt of Spark 1.6 and import some essential packages here. First, we create a data frame of users containing tuple values with a mandatory string field as ID, and another string type as the property of the vertex. Here, it can be seen that the vertex identifier is no longer a long integer. Next, we create a data frame for edge with string type as the property of the edge. Let's create the graph frame. Now, search for pairs of users who are following each other. In other words, the query can be read like this. Find the list of users having a pattern such that the user U1 is related to user U2 using the edge E1, and user U2 is related to the user U1 using the edge E2. When a query is formed like this, the result will list with columns U1, U2, E1, and E2. When modeling real-world use cases, more meaningful variables can be used suitable for the use case. Let's now show the graph query. Note that the columns in the graph query are formed with the elements given in the search pattern. There is no limit to the way the patterns can be formed. Note that the data type of the graph query result. It is a data frame object. That brings a great flexibility in processing the query results using the familiar Spark SQL library. The biggest limitation of the Spark graphics library is that its API is not currently supported with programming languages such as Python and R. Since GraphFrames is a data frame-based library, once it is matured, it will enable graph processing in all the programming languages supported by DataFrames. This Spark external package is definitely a potential candidate to be included as part of the Spark. For more information related to GraphFrames, you can visit this link, spark.apache.org. To get the overview of the GraphFrames, you can also read at graphframes.github.io/index.html. And for Spark package information, you can visit at spark-packages.org/package/graphframes/graphframes. Amazing! In this section, we had a whirlwind tour of the Spark graphics library and covered some of the basics through use cases at an introductory level. We also used the tennis tournament results for analysis and applying PageRank. We also explored about connected component algorithm and graph frames. In the next section, we will cover the design and development of a data processing application using Spark and the family of libraries built on top of it. Hey there! Welcome to the last section of this video course, Designing the Spark Architecture. In this section, we will cover the design and development of a data processing application using Spark and the family of libraries built on top of it. we will start with the Lambda architecture and then swiftly move to microblogging with Spark. We will then explore data dictionaries and coding style, and finally, we will dive into data ingestion. Let's move on to the first video of this section, Lambda architecture. In this video, we're going to take a look at different layers of Lambda architecture. Application architecture is very important for any kind of software development. It is the blueprint that decides how the software has to be built with a good amount of generality and the capability to customize when needed. For common application needs, some popular architectures are available, and there's no need for any ground-up architecture effort in order to use them. These public architecture frameworks are designed by some of the best minds for the benefit of the general public. These popular architectures are very useful because there's no barrier to entry, and they are used by so many people. There are popular architectures available for web application development, data processing, and so on. Let's now talk about Lambda architecture. So, Lambda architecture is a recent and popular architecture that's ideal for developing data processing applications. There are many tools and technologies available in the market to develop data processing applications. But independent of the technology, how the data processing application components are layered and composed together is driven by the architectural framework. That is why Lambda architecture is a technology-agnostic architecture framework, and, depending on the need, the appropriate technology choice can be made to develop the individual components. The figure which you see captures the essence of Lambda architecture. Lambda architecture consists of 3 layers. Let's have a look at all of these. First is the batch layer, which is the main data store. Any kind of processing happens on this dataset. This is the golden dataset. Next comes the serving layer, which processes the master dataset and prepares views for specific purposes, and they are termed purposed views here. This intermediate step of processing is required to serve the queries or for generating outputs for specific needs. The queries and the specific dataset preparation don't directly access the master dataset. And the last one is the speed layer, which is all about data stream processing. The stream of data is processed in a real-time fashion, and volatile real-time views are prepared if that is a business need. The queries or specific processes generating outputs may consume data from both the proposed data views and real-time views. Using the principles of Lambda architecture to architect a big data processing system, Spark is going to be used here as a data processing tool. Spark fits nicely into all the data processing requirements in all 3 distinct layers. This section is going to discuss some selected data processing use cases of a microblogging application. The application functionality, its deployment infrastructure, and the scalability factors are beyond the scope of this work. In a typical batch layer, the master dataset can be plain splittable serialization formats or no SQL data stores, depending on the data access method. If the application use cases are all batch operations, then standard serialization formats will be sufficient. But if the use cases mandate random access, no SQL data stores will be ideal. Here, for the sake of simplicity, all the data files are stored in plain text files locally. Typical application development culminates in a completely functional application. But here, the use cases are realized in Spark data processing applications. Data processing always works as a part of the functionality of the main application, and it is scheduled to run in batch mode or run as a listener, waiting for data and processing it. So, corresponding to each of the use cases, individual Spark applications are developed, and they can be scheduled or made to run in listener mode as the case may be. Cool! In this video, we've had a look at Lambda architecture. In the next video, we'll learn about microblogging with Lambda architecture. We are now at the second video of this section, microblogging with Lambda architecture. In the previous video, we looked at different layers of the Lambda architecture. In this video, we'll learn about microblogging with Lambda architecture. We will first have an overview of SFB microblog, and then we will understand the different data sets in a blog. We will also see how to set the data dictionary. Blogging has been around for a couple of decades in various forms. In the initial days of blogging as a medium of publication, only professional or aspiring writers published articles through the medium of blogs. It spread the false notion that only serious content is published through blogs. In recent years, the concept of microblogging included the general public in the culture of blogging. Microblogs are sudden outbursts of the thought processes of people in the form of a few sentences, photos, videos, or links. Sites such as Twitter and Tumblr popularized this culture at the biggest scale possible, with hundreds of millions of active users using the site. Let's have an overview of SFB Microblog. SFB Microblog is a microblogging application with millions of users posting short messages. A new user who's going to use this application needs to sign up with a username and password. To post messages, users have to sign in first. The only thing users can do without signing in is read public messages posted by users. Users can follow other users. The act of following is a one-way relationship. If user A follows user B, user A can see all the messages posted by user B. At the same time, user B cannot see the messages posted by user A because user B is not following user A. By default, all the messages posted by all the users are public messages and can be seen by everybody. But users have settings to make messages visible only to users who are following the message owner. After becoming a follower, unfollowing is also allowed. Also, usernames have to be unique across all users. A username and password are required to sign in. Every user must have a primary email address, and without that, the sign-up process will not be complete. An alternate email address or mobile phone number can be saved in the profile. Messages cannot exceed 140 characters. Messages can contain words prefixed with the hashtag symbol to group them under various topics. Messages can contain usernames prefixed with the @ symbol to directly address users through messages that are posted. In other words, users can address any other user in their messages without being a follower. Once posted, the messages cannot be changed. Once posted, the messages cannot be deleted. Let us now get familiar with data. All pieces of data that come to the master dataset come through a stream. The data stream is processed. An appropriate header for each message is inspected, and the right action to store it in the data store is done. Here's the list that contains the important data items that come into the store through the same stream. The user dataset contains the user details when a user signs in or when a user's data gets changed. Next comes the follower. This dataset contains the relationship data that gets captured when a user opts to follow another user. And the last one is message. This dataset contains the messages posted by registered users. This list of datasets forms the golden dataset. Based on this master dataset, various views are created that cater to the needs of the vital business functions in the application. Whereas the second list contains the important views of the master dataset. Messages by users. This view contains messages posted by each user in the system. When a given user wants to see the messages posted by him or her, the data generated by this view is used. This is also used by the given user's followers. This is a situation where the main dataset is used for a specific purpose. The message dataset gives all the required data for this view. Next is messages to users. In the messages, specific users can be addressed by prefixing the @ symbol followed by the addressee's username. This data view contains the user's address with the @ symbol and the corresponding messages. There is a limitation enforced in the implementation. You can only have one addressee in one message. Then comes tagged messages. In the messages, words prefixed with the hashtag symbol become searchable messages. For example, the word #Spark in a message signifies that the message is searchable by the word #Spark. For a given hashtag, users can see all the public messages and the messages of users whom he or she is following in one list. This view contains pairs of the hashtag and the corresponding messages. There is a limitation enforced in the implementation. You can only have one tag in one message. We also have follower users. This view contains the list of users who are following a given user. In this figure, users U1 and U3 are in the list of users following U4. And the last one we have is followed users. This view contains the list of users who are followed by a given user. In this figure, users U2 and U4 are in the list of users who are followed by user U1. In a nutshell, the figure which you see gives the Lambda architecture view of the solution and gives details of the datasets and the corresponding views. Let us see how to set the data dictionary. The data dictionary describes the data, its meaning, and its relationship with other data items. For the SFB microblog application, the data dictionary is going to be a very minimalistic one to implement the selected use cases. Using this as a base, readers can expand and implement their own data items and include data processing use cases. The data dictionary is given for all the master datasets as well as the data views. The table on your screen shows the data items of the user dataset. The next table captures the data items of the follower dataset, while this table captures the data items of the message dataset. Now, here's the table capturing the data items of the message to users view. Finally, we have the table which captures the data items of the tagged messages view. The follower relationship of the users is pretty straightforward and consists of the pairs of the user identification numbers persisted in a data store. Superb! In this video, we've seen about microblogging with Lambda architecture. In the next video, we'll see how to implement Lambda architecture and work with Spark applications. This is the third video of this section, implementing Lambda architecture and working with Spark applications. In the previous video, we looked at microblogging with Lambda architecture. In this video, we'll learn about the implementations of Lambda architecture at different layers, and we will then see the working with Spark applications. The concept of Lambda architecture was introduced in the beginning of this section. Since it is a technology-agnostic architecture framework, when designing applications with it, it is imperative to capture the technology choices used in specific implementations. This video does exactly that. So let us start with the batch layer. The core of the batch layer is a data store. For big data applications, there are plenty of choices for data stores. Typically, Hadoop Distributed File System, HDFS, in conjunction with Hadoop Yarn, is the current and accepted platform in which data is stored, mainly because of the ability to partition and distribute data across the Hadoop cluster. There are two types of data access any persistent store supports. One is the batch write or read, and the other one is random write or read. Both of these need separate data storage solutions. For batch data operations, typically splittable serialization formats such as Avro and Parquet are used. For random data operations, typically NoSQL data stores are used. Some of these NoSQL solutions sit on top of HDFS and some don't. It doesn't matter whether they are on top of HDFS or not. They provide partitioning and distribution of data. So depending on the use case and the distributed platform that is in use, appropriate solutions can be used. When it comes to the storage of the data in HDFS, commonly used formats such as XML and JSON fail because HDFS partitions and distributes the files. When that happens, these formats have opening tags and ending tags, and splits at random locations in the file make the data dirty. Because of that, splittable file formats such as Avro or Parquet are efficient for storing in HDFS. When it comes to the NoSQL data store solutions, there are many choices in the market, especially from the open source world. Some of these NoSQL data stores, such as HBase, sit on top of HDFS. Some of the NoSQL data stores, such as Cassandra and React, don't need HDFS, can be deployed on regular operating systems, and can be deployed in masterless fashion so that there is no single point of failure in a cluster. The choice of the NoSQL store is again dependent on the usage of a particular technology within the organization, the production support contracts in place, and many other parameters. This video course doesn't recommend a given set of data store technologies for usage in conjunction with Spark because Spark drivers are available in abundance for most popular serialization formats and NoSQL data stores. In other words, most of the data store vendors have started supporting Spark in a big way. Another interesting trend these days is that many of the prominent ETL tools have started supporting Spark, and because of that, those who are using such ETL tools may use Spark applications within their ETL processing pipelines. In this application, neither an HDFS-based or any NoSQL-based data store is being used in order to maintain simplicity and to avoid the complex infrastructure setup required to run the application for the readers. Throughout, the data is stored on the local system in text file formats. Readers who are interested in trying out the examples on HDFS or other NoSQL data stores may go ahead and try them with some changes to the data write-read part of the application. Next, we jump into the serving layer. So, the serving layer can be implemented in Spark using various methods. If the data is not structured and is purely object-based, then the low-level RDD-based method is suitable. If the data is structured, a DataFrame is ideal. The use case that is being discussed here is dealing with structured data, and hence, wherever possible, the Spark SQL library is going to be used. From the data stores, data is read and RDDs are created. The RDDs are converted to DataFrames, and all the serving needs are accomplished using Spark SQL. In this way, the code is going to be succinct and easy to understand. Now we move on to the speed layer. The speed layer is going to be implemented as a Spark streaming application using Kafka as the broker with its own producers producing the messages. The Spark streaming application will act as the consumer to the Kafka topics and receive the data that is getting produced. As discussed in the section covering Spark streaming, the producers can be the Kafka console producer or any other producer supported by Kafka. But the Spark streaming application working as the consumer here is not going to implement the logic of persisting the processed messages to the text file, as they are not generally used in real-world use cases. Using this application as a base, readers can implement their own persistence mechanism. Let us now talk about queries. So here, the queries are all generated from the speed layer and serving layer. Since the data is available in the form of DataFrames, as mentioned before, all the queries for the use case are implemented using Spark SQL. The obvious reason is that Spark SQL works as a consolidation technology that unifies the data sources and destinations. When you are using the code samples from this video course and when you're ready to implement it in the real-world use cases, the overall methodology can remain the same, but the data sources and destinations may differ. Here are some of the queries that can be generated from the serving layer. It is up to your imagination to make the required changes to the data dictionary and be able to write these views or queries. Find the messages that are grouped by a given hashtag, and also that are addressed to a given user. Find the followers of a given user, and find the followed users of a given user. We are now ready to explore about the working with Spark applications. So let's do it! The workhorse of this application is the data processing engine consisting of many Spark applications. In general, they can be classified into these types. A Spark streaming application to ingest data. That is the main listener application that receives the data coming as a stream and stores it in the appropriate master dataset. Next is a Spark application to create proposed views and queries. This is the application that is used to create various proposed views from the master datasets. Apart from that, the queries are also included in this application. And the last one is the Spark GraphX application to do custom data processing. This is the application that is used to process the user-follower relationship. All these applications are developed independently and they are submitted independently, but the stream processing application will be always running as a listener application to process the incoming messages. Apart from the main data streaming application, all the other applications are scheduled like regular jobs, such as cron jobs in a Unix system. In this application, all these applications are producing various proposed views. The scheduling depends on the kind of application and how much delay is affordable between the main dataset and the views. It completely depends on the business functions. So this section is going to focus on Spark application development rather than scheduling to keep the focus of the concepts learned in the earlier sections. It is not ideal to persist the data from the speed layer into text files when implementing real-world use cases. For simplicity, all the data is stored in text files to empower all levels of viewers with the simplest setup. The speed layer implementation using Spark streaming is a skeleton implementation without the persistence logic. You can enhance this to introduce persistence to their desired data stores. Wonderful! In this video, we've learned to capture the technology choices used in specific implementations of the Lambda architecture. In the next video, we'll learn about coding style, setting up the source code, and we'll also understand data ingestion. We are now at the fourth video of this section, coding style, setting up the source code, and understanding data ingestion. Previously, we looked at implementing Lambda architecture and working with Spark applications. In this video, we will first have a look at coding style and then see how to set up the source code. We will also understand data ingestion and how to work on it with Spark. Let us begin with coding style. Coding style has been discussed, and lots of Spark application programming has been done in the earlier sections. By now, it has been proven in this video course that Spark application development could be done in Scala, Python, and R. In most of the earlier chapters, the languages of choice were Scala and Python. In this section, the same trend will continue. Only for the Spark graphics application, since there is no Python support, will the application be developed in Scala alone. The style of coding is going to be simple and to the point. The error handling and other best practices of application development are avoided deliberately to focus on the Spark features. In this section, wherever possible, the code is run from the appropriate language's Spark REPL. Since the anatomy of the complete application and the scripts to compile, build, and run them as applications have already been covered in the section that discussed Spark streaming, the source code download will have it available as complete, ready-to-run applications. Moreover, the section covering Spark streaming discussed the anatomy of a complete Spark application, including the scripts to build and run Spark applications. The same methodology will be used in the applications that are going to be developed in this section too. When running such standalone Spark applications, as discussed in the initial sections of this video course, you can enable Spark monitoring and see how the application is behaving. For the sake of brevity, these discussions will not be taken up again here. Let us see how to set up the source code. As you can see that the structure of the source code and the data directories that are being used in this section. A description of each of them is not provided here, as you should be familiar with them, and they've been covered in the previous section, Spark Stream Processing. There are external library file dependency requirements for running the programs using Kafka. For that, the instructions to download the jar file are in the todo.txt file in the lib folders. The submitpy.sh and submit.sh files use some of the Kafka libraries in the Kafka installation as well. All these external jar file dependencies have already been covered in the previous section, Spark Stream Processing. So we go to todo.txt file and click on it. Here you can see that it is a jar file with a link to obtain it. You need to just copy this link, move to your browser, and enter the URL and click Enter and download this file. You need to place this file in the lib folder. Let us now understand what is data ingestion. The Spark streaming application works as the listener application that receives the data from its producers. Since Kafka is going to be used as the message broker, the Spark streaming application will be its consumer application, listening to the topics for the messages sent by its producers. Since the master dataset in the batch layer has three datasets, that is user dataset, following dataset, and message dataset, it is ideal to have individual Kafka topics for each of the topics along with the datasets. Screen provides an overall picture of the Kafka-based Spark streaming application structure. Since the Kafka setup has already been covered in the section Spark Stream Processing, only the application code is covered here. The entire scripts are run from a terminal window. Make sure that the Kafka home environment variable is pointing to the directory where Kafka is installed. Also, it is very important to start Zookeeper, the Kafka server, the Kafka producer, and the Spark streaming log event data processing application in separate terminal windows. Once the necessary Kafka topics are created as shown in the scripts, the appropriate producers have to start producing messages. You can refer to the Kafka setup details that have already been covered in previous section Spark Stream Processing before proceeding further. Let us move to the terminal window prompt now. Here, we first start the Zookeeper. Next, we start the Kafka broker in a separate terminal window. We now create the necessary Kafka topics. This is to be done in a separate terminal window. Now, open one more terminal window and start producing message and publish it to the topic which we have created earlier. So, we provide the details of the Scala code for the Kafka topic consumer application that processes the messages produced by the Kafka producer. The assumption before running the code is that Kafka is up and running. The required producers are producing messages, and then, if the application is run, it will start consuming the messages. The Scala program for the data ingestion is run by submitting it to the Spark cluster. Starting from the Scala directory, we first compile the program and then run it. The readme.txt file is to be consulted for additional instructions. Here, we use two commands, compile.sh and submit.sh, to compile and run the program. So let's do it. So, you can see that batches are being processed. You can also go to the local server and go on entering these commands here. You can notice that you get the same message which you type in the other terminal along with the time intervals. So, the program can be compiled and run using SBT wrapper scripts, which you can find here. We have given here the log level settings. Also, we have defined the checkpoint directory for the recovery. Next, we have used variables for creating the Kafka stream and Zookeeper host. We have also defined the Kafka message group. Kafka topic, where the programming is listening for the data. Next, we create the Spark session, the Spark context, and the streaming context. This is where the messages are printed to the console. As an exercise for you, instead of printing messages to the console, implement your own persistence logic. Then, we do checkpointing for the recovery and return the Spark streaming context. Note the function that is defined above for creating the Spark streaming context is being used here to create the Spark streaming context. Then, we start the streaming and wait till the application is terminated. We have also defined the log settings with this code. This is to make sure that the console is clean from other info messages printed by Spark. Let's open a new terminal window. The Python program for the data ingestion is run by submitting it to the Spark cluster. Starting from the Python directory, we run the program. The readme.txt file is to be consulted for additional instructions. All the Kafka installation requirements are valid even when running this Python program. Since Python is an interpreted language, there is no compilation required here. Let's do the Python implementation of the same application. So we first navigate to the right directory. Now, in the Python directory, we run the submitpy.sh command. As you can see, after every 10 seconds, it will print the time. Also, you can refer the readme.txt file for more information. We have run this file, dataingestionapp.py, and included these codes in it. So, we've used the script to run this application in Spark. We are now at the dataingestionapp.py1 file. Here, we first create the Spark context. Next, we create the Spark streaming context with 10 seconds batch interval. Then, we set the checkpoint directory setting, and also the Zookeeper host. We have also defined the Kafka message group. Here's Kafka topic, where the programming is listening for the data. Here, only one topic is included. It can take a comma-separated string containing the list of topics. When using multiple topics, use your own logic to extract the right message and persist to its data store. Next, we create a Kafka dstream. This is where the messages are printed to the console. Instead of this, implement your own persistence logic. And now, you need to wait till the application is terminated. Cool! In this video, we've explored about coding style, setting up the source code. We also dived into data ingestion. In the next video, we will be learning about generating proposed views and queries. We are now at the 5th video of this section, generating proposed views and queries. In the previous video, we looked at coding style and setting up the source code. We also explored about data ingestion. In this video, we will load all the required data from persistent stores into DataFrames and then use these DataFrames and create various proposed views and queries. We'll now see the implementations in Scala and Python, which are the application that creates the proposed views and queries discussed in the previous video of this section. Let's move to the Scala repo prompt. Here, first we need to change the directory to point our data directory. So here, you can see the data directory with the three subdirectories, follower.txt, message.txt, and user.txt. Next, we define the case classes in Scala for the entities. Next, we define the utility functions that are to be passed in the applications. Now, let's load the user data into a dataset. Then we convert the dataset into DataFrame, and now we create a temporary view and show the data. Let's load the follower data into a dataset. And next, we convert the dataset into the DataFrame. Let's create a temporary view and display it. Now, we load the message data into a dataset. Next, we convert the dataset into DataFrame. Let's again create a temporary view and show the data for it. So, with these steps, we complete the process of loading all the required data from persistent stores into DataFrames. Here, the data comes from text files. In real-world use cases, it may come from popular NoSQL data stores, traditional RDBMS tables, or from Avro or Parquet serialized data stores loaded from HDFS. Let's see how to use these data frames and create various proposed views and queries. For this, we first create the proposed view of the message to users. Next, we convert the dataset into DataFrame. Let's create a temporary view and display it. After this, we create the proposed view of tagged messages. Now, convert the dataset into DataFrame. We again create the temporary view and display the message which we have stored. Let's have a look at the queries given in the use cases. So we find the messages that are grouped by a given hashtag. Now, we show the related data. Next, we find the messages that are addressed to a given user. Let's display these messages. Now, we need to find the followers of a given user, so we do it right here. Then, we find the followed users of a given user and also we display it. In this Scala code, the dataset and DataFrame-based programming model is being used because the programming language of choice was Scala. Now, since Python is not a strongly typed language, the dataset API is not supported in Python. Hence, the Python code which we're going to use now is the traditional RDD-based programming model of Spark in conjunction with the DataFrame-based programming model. So we now move on to the Python repo prompt. Here, we first change the directory to point to our data directory. Next, we load the user data into an RDD. Now convert the RDD into DataFrame. To view the data, we create a temporary view and show it. Let's load the follower data into an RDD. After this, we load the message data into an RDD. Now, let's convert the RDD into DataFrame. Let's again create a temporary view and display it. So, with these steps, we have completed the process of loading all the required data from persistent stores into DataFrames. Here, the data comes from text files. In real-world use cases, it may come from popular NoSQL data stores, traditional RDBMS tables, or from Avro or Parquet serialized data stores loaded from HDFS. Let's now use these data frames and create various proposed views and queries. So here, we create the proposed view of the message to users. Next, we convert the RDD into DataFrame. Here, we create a temporary view and display its data. Let's create the proposed view of tagged messages. And now convert the RDD into DataFrame. Again, create a temporary view and display the data. Let's move to the queries given in the use cases. So find the messages that are grouped by a given hashtag. Now, we display the data as well. Next, find the messages that are addressed to a given user. Also display the details. Now, find the followers of a given user and display the list. Finally, find the followed users of a given user and show the list. Awesome! The proposed views and queries required to implement the use cases are developed as a single application. But in reality, it is not a good design practice to have all the views and queries in one application. It is good to separate them by persisting the views and refreshing them at regular intervals. If using only one application, catching and the use of custom-made context objects that are broadcasted to the Spark cluster could be employed to access the views. In this video, we've learned to generate proposed views and queries. In the next video, we will dive into custom data processes. Hello! We are now at the last video of this video course. Previously, we saw how to generate proposed views and queries. In this video, we will create a user graph with the users and the vertices and the connection relationship forming the edges. On this graph data structure, we will run the graph processing algorithm, the connected component algorithm, and get a list of users and their connected component identification numbers. The views created here were created to serve various queries and to produce desired outputs. There are some other classes of data processing applications that are often developed to implement real-world use cases. From the Lambda architecture perspective, this also falls into the serving layer. The reason why these custom data processes fall into the serving layer is mainly because most of these use or process data from the master dataset and create views or outputs. It is also very possible for the custom processed data to remain as a view, and the coming use case is one of such cases. In the SFB microblogging application, it is a very common requirement to see whether a given user A is in some way connected to user B in a direct follower relationship or in a transitive way. This use case can be implemented using a graph data structure to see whether the two users in question are in the same connected component, whether they are connected in a transitive way or whether they are not connected at all. For this, a graph is constructed with all the users as the vertices and the follow relationship as edges using a Spark graphics library-based Spark application. Let us now move to the Scala repo prompt, and here we will import few essential packages. Here, we first change the directory to point to your data directory. Next, we define the case classes in Scala for the entities. Now, we define the utility functions that are to be passed in the applications. Let's load the user data into an RDD. Then convert the RDD into DataFrame. Here, we create a temporary view and display the data. Now we load the follower data into an RDD. Let's now convert the RDD into DataFrame and again create a temporary view to display the data. Now we join the follower and followee users with the master user DataFrame for extracting the unique IDs. Next, create the vertices of the connections graph, and after this, display the connections on the terminal. Also, we create the edges of the connections graph, and let's print it. We then create the graph using the vertices and the edges. The user graph with the users and the vertices and the connection relationship forming the edges is done. On this graph data structure, run the graph processing algorithm, the connected component algorithm. So let's do it right now. For this, we first calculate the connected users, so here what you see are the warnings which you can ignore. Next, we extract the triplets of the connected users. Lastly, we print the structure of the triplets. The connected component graph, CC, and its triplets, CC triplets, are created, and this can now be used to run various queries. Since the graph is an RDD-based data structure, if it's necessary to do queries, converting the graph RDD to data frames is a common practice. Let us have a look now how we could do it. So, we print the vertex numbers and the corresponding connected component ID. The connected component ID is generated by the system, and it is to be taken only as a unique identifier for the connected component. Also, let us show how the graphs are connected. Then, we find the users in the source vertex with their CC ID. After this, we find the users in the destination vertex with their CC ID. Now we find the union. Let's join with the name of the users and convert the RDD to DataFrame. Finally, we print the usernames with their CC component ID. If two users share the same CC ID, then they are connected. Fantastic! Using this implementation of a proposed view to get a list of users and their connected component identification numbers, if there is a need to find out whether two users are connected, you can just read the records of those two users and see whether they have the same connected component identification number. For more information, you can visit this link and read this web documentation, www.dre.vanderbilt.edu. Or you can also find more information at lambda-architecture.net. This section concludes this video course with one single application's use cases implemented using the Spark concepts learned in the earlier sections. From a data processing application architecture perspective, this section covered the Lambda architecture as a technology-agnostic architectural framework for data processing applications, which has huge applicability in the big data application development space. From a data processing application development perspective, RDD-based Spark programming, dataset-based Spark programming, Spark SQL-based DataFrames to process structured data, the Spark streaming-based listener program that constantly listens to the incoming messages and processes them, and the Spark graphics-based applications to process follower relationships have been covered. The use cases covered so far have immense scope for viewers to add their own functionalities and enhance the application use cases discussed in this section. Wonderful! I hope you've enjoyed learning Spark from this course as much as I have in creating it. Wish you all the good luck.